also, and I'll start again. Professor Otto Koudelka is a full professor of communications at TUGraz University in Austria. He's also the program director of this program, so I'd like to hand over to him so he can give a few words of introduction. Otto, can you move your camera down because we see your eyes?
Yes, can you hear me?
Yes, we can, thank you.
Okay, so thank you very much, Jose. Good morning, ladies and gentlemen, dear participants. Also a warm welcome to the Alumni Symposium. And I would like to say a few words about SpaceTech. SpaceTech has a long tradition. It was originally hosted by Delft University and found its restart and is now hosted by Graz University of Technology. Our university, Space, has also a long tradition, and we have a long track record in space activities. Very first Austrian space object, an ionospheric probe, was put on a ballistic flight on board of a Norwegian sound rocket already in 1969, the year when Neil Armstrong and Edwin Aldrin landed on the moon. And another milestone has been the launch of the first Austrian satellite in 2013. Which was developed by my institute. It's an astronomical satellite as part of the Bright constellation, and the satellites are still working, which makes us quite proud. I'm also very glad that one of the founding fathers of SpaceTech, Professor Heinz Stohler, is today with us in presence. I apologize that I couldn't come to ESTEC, so I deliver my message here by electronic means. SpaceTech is a unique postgraduate master studies program on space systems and business engineering, focusing its curriculum on experts with several years of experience working in the aerospace sector, international mid-career professionals seeking top-level expertise in space systems and business engineering. It is a fully accredited studies program compliant with the Bologna process, and it's running over 18 months. We have 6 sessions with mandatory attendance, each lasting 2 weeks and located normally at 6 European space centers, starting and finishing at GEOGraz, then another session at CNES in Toulouse, another one at ESOC in Darmstadt, one at GSOC, in the DLR center near Munich, one at ESA Esrin, one at ESA Estec, and we have a lot of accompanying online courses. Central case project is conducted in a team. Also, each individual participant has to write a master thesis with the defense. This will take place in September here at GEOGraz. And the participants will finish with a degree in Master of Engineering in Space Systems and Business Engineering. By combining online lessons with lessons taught on site, the course has been very well designed to the needs of people who are working. So there are these normal present sessions. This year we had, or in this course, we had to face a particular problem due to COVID, but I come to that in a moment. The topics are applied project management, business engineering, space mission analysis and design, telecommunications, Earth observation, system engineering, navigation, and this we added in the new curriculum, human spaceflight. Very special is the central case project, which is typically defined by a sponsoring organization, this year by ESA ESOC, and the topic is space situation awareness and space debris monitoring. We have a really outstanding team of 11 participants from 8 countries. Several of them have already a PhD degree, and they have been elaborating fascinating design of an innovative space debris monitoring mission in the GeoBelt. This is both from an engineering standpoint, but also they developed a very good, valid business case. And you will hear later today the summary of the CCP presented by the participants' team. Normally, SpaceTech, as said, is conducted in present sessions at the various space centers, but due to COVID, had to run it online. A big challenge, but which was mastered very well. So here at ESTEC, it has been the first time that the participants could meet in person, but we are all very impressed by the professionalism and how well the team managed the work via teleconferences and by online tools. Unfortunately, we had to face during the conduct of SpaceTech a very sad situation, which we had all to cope with. Our dear participant, Emilio De Pasquale, ATCS and systems engineer, ESA, suddenly died. And he had been very important contributor and a true friend. So we will always keep a deep memory, and it is excellent that the team decided to dedicate the CCP to him. Also, we'll convey best wishes to other participants, Maria Nestoridi, who is currently hospitalized and cannot be with us and in the presentation. So we wish her a fast and good recovery, and we hope that she can be at the final session in Graz. It is now the time to thank many institutions and persons. First of all, I would like to thank Director Franco Ongaro, who hosted us here at ESTEC and made this possible, which was not so easy. And it has been a real benefit to the team, so that for the first time in the whole course, they had to be able to sit around, discuss, and also meet the coaches in person. Also, many thanks are due to Holger Krag from ESOC, who supported the CCP financially. He defined the topic and supported the team by lecturing and giving constant advice to them. I would also like to thank all the coaches, in particular the head coach, Wiley Larsen, the co-director, Jeff Austin and Uli Fricke, as well as the many lecturers for various space topics. And my special thanks go to my colleague Peter Schrotter, who is the SpaceTech program manager and who makes, with his endless effort, all the organization possible and flawless. Many thanks, Peter, and thanks are also due to the rectorate. Yes, this is very appropriate. Thanks are also due to the rectorate of TUGraz and especially the head of lifelong learning, Ernst Kreutzer, for continuing support. At this point, I also wish to acknowledge the key contribution by my friend and colleague Ed Ashford, another SpaceTech founding father. He was formerly the ESA head of satellite systems and a longtime space director at Delft. He successfully persuaded me during the IAC Naples over a beer or two to embrace the SpaceTech program, which was an excellent decision, and he also helped us establish it with an extended curriculum, and he was SpaceTech director until SpaceTech 2018-2019. Finally, I wish to thank Jose Pizarro and John Irving, who have been very active organizing this Alumni Symposium, and I wish you all an exciting day. Thank you very much.
Thank you, Otto. I'll get used to this one of these days. Now I'd like to introduce Heinz Stohler. I was going to give you his bio, but I looked on the internet and there's like 14 bullet points. Suffice to say, of all the senior positions in ESA and European industries had over the years, I think the most important one to us is that he helped found SpaceTech and allow us all to develop ourselves as system engineers. Heinz, over to you.
Thank you, Jose, and good morning. Good morning also wherever you are virtually attending this session. Wiley asked me with his charm and with his retching, you should come and say a little bit about something of the background, the history of SpaceTech. Now, I grudgingly accepted, but I'll do that just very shortly because I also want to leave a message with you, namely, where is the future of system engineering going to? Well, firstly, when I listened to the presentations yesterday, I felt straight away back home again, because you created the spirit that we've initiated in this program from the very first day by showing a team performance on a project which is very down to earth, in quotation marks, and which is an innovative approach to doing things in a context of education. This innovation was what drove us when we set up the program. Background in very short terms is, while I was here in Estec, in this wonderful center in which I haven't been for 1.5 years, I headed the Department of Systems Engineering and Programmatics. And while I did this, TU Delft approached me whether I could teach in Delft. Well, I organized a group of our collaborators of Estec, amongst them at Ashford, to teach in Delft. Well, this grew out to a professorship for myself, which always was a part-time professorship because I never had time to be a full-time professor. But when I eventually retired from the German Space Agency, where I was a managing director for running most of the projects, there was an opportunity to build this SpaceTech program in Delft. It wasn't my idea, it was the idea of 3 of my students who had sat together with a couple of people in Delft and create the idea of a postgraduate program. Postgraduate program for system engineering was exactly down my line, because I don't really think, even though I teach system engineering all around the world, I don't think system engineering is a first engineering profession or education. You need to have some experience first in real life on one or the other or several technical subjects before you can really stand up and say, I understand the implementation, now I want to understand the horizontal integration. Because it's this T system that system engineers need to have: depth in engineering and breadth in engineering at the same time. Now in SpaceTech we've gone one step further, namely we said the development of space is going to be commercial, and the teaching of system engineering is best if it is oriented around some commercial approaches. So that brought us into that direction. One step back, my good friend Wiley was the first one I contacted when I set up a curriculum committee at that time. I didn't know Wiley from anywhere, but I saw and I've read SMED. And I said, darn it, if I'd written a book on system engineering, it would have been something like SMED. So I called Wiley. I had no idea where he was, whether it was in America or wherever. He's always somewhere. And he was in Strasbourg at the ISU. I said, Wiley, come here, we want to talk. So Wiley and I talked for a day and found that we were in violent agreement on our approach to system engineering, which is another reason I'm so happy that Wiley is still so deeply involved with SpaceTech, because that was the foundation. We then added somebody from the Earth observation field, from the communication field, and from the programmatics, because we wanted that this has a commercial background, deals with business, because system engineers need to deal with business, they need to deal with technical things, they need to deal with this full spectrum or matrix of what needs to be done to get things done. And it should be engineering oriented. One little story on the side that most of you will never have heard. We were lucky in the timing, because as it turns out, about the same time MIT had set up a systems management program, and they were traveling through Europe trying to sell their program and get everybody convinced to join that program. But wherever they came at that time, well, We just heard there is a program in Delft called SpaceTech. What can you do better than they do? And in the end, they just grudgingly went back to Boston and Cambridge and didn't succeed in settling it in Europe. Because one other principle, and you were again witness to that, was that we wanted it to be not in a hotel somewhere, but we wanted it in the middle of the space centers. And the most difficult sell, I admit it, was to sell my Toulouse friends from the schools and from the center to accept it as a program which was not invented in France, which was invented somewhere else, and you know the stories a little bit. But finally, Toulouse became and still is one of the strongest supporters, because it is and has been a wonderful and a very, very good program. The story of MIT, incidentally, was a couple of years later. We've had one of their professors come and teach with us. A couple of years later, MIT said, SpaceTech is the best system engineering program for space worldwide. So we became friends again, and ever since been friends. I've been teaching MIT, and they've come here perfectly set up. So that's, in a few words, the history of SpaceTech. And I'm extremely grateful that people like Jeff Austin are still in it. Wiley, of course, I've heard all the good deeds he's done for you again this year. It's fantastic. I cannot name everybody, but I'm of course very happy to come back to what Otto just said, that Graz was taking it over under not quite easy circumstances and so forth. Now, I said I'm going to speak about a second subject. Now, I'll do that just as rapidly. I don't know whether I still have 3 minutes or 5. 3, 4, good. Because I brought a present with me, which I cannot deliver yet, but I can deliver it in something like 6 months from now, early next year. And it's a present which will shape your future. Every one of you here in this room, everyone who is an alumni out there, because it's about the future of system engineering. What is happening in the field of system engineering in the next 15 years? And it's a lot. It is probably much more than most people think. Background is, some of you may know that I've been the president, the first non-American, incidentally, president of the International Council on Systems Engineering, and been active in this organization ever since. And one of the actions that we're doing at the moment is create a Vision 2035 for system engineering. You'll be amazed if you really dig into this question from various different viewpoints, what you'll find out. We structured it in 4 different chapters, and the first one sets the scene. What is changing in the world? And it's not space, it's all industry, it's across industry. What is changing in the world in the next many years in terms of sustainability, in terms of digital transformation, in terms of mobility, in terms of smart systems? What are the mega trends in technology, the mega trends of system development, etc., etc.? Then we take a short view in where are we, globally speaking, on system engineering, we, the global system engineering community, today with the science or the profession of systems engineering, and then delve into what's going to happen in the next 15 years. It's fascinating because you come across lots of things. Obviously, the digital transformation is driving many things that we do. Franco just a bit before said software driven and changing things in space. Well, we're also maintaining machines in Indonesia from Germany, or we're running all kinds of things remotely in many ways. if you think this whole idea further, what does it mean to model-based systems engineering? You'll find a lot of surprises. My promise, and Jose is already standing up to stop me talking on, subject I could talk for the next 2 hours. My promise is to you, if you like, I will make available a copy of that vision. It's only a 50-60 page document for the for you, for the alumni, and for the participants. Quite obviously, I think you'll find a lot of interesting things there about your future. So thanking everybody again, Jose, for organizing the symposium. I understand. I greet all my previous students, and I wish you a good symposium. I'll stay for a little while, but the rest of my day is already scheduled. So thank you very much for having me. It is a pleasure to be here and to witness such a fantastic group of participants. Thank you.
Thank you very much, Professor Heinz. Now it's my great pleasure to present the next speaker. He has two roles. One, he's currently the head of the ESA Security Office, which means he's the equivalent of a Chief Information Security Officer for the agency. And he also used to be my boss. So without much more ado, Massimo, are you there?
Yes, I'm here, Jussi. So, thank you, Jussi. Thank you, everybody. It's a real pleasure to be here and to introduce this symposium with really my pleasure. Apologize not to be there in person, but it was literally impossible to finish a huge conference yesterday night in Esrin, and to come back in Estec was literally impossible. But I'm here at least to give my experience and some key message from this symposium, space technology and security, especially for what concern the security for space. And in line with what Franco says at the beginning, let me start to say that I am as well a very peaceful person. And but this does not mean, I always used to say, that I leave the door of my apartment open 24 hours. In somehow, we need to protect ourselves. We need to close the door when it's important and need to close the door. And for space is the same. And why is the same? Because we have seen in the last 10 years an increasing of importance of the space in the daily life of Europe, of the world. Now a lot of citizens and pillars of the society relying on space service. And therefore, security need to, let me say, adequately protect the availability, the integrity of the service that the space domain can offer. So, what is doing ESA and what, together with industry, what we are doing today in this important sector. ESA is doing a lot with their industry. I comes from, with John and Jose, from the Galileo world, in which the security for space with an important customer like a commission was very important. Tech in the last years has done a lot of technology study on cybersecurity, even before this word was becoming a fancy word used by everybody, maybe used too much by everybody. But then in 2019, in the ministerial of 2019, something happened, something that go beyond the importance of security in terms of technology. people start to be really aware of the importance of the security. People, not technology, people. And so we start to launch activity in this direction. And today, in the Agenda 2025 of the DG, and also in our personal agenda in the security office, security is one of the key factors. So which is the one of two first messages that I want to give you. Security is important, but cannot be the only factor to be taken into account. Security is important with respect to the activity that you are considering in front of yourself. Can be an activity, can be a project, need to be evaluated always with some question and the right answer. What I'm doing to do with this project in the next 5 years, in the next 10 years, which is the mission, which is the objective, and therefore in which way I can protect adequately this objective. This question and answer we call it the risk analysis, security risk analysis. And following the intervention of Mr. Haynes, let me say that the security, in order to be properly managed, need to be managed from the beginning of the system engineering. It's a process. If security is tackled at the end, has no value at all, can lead only to an enormous increasing of budget. People will not understand the value of security. Therefore, what we are trying to do and what we are doing, even changing the regulation and the framework of ESA in 2020, is to include the security and the security engineering and the security accreditation engineering in the life cycle of the project from the beginning, from the early stage of concept of mission. And when my colleagues sometimes come to me and say, "Ma Massimo, my project is fully unclassified." Yes. And do you know the level of damage that can occur if, for example, Galileo Open Service that is fully unclassified, the service go down? Could you understand the level of damage for the European citizen, for the civil domain of Europe? The fact that a project or an activity is fully unclassified, today it doesn't say anything. Because the threat, even if I know that this kind of word my friend Franco doesn't like, but the threat that are outside the space domain point not only to grab information for industrial purpose, but also to interfere with the availability of the service, the integrity of service for many reasons. And the challenge in front of us in the next 10 years is go exactly in this direction. We need to take care more on the availability, on the integrity of the parameter of our activity and service, because are the one more vulnerable. So what I was saying as a message, please consider to embed the security from the beginning, from the system engineering, from the IT. Risk analysis is not a word that need to be scared. I always say the risk analysis can be question and answer. We as a ESA, we are developing a model, the security office, threat modeling. We are supporting the security risk analysis. We are also analyzing in terms of strategy the evolution of potential threat in space for signal, for ground that can affect the space activity. Of course, this is a synergic work that we are carrying on with the term security, with the terminology of cybersecurity, together with all the directorate, especially with tech, but also with the support of industry. Technology, system engineering, awareness of the people need to be compared with the evolution of the threat. Because in 10 years from now, the space will consolidate their importance in the life cycle of the citizen, of the European citizen. Therefore, we need to be ready all together to protect this value. ESA is there, and we really looking forward for your help all together. Thank you. Thank you to everybody.
Thank you very much, Massimo. Before I present the next speaker, I'd just like to mention that if anybody has any questions, they can put them in the chat in the WebEx and we'll answer them or request an answer later on in the day. Now, the next speaker I would like to present is someone who's very important to the participants who presented their final project yesterday. His name is Holger Krach. He's head of the ESA Space Debris Office at ESA in Germany. He also sponsored the project yesterday.
Thank you very much, and good morning, everybody, and good morning on WebEx as well. And thanks a lot to the CCP team for that fantastic work. First of all, team effort that you did, and also the presentation pitch of yesterday. I listened to many pitches on the phone, on WebEx in person, and what you did was really outstanding compared to that. And what I selected as a topic today, space traffic management, is a word or a term you probably heard already, but it is a topic that I believe will come up more importantly in the near future. And it's triggered by the increasing amount of space traffic that we are seeing. And if you compare yourself as a satellite operator or manufacturer to a car operator or a plane operator, a pilot, as a pilot, you have a flight plan, you look at the weather forecast before you go off, you have a regime and flight rules to follow, and you react, and you have some automatism in reacting to critical events. As a car driver, you have the same. You have a training, you bring your car to regular checks, you have rules of the road, and that all exists. In space traffic, we don't have that, and it was not necessary perhaps so much in the past, but things are changing as we see in this presentation in a while. Now, the first difference to all the other traffic regimes is that when it comes to space traffic, not all space objects have a driver. Actually, only 10% or even less than 10% of the objects we know in space are actually controlled by somebody. So that brings a first difficulty. And the number of objects that we know of today, they consist of roughly 30,000 objects. That's about the size of this remote control, right? These kind of objects and larger, they can be tracked from ground regularly. Doing this means a lot of effort. You need powerful radar systems, optical telescopes to do that, something which is in the hand of air forces today, not so much in the civil sectors. 20,000 objects, 8,500 tons, or when it comes to the geometric cross-section put together by all of these objects, you end up with close to 100,000 square meters. That's several soccer courts that are orbiting Earth. And we see events happening in space that even make the situation more severe. An anti-satellite test, so an intentional destruction of a spacecraft with a lot of fragmentation in 2007, and an unintentional collision equally impacting the environment and increasing the number of objects in space. We also have weather in space, and that is the space weather. And that is, like the weather on Earth, is caused by the sun in interaction with the Earth's geomagnetic field. It can have an influence on ground, rarely, but there can be events that are more significant than what we see on a daily scale. Back 150 years ago, there was the famous Carrington event, so a coronal mass ejection hitting hitting Earth and bending the geomagnetic field so much that aurora and the interaction with the ionosphere went down to mid latitudes, and people in New York could actually read newspaper in the middle of the night. It was so bright. And telegraph lines, which was the highest level of technology development, went completely down. Imagine this to happen with the digitalization that is coming up, autonomous driving and all the vulnerable applications that we are facing. We need to space weather forecast as well, and also for space, because outside of the geomagnetic field, you're even more vulnerable. And you don't have to go back far in history to look for latest major events. They happen, they do not always hit Earth. The latest report here was a coronal mass ejection directed towards Mars, but we are coming from witnessing solar events from the past to nowcasts, and then hopefully also forecasts, so that we can have a few hours of forecast. And that means we need to put up the infrastructure to look at the space weather and try to involve modeling so that we can actually enter into forecast situation. Now, space traffic management might sound for you like a legal regime. We need the regulation. That's certainly one part, but I would like to show here what we as engineers can do to contribute to that topic that will certainly come up. And that has to deal with the situation in space as concerned of man-made objects in conjunction with the space weather, in my view. These are the 6,000 objects above 1 meter size that we believe to have in space today. Going one order of magnitude down, everything above 10 centimeter, we're speaking of around 30,000 objects. Everything in red are spacecraft. In yellow, you have upper stages, and in white, you have fragments, so pieces of upper stages and spacecraft. Above 1 centimeter, we are speaking of close to 1 million, and then above 1 millimeter, we're speaking of 150 million. We can't see them. They are still critical when they hit at orbital velocities. And for the large ones that are tracked, what we are doing already today is collision avoidance. Once you have information on an object, its position, orbit parameters, you can predict their position, you can actually avoid them. Today, that comes with the caveat of a bit of uncertainty around the position, which we call the covariance, indicated by this sphere and ellipsoid. But it's daily practice today in operations to do these kind of avoidance maneuvers. In ESOC, it's every second week. We have to send one of our 20 LEO spacecraft on a collision avoidance maneuver. That case here in particular is a highlight with a collision probability of 1 in 50. And you see already one thing here, we are talking of probabilities. We are not talking of a situation, there will be a collision, yes or no, but we can only present it with a likelihood, and that is because of the uncertainty in the orbit information that we are getting. And the challenge is increasing because we are tracking a bit the kind of chasing objects that are encountering us. It used to be fragments in the past. Painful enough, but the fragment is easy to avoid because the fragment will be passive, its course is relatively predictable, and it's on the active satellite to do the collision avoidance maneuver. Now, we see a situation where more and more spacecraft are encountering other spacecraft. And that means some sort of interaction is required between the operators. And you won't believe how it is working today. It's actually phone and email. And that cannot be sustainable. It's a negotiation. When you know at all the address of the other operator, there's not even a common phone book. All these kind of things are completely missing. And even if that exists, and even if we can work around flight rules by being pragmatic and not wait for a regulator to invent flight rules, I don't think we need that. We still don't want the manual work. So there needs to be an automation of that process as well. And we heard artificial intelligence, and I think these kind of topics would be important and will play a major role in automating it. Our ground systems would have to communicate and solve the problem to us. Like the pilot is, when two planes are approaching each other, it is the TUGraz system on board of the two airplanes negotiating the best way out, and the pilots won't even notice. They just get the direction in the end. And that can be solved by communication between the ground systems as well. Still, you need to know what's going on. There are still the 90% of non-operated objects out there. And that's an effort done today, mainly in the US, and in Europe, we are completely dependent on the data coming from there. In the US, it's even moving further. It's moving from Air Force into more private operators of that information, because when the information is required and when it has a good quality, there will be somebody that pays for it. And that's something we are seeing. And what is the information you would like to have? That's information that is as accurate as possible. The more accurate we are with that information, the less false alerts we will have. To give you an idea, in ESOC, we're receiving hundreds of collision warnings in a day to be filtered, to be selected by the highest probability, and then the ones with the highest probability will be avoided, and most cases it will be a false alert. We just don't know because of the uncertainty of the data. The more accurate we get, the less we will have to maneuver, and there we were looking for technologies to do that. And when we have this technology, in your case, your CCP actually went along these lines in a fantastic way. And laser could be one way to get there. Laser is something that is used today already to track scientific satellites, which have a retroreflector on board, and you can get millimeter ranging. But by the way, I should mention it with Graz in particular. Institut für Weltraumforschung is the leading institute in that field. They managed to get also a photon echo back into a telescope from an object that is non-cooperative, a piece of debris that doesn't have a mirror on board, and do ranging on single photons by using single photon detector. And that has many fantastic effects. You can see from the range residuals, you can get not only the range, but you also get some idea on the extension, on the geometric dimension of the object, and even on the rotation rate, as you see here from this oscillation. And another breakthrough was achieved 2 years ago when these echoes were also received in daylight. So you can expand the hours of tracking. And if you consider that technology a bit further, if there was a bit more light pressure, and we did the calculation already in an extensive study, it's the light pressure that the sun, the natural light pressure of the sun, 1.4 kilowatt per square meter, that's enough. If that could be directed in a laser in a range of 1,000 kilometers, that light pressure is enough to trigger a small delta V just by momentum transfers through the photons. So we are not burning the object, not at all. It's just shining light on the object. Just the light pressure will cause a delta V of a few millimeters per second, just enough to prevent a collision, because many of the collisions will still happen between objects that are not controlled. This could be, this is an activity we are following on in the space safety program as well. This is, for me, the technology we need to manage the space traffic on the short term, but I think we also have a long-term need of space traffic management. And there it looks completely different. Here we have to look at what we leave behind, because everything that is left behind is a burden for the space traffic today, but it's even more of a burden for the space traffic of tomorrow, because it will not stay where it is. It will interact with the rest of the environment, produce more fragments, and make life for future generations even more difficult. We want to do spaceflight with the same risk levels also in future generations. And for that, the mitigation measures have been invented. Franco has been mentioning them, and they are pretty old. They're pretty old. They're around since 20 years, and they're very simple. They're very simple. They say, when you operate a spacecraft in LEO, make sure after end of life it gets deorbited within 25 years. When it re-enters through the atmosphere, make sure you have an acceptable risk on ground. When you operate in GEO, you may reorbit it to a graveyard zone. And for everything else, in all cases, you need to do collision avoidance and passivation, which means venting residual energy. Is this happening? No. You can actually quite nicely see the behavior in space, thanks to space surveillance. You cannot hide in space. It's very transparent what you do. You can see maneuvers happening, and you can see when a maneuver is not happening. For example, the disposal maneuver. And that chart here gives you the statistics on how many of our LEO missions, and I mean the global ones, all across the whole globe, are actually implementing the post-mission disposal from LEO. And that's, you see, it's just half of them doing. And is that because the regulation is not sufficient, perhaps, but I believe, and we know it also from our own operations, it's also because of lack of technology, and I will come back to that. Just to explain what happens on the long run. If we do not do mitigation, the number of objects in space will follow the white curve. If we manage to suppress all breakup events from internal energy, we would cut the trend by half. That's the 100% passivation case. And if you combine that with the success rate of 90% for post-motion disposal, we can stop the growth. We cannot revert it because there's already an amount of objects in space that is active and interacting with each others. And if you want to invert the trend, we would have to add also active removal, which is of course the most complex thing you can think of, going there and take an object that is already out of function. But if we extrapolate the trend of what we are doing now, so a bit of mitigation, we end up with a red curve, and there you see it's close to do nothing. And that will not be a way to go for the future generations. So what can we do? What is our task as engineers? Regulators, through space traffic management regulation, will probably tighten the rules. But when they tighten the rules, we must be able to follow them technically. And that means we need the technology to do passivation also fail-safe. When you lose contact to a spacecraft like Envisat, you will not even have the chance to command it to passivate itself, even if the function was on board. We need that fail-safe options on board. A deorbiting system. A spacecraft that is lost due to a problem in the power bus cannot even be commanded to be deorbited, even if it has the remaining fuel that we need. Why not having independent deorbiting kits or the relevant autonomy on board to communicate with the device on board that can still initiate a disposal maneuver? And then prepare for active removal, have the navigation means on board to understand the attitude of an object, for example, with mirrors, and also rendezvous equipment and a grappling fixture that we can use to actually get these objects if they are finally stranded. And as you probably heard in the space safety program, we would like to make a step and remove a piece of debris from space. It will make space a bit cleaner, but of course that's not the solution, us taking one out of 30,000 objects out. But the object that is selected is the Vespa upper stage, 100 kilogram, rotation symmetric, in a meaningful altitude, 700 kilometers, too high. It should actually never been released there. The startup company, ClearSpace, will go there in 2025, use their robotic device to capture it. It has four robotics arms, as you can see, so it's symmetric, so you don't have reaction torques to deal with, and you will be able to embrace the object before you touch it, so avoiding a bit the complex contact dynamics, and then get that object down. And that, of course, is scalable also for other objects. Now, one removal action will not solve the problem, but we are not here to clean up space in this way, for sure. That will not work. But when we can demonstrate that this technical option is available to regulators, regulators might say, well, when this option is now available and such a mission can be repeated at a very low price, then I can dare to make that a mandatory requirement in the regulation that whenever a space object gets stranded and was not disposed, such a removal service must be used. And the effect that we hope for is that mitigation will be implemented more tightly, because it's still better to prevent than to get things back. But there will be a market for these kind of services, and that's why this is a startup and not the classical space business. They understand that case very clearly. And from there, we must go into, and Franco said it, into an economy on orbit. When you have an active spacecraft that has a need of refueling, repair, then it's even more obvious that there's a customer paying. So active removal combines all the technology steps that we need also to get to in-orbit servicing and in-orbit manufacturing and recycling later on. Still, space flight is changing radically. What we were used to was a launch rate of 100 objects into LEO throughout the history of spaceflight. And what we see now is that spaceflight goes from the hands of the taxpayer more into the hand of commercial, which is good. But it providing broadband communication from space means you need a lot of spacecraft for low latency and for all the bandwidth that is required to be provided. And there we will see a revolution. We will see in the next years more spacecraft to be launched than all humanity has launched in the whole history of spaceflight together. That will come in the next years, and that needs to fit. That needs to fit into space. And there, I think, in the end, we also need creative solutions how we can coordinate. Nobody shall be prevented from going into space. That everybody must be going into space, but we must make sure that everybody has enough room. And there's a similar problem when it comes to organizing frequencies. Everybody understands immediately that is a limited capacity, and everybody voluntarily subjects itself to the process of coordinating the use of frequency. And if you don't fit, you make sure that you're more efficiently using frequency so that you can fit yourself and also others. And in space, you can do the same. It's less obvious. It's less obvious because you have to calculate the environmental footprint or impact emission leaves behind. We are not packing space geometrically, but we need some room to operate, and we need some sort of risk levels that we need to entertain. But that can be calculated and translated. And I'm pretty sure future space traffic management regime will also look at these kind of aspects. That's the final thought I wanted to offer on the topic. Thanks so much for listening.
I'll use this one. We're still learning the new rules. Holger, thank you very much. I think for now we take a 5-minute break for a well-deserved coffee break. Are there any questions on the floor to anybody to Holger? We have
Ms. Eleni Patouni, who is the Project Officer of Emerging GNC Technologies from the European Defence Agency. She's kindly offered to give her an overview of what's happening in EDA, obviously in the space area, so very welcome. And at this point, I'd like to hand over to Eleni, and maybe you can just give us a little bit more of an introduction of yourself, Eleni. Thank you.
Yes, thank you, John. Thank you very much for inviting me and for giving me this opportunity to present the EDA view on space R&D. So as John said, I am working in EDA under the post of Project Officer Emergency and Technology since last year. Before that, I was working in NATO as the Business Development Manager for EU projects. At the moment, I'm also the moderator of the new ad hoc working group Space. This is a new activity that started in EDA this year. I'm coordinating all related R&D work, so I will. This is, let's say, the main scope of my presentation. I will now try to share my slides.
Just to warn you, Eleni, when we trialed this yesterday, we had a 4 to 6 second delay between slides. So we can see your screen now in non-presentation mode. So we don't see presentation mode.
Okay. Now it should be fine.
Yep, now it's good. Perfect. Thank you.
Great. Thank you very much. So this first slide is about the new ad hoc working group Space. We started our operation in January this year, and I would like to give you some background about the reasoning behind it. So in EDA, we recognize that space is a distinct warfighting domain, and there is extremely a lot of work done, like for example, by the European Space Agency and the European Commission in the domain, which is mainly related to pure civilian applications. So we see that as regards the R&D for space defense, this is mainly conducted at the national level, given the efforts of the individual member states, and thus the cooperation is very scarce. So we need that there is, let's say, a need to achieve the goal of European autonomy in this domain. So with this ad hoc working group, our goal is in EDA is to accommodate the coordinating role of R&D for space defense in Europe, and at the same time to provide an interface between the MODs and industry in order to achieve the European autonomy. On top of that, we are planning to grow up the existing activities of the Agency for Space Defense in a distinct ad hoc working group with a final duration of 2 years. So we got an approval from our steering board to run the ad hoc working group until December 22, and then there will be a decision whether this ad hoc working group will remain active as it is, or whether we will evolve in a CAPTEC. Some more details about our activities. Within the ad hoc working group, we also identify the relations with the capability domain. So there is a set of capability needs that are related with our work, like, for example, the space-based information communication services, with all the comprising modules, namely Earth observation, PNT, SSA, and satellite communication. But there are also relations with other capability needs, including, for example, information superiority, air superiority, like, for example, ballistic missile defense and cyber defense in space. As regards the technologies and research domains, we started with a baseline of 4 high-level technological domains for space R&D and a supporting domain that I will explain further on within my presentation. Concerning the related projects and programs, we have one category B, as it is called, project within EDA, the Miracle-2. That is an activity that started within CAPTEC Simulation Space. It is a project of 2.4 million euros, and it will conclude its operation within this year. On top of that, we also have an OB study for Space SRA. This is an internal operational budget study funded by EDA in order to develop the system research agenda for space. The contract was signed with Ernst & Young this March, and there is a total budget of 240K for this contract to run until December next year, and most probably will be extended with additional budget. Here is an overview of the so-called CAPTECs, the capability technology groups and ad hoc working groups in EDA, versus the different technology domains and networks, so that you get an idea of what we are doing and where space is placed within EDA. So we have a set of CAPTECs that are related to information superiority, like, for example, cyber research and technology, a set of CAPTECs related to intervention and protection, like, for example, the ones related to the aerial, ground, and naval domain, and the ones, another category is the innovative research, like, for example, the energy related to one of the materials and structures. So we see that the ad hoc working group spans across both information superiority CAPTECs and intervention and protection, as it includes different aspects. I would like now to give you an update on where we stand at the ad hoc working group. So we did our first meeting in March. We had an impressive participation of 16 member states with designated national contact points, plus EDA, Ernst & Young team, and experts working in the area. What is very important is that as an outcome of this meeting, we took the decision to incorporate industry, universities, SMEs, and other stakeholders within the ad hoc working group. And we had our first workshop with industry that was organized in June 2021. And we also, as part of it, we have EDA now as a stakeholder within the ad hoc working group, and we had the presentation from Florent Mazurelle. In addition, we had the decision to pursue Cat B projects, so we will already start working in projects if possible, and the possibility of funding is a question mark, and it's something under investigation with the member states that are already very active and would like to work on and cooperate with each other within these projects. And finally, we have the decision on the participation of non-governmental and AAA countries. Our next steps is to get the feedback from the member states on their priorities on the different research aspects, to work on the industry and stakeholders portfolio, get feedback on Cat B projects, and extend the list of experts. So this was the outcome of the first meeting. Then we had our second meeting in June, and on top of the already designated member states, 2 additional member states joined us. Our main outcomes were to have a roadmap for the development of our system research agenda for space, to work on technology landscaping activities, and discuss on the category B projects. And finally, we had our first industry workshop of the ad hoc working group space in June. This was actually a whole week, so we had on Monday, 28th of June, the meeting with our governmental experts, and then we had 4 days of industry workshop. We had an impressive participation of more than 120 experts from industry, RTO, SMEs, and universities. And the main focus was to get the feedback from all the participants on the R&D needs. We had a questionnaire and a call for inputs. So the presentations were based on that. So we received more than 56 inputs in our call for inputs, and we also received 45 presentations that were conducted as part of the workshop, including the one of the European Space Agency. I would like now to give you an overview of our technological activities. So how we started within the ad hoc working group. We started by the identification of challenges, namely precise knowledge, access to data, space data exchange, efficiency in data management, decision making in space-based PNT. And based on that, we try to identify what are the related technology needs that we need to consider as part of the ad hoc working group work. So the ones that we are identified correspond to, let's say, to the baseline of challenges that we identified, and include SSA, information acquisition, data interoperability, automated data management, including analytics, decision-making tools, and space-based PNT. As regards based on these technology needs, let's say, the next step was to identify a set of high-level technological domains for a space R&D, focusing, of course, on the defense area. So we identified 4 technology domains, plus a 5th supporting one. This includes the architectural analysis and interoperability, sensors and supporting mechanisms, imaging radar and supporting technologies, space-based PNT, and the 5th supporting technology domain on artificial intelligence, decision-making, information management. In addition, we inherited 2 technology building blocks from CAPTEX simulation space, where there was before some work in the domain, and these include the TBB-8 recognized space picture and TBB-9 defense satellite recognition system. In addition, we are considering, let's say, an extended list of topics that are proposed as an outcome of the OP study with Esther Young, that are proposed by member states, and of course, the ones that we got as an input from our workshop. Here I give you some examples, let's say, of what we are considering within each technology domain. So for technology domain 1, architectural analysis and interoperability, the focus is on the framework architecture and the roadmap for space-based reconnaissance and recognized space picture, but as well as to support the interoperability of the different space surveillance systems. Within this work, we are also considering network and interoperability facilities on the European military level. For example, for processing of data that come from different data sources at the same time, like, for example, not only optical, but also optical to RF. And finally, interfaces and standardization. Next technology domain is the one of sensor supporting mechanisms that includes the development of a novel architecture and sensors for supporting the recognized space picture. Here we are considering the development of new ad hoc sensors that are both spaced and non-space based in order to improve the quality of the data and the coverage. On top of that, it's very important that we are putting a lot of attention in the ground segment, so we are considering the extension of the ground sensors with optical ground-based network, laser tracking, and other related capabilities, as well as the topic of multi-sensors constellations for persistent surveillance. Technology domain 3 is dealing with the development of high-resolution satellite images and hyperspectral imaging satellites and sensors to improve the information from the overhead. Within this domain, we are considering imaging radars, like, for example, spectronics for space sensors, as well as SAR with multi-channel ISAR and insert capability. In addition, we are considering the development of a set of supporting technologies for space-based reconnaissance, like, for example, fuel cells or all the related technologies for satellite-based early warning. Technology domain 4 is the one of space-based PNT. Here we have a lot of synergies with our CAPTEC guidance, navigation, and control, and we are investigating how we can further, let's say, cooperate with them. We have a list of topics that are also part of CAPTEC GNC, like, for example, robust GNSS space receivers and secure GNSS receivers based on the implementation of software-defined radio solutions. In addition, on top of that, we have topics related to R&D for countering interferences, spoofing, cyber threats, as well as the topics of advanced fiber optics and inertial navigation systems. Technology domain 5 includes AI technologies and analytics, like, for example, artificial intelligence at the edge, sensor fusion and visualization in order to support decision-making based on artificial intelligence, as well as synthetic rendering capabilities and visualization, virtual and augmented reality in digital twins. For all these sets of technologies are introduced, since it's very important to have, let's say, to incorporate R&D in order to support the data administration in a timely and efficient manner, enable the recognized space picture, and at the same time optimize the decision making. We are considering a different set of applications that are related to this domain, like, for example, the data fusion for ground-based systems, the SSA data processing, as well as other topics including the detection and identification of space objects with unexpected behavior. Within the working group, we also collected the first set of additional topics from the inputs we received from the member states and from, let's say, my work and the one from Yau-ESA. This includes the data processing, the Sentinel data processing, the R&D to support SATCOM, the concept of micro and nano satellites that is an emerging idea and it's very important for this domain, and others like, for example, quantum technology, the novel concepts for launchers, as well as topics related to propulsion, hypervelocity, and energy. We also inherited, as discussed, two defined technology building blocks, the recognized space picture and defense satellite reconnaissance systems that we plan to reuse. I will now give you like a short overview of what is a TBB so that you get a bit acquainted with this idea. So a TBB in EDA describes the application of a technology, clusters certain R&D developments that are required to support the capability needs, and at the same time the ones that enable functionality that provides a solution to a capability gap. So with the TBB, we are trying to align and define the capability push and the technology push at the same time, specifying a set of functionalities that are required for a specific area. So within our work, we have these TBBs up to now, but the idea is that we elaborate on the technology domain so that we have a set of 12 to 20 TBBs on specific topics. And in order to do that, we received the first input from the member states, and via the workshop, we received the first input from industry, and this will be an ongoing activity. What is the roadmap, let's say, and the plan for the ongoing activities from the ad hoc working group on space? For this year, we worked on the community gathering, on incorporating the first input from the member states and industry, but at the same time, we continued the existing activities, like, for example, the Miracle 2 project, and we worked on elaborating the technological domains. For this year, our main focus is to, let's say, conclude the preparatory steps that are needed in order to set up our distinct ad hoc working group with a final duration of 2 years. For our next year, our ultimate goal is to finalize the space system research agenda and deliver this set of 12 to 20 TBPs. In addition, we will organize a technology foresight workshop on space defense. The exact topic is still to be defined. The workshop will take place on the beginning of next year. And we are also planning on a set of related networking events. The key aspects for our work and our work plan are the delivery of the space SRA and TBPs, incorporating the interest from the member states, the R&D needs that are based on operational challenges, capability needs, and technological gaps, and existing work conducted within CAPTEC simulation space. The pre-final proposed work plan for the ad hoc working group space includes three main activities. So first is the incorporation of industry and key stakeholders. This is ongoing. We already have more than 150 participants within the ad hoc working group from industry, but there are some member states that keep adding participants. The possible preparation of category B projects and the execution of the operational budget study for the space SRA. As regards the meetings, we already had our first and second meeting and workshop as discussed, and we are now planning a meeting with the governmental experts in October and another workshop with industry where we will invite the participants of the ad hoc working group to attend and provide their feedback on the R&D needs and the technological building blocks. As part of the OB study with Esther Young, and this is also part of our work in EDA within the ad hoc working group, we will also work within this and next year on the defense technology landscaping on space R&D, the R&D gap analysis for defense in space, and the development and finalization of the space SRA. So this concludes my presentation. Thanks again very much to John and all the EDA colleagues for inviting me and giving me this slot to present our view on space R&D in defense. If you have any questions, please let me know, and I give the floor back to John.
Well, I'm just taking over for John quickly. Thank you very much, Eleni, for that informative presentation. I now open the floor to any questions. Any questions online, John?
So there's no questions online, but I do have a few questions, Eleni, if that's okay.
Yes.
For me, thank you. So super interesting, a huge amount of work going on in EDA. I'm just wondering, there's so much there and so many acronyms. Is there anything that, from a commercial point of view, that you see coming downstream? Because obviously it's very defense focused, lots of industry in the LISTEX projects. But is there anything, because obviously a lot of the symposium here are working in the commercial domain, is there any messages, any trends that you see that they should be looking out for? Because you guys see a lot more of the threat intelligence than we do. Is there any messages you could give people today? Any takeaways?
Well, as we are now at the point, let's say, of processing the inputs that we got from the workshop from different industrial industrial partners and other stakeholders. So there was a huge participation and a lot of interest from industry on specific topics. So what I can share with you is that there is a lot of interest on the development of imaging and the radar capabilities, on the development of sensors, a big focus on the topic of launchers. We received a lot of inputs from industry in this domain, and also there were a lot of inputs related, for example, to quantum technology, to supporting technologies for SSA. So there are some. I fully agree with you that there is a huge list of topics there. And it's also very important for us to try, let's say, to prioritize them a bit and see what is, let's say, the hot topic for our industrial partners. So we are now at the process of doing that. So once we filter a bit these 45 presentations and 56 written inputs that we got, we will have a, let's say, more clear idea. But my first, let's say, my first feedback is what I shared with you.
Thank you, Eleni. Very interesting. Just one little comment. I think, we've got 3 minutes left for our allocated slot before Florent comes online. I saw SBSRA, so space-based, is that security risk analysis?
No, this is an EDA terminology. It's the System Research Agenda. It's the design of the system for space R&D in defense, and this is part of our work for the ad hoc working group.
Okay, thank you, Eleni. So much appreciation for your time today. Very, very interesting, I think, for many people here, especially some of the guys online I see. So thank you so much.
Okay, thank you very much for doing this.
I'd like to now introduce our next speaker, Florent Mazurelle. I apologize for the mispronounced name. Florent Mazurelle is a Principal Security Strategy Officer for ESA. He has over 2 decades experience in international relations analysis and European policy making, with specific emphasis on European affairs and the defense sector. He has contributed to both the European Space Agency and the European Defence Agency and the European Commission in both as a legal and a professional policy officer. Florent, are you there?
I am here. Thank you for having me. Can you hear me okay?
We're reading you 5 by 5.
Wonderful. Thank you so much for the introduction. Honestly, it sounds like I'm really old now, so thank you so much. I apologize, I'm not wearing a suit and tie because I'm on holiday, and I see that John is sporting a suit and tie. And I just wanted to mention that I'm very happy to see Estec populated again. So I miss being in Estec. It was my last mission before the lockdowns, and I hope to be back very, very soon. John, would you like me to take care of the presentation, or should you?
We've got it showing on the screen, Florent. It's entirely up to you. I don't know if you're remote or you've got a landline there for a decent internet.
I think it's decent, so let me try to share my screen.
Okay, I'll give you screen sharing rights then. Give me 1 second.
Yeah.
Okay, you've got the floor, Florent. You should have a share option in your WebEx now.
Okay.
Yeah. It's coming through. I think we had an 8-second delay yesterday, so don't forget that.
Yeah, we did. So I'll try to be as careful as I can. In any case, I might be running through my slides a little bit fast, but my intention with the slides was also for everybody to have background material once all this is over. So I'll start with the truism, and everybody might fall off their chairs with this slide. But it's something that actually took me a while. I'm not a space engineer. I'm not a scientist. So I'm one of the oddball in that, I guess, and maybe that's why I'm in the policy sector. But basically, it took me a while to understand that space in itself had to provide and contribute to something. And security, the topic of today, is precisely one of those elements and one of those domains where space is absolutely critical. It might not have been so about 15 years ago, but now it is definitely embedded in everything that we do, and especially security. So why? Simply because, and I'm not going to be informing or revealing anything grand to everybody around the table today, because space, you gather information, you gather that information and you treat that information, you transfer that information. And in the end, from a policy point of view, it enables the decision makers, our politicians, our ministers, our heads of states, to make informed decisions about what they need to do. There are plenty of anecdotes going back the last 20, 30 years where you have had a lot more member states and states going towards their own space assets, especially in security and defense, that have made very different choices than in the past. And one of those reasons is simply because they had the independent ability to take those decisions based on independent data. And of course, afterwards, space is necessary more and more for operational implementation of security operations. Now, all this has been recognized at the highest possible level in member states. I'm sure that you follow what's been going on in the UK, France, etc., including in the US, the Space Force, etc. And it's also been recognized at European level, and that's very important to us at the European Space Agency, where we tend to at least have a similar momentum than our friends in the EU. Now, the global strategy in 2016 is still in force. It's basically the policy framework for external relations of the EU. And within that framework, there are calls, of course, for capabilities. And for the very first time, and you're going to say that's extremely late, in 2016, the EU recognized the strict importance of space in all domains, ISR, RPAS, GovSatcom, etc. And that was absolutely key for us. Now, there's an elephant in the room. That elephant, and it's a question that I get very often in many of my talks or discussions, is, yeah, but Europe is NATO. And there's a clear distinction in the EU, legal and political, of course, regarding who does what. So the EU treaties themselves give the responsibility for collective security to NATO. Okay, this at the time was sponsored by the UK. Whether or not the Brexit happened has not changed the treaties. Okay, so collective self-defense is still implemented via NATO. Okay, there is a mutual self-defense clause in the EU treaties, but honestly, there's no framework to actually achieve that clause without NATO. So basically, in a nutshell, and how we go about explaining things is that the EU basically protects Europe, but if you need to defend Europe, that's going to be NATO. So take another example, which is when Russia annexed Crimea. The forces that went to the eastern borders of the EU were NATO forces. They were not EU forces, and that's very important. Now, NATO, as a organization within Europe, is also beefing up its space capabilities. So space capabilities in NATO, and John will know this way better than I do, are national based. However, they're getting organized like member states and everybody else on how to better integrate space in what they do. And now NATO, whether it's NATO, the EU, or ESA, member states are clearly at the heart of what we do in space, and ever more so in security, and that's very important. However, that does not mean that ESA, as an intergovernmental and international organization, is not privy to challenges, stakes, and what's going on in the world. And that's very important to understand. People like me, like John, all these teams, we're basically listening to what's going on and what matters to our member states and therefore to their citizens, how we can provide those instruments and space instruments that matter. So the global challenges right now, they're obvious. Global pandemics, climate change, and that has clear security repercussions, displacements, etc. European challenges, right now, they're more from a policy and regulatory point of view, which I'll cover very quickly later on. Security challenges, again, I think people in this symposium are better learned than I am regarding what's going on in cyber, whether it's SolarWinds, what just happened in Iran, etc. The hack of Microsoft. Cyber, for example, will be one of the upmost key security challenges in front of us. And this is linked, of course, to technology challenges, simply because technology off the shelf is just more readily available, and there are more scales out there to actually use that technology against us if it happens. Now, all this comes at a time in ESA where we have a new Director General, Joseph Aschbacher, who publicized and made public Agenda 2025, and that's basically our policy backbone towards what we're going to do in the next few years. Now, security has a prominent place in that agenda, and very happy about this because it basically it doesn't clarify things, but at least it points the finger to something that was a little bit obvious, another elephant in the room, because security is basically embedded in everything that we do, and because ESA, because of our role in R&D, because we develop systems, because we work hand in hand with member states, industry, and the EU, we are providers of security, whether satellite launchers, the Sentinels, etc. Now, it doesn't mean that we do operations and security operations at large. We don't. There are users for this, and this has always been the role of ESA. It's to be that organization between the user and the governments, and how we provide a tool. Again, my first slide on space being a tool. Now, all this comes into a new political process that our Director General is calling for. And the big thing will be a summit early next year, which we're currently setting up, and there will be a workshop, a conference, hopefully in Ezrin, in person in Ezrin in November, to give some elements to what we could contribute to a space summit early next year. And this space summit's intent is also to contribute to our ministerial council, which will happen later in the year of 2022. Now, ESA security, I mean, very often I'm told, but there's a peaceful purposes clause in the ESA Convention, Article 2. Well, this clause has been interpreted in 2003, so almost 20 years ago, as basically meaning non-aggressive. So in a nutshell, ESA cannot put a weapon in space, okay? Nobody can, actually, but we can do that. However, if our member states ask us for a secured system in quantum, whatever it is, we can, of course, provide this, because it basically means that we're not a civil agency per se. It means that we can do dual use. It's just a question of what our member states require of us. Now, there are plenty of examples where we are contributors to security at large. The Space and Major Disasters Charter, maybe you've heard of this. It basically gathers space agencies and users regarding emergencies. This example, which I hope you can see on your screen, is very well known because it was very much in the news last year. It was the Beirut explosion in the harbor, where we provided images, and it doesn't mean that it's only in Africa or these types of countries. Here, for example, is an imagery over Florida for damage assessments after a hurricane. So, of course, at ESA, we believe that security comes straight from the beginning, which is sustainable development. And we have different partnerships, including with the World Bank, on how to use our space assets and space in general for quality of life, agriculture, climate resilience, etc., etc. And these are things, the SDGs being the Sustainable Development Goals that were endorsed by the UN, and we're trying to contribute to every single one of these. Now, what I'd like to remind everybody in my talks is usually we forget about science and security, but it's actually the first thing I learned when I was a student, a law student. I had a friend who was a bio PhD student, and she told me that her PhD had been financed by the French MOD, and I didn't understand. And then I understood her topic, which was basically currents in the ocean. And she told me, yeah, because the ice caps melting changes the amount of salt, which changes the performance of sonars, and that matters to the MOD. And that's when I realized the first thing that MODs or security forces, Coast Guards, what have you, will be looking for is, are there major changes on the planet? Ice covers, icebergs, currents, winds, etc., etc. And this is absolutely key to maritime security, flight security, whatever type of security. Of course, and this is also something that our DG has recalled time and again. The first thing you look at in an emergency operation is the weather. Everybody tends to forget this, but the first act of security is actually knowing what you need to wear and what type of equipment you need to do. And of course, we work with MedSat on these elements. Now, one of the very big contributors to our security programs is SATCOMs and what we call ARTES. You might have heard of the GovSatcom precursors, SAT AIS, which is maritime security, but also 4S or Quantum, which or EDRS, which we are undertaking right now in coordination, some of it with EDA, but both of them with the EU and with the European Commission. And one of the big pieces, of course, is space situational awareness. I think Holger, our colleague Holger, who might be in the room, I'm not entirely sure, or maybe he's still in ESOC, I think he just delivered a talk about SSA, so I will not be insulting his intelligence by actually adding any elements to this. I'll just make one little point, which is basically we have 3 dimensions to SSA: space weather NEOs and space surveillance and tracking. That last part, SST, is usually considered a little bit more intelligence or defense related by our member states, and it is something that's undertaken nationally, bilaterally, or within the EU in a sort of intergovernmental system. But per se, ESA does not have a very specific mandate on this. Now, what's been happening at ESA is that we're trying to make sense of all this in a rational way for member states to understand and to take policy decisions, but also for the public at large to understand. And Space 19 Plus, our Ministerial Council in 2019, was very important because for the very first time, we were basically trying to put the building blocks where they belonged. Basically, now we have a sort of dichotomy between security in space, space logistics, planetary defense, cybersecurity, etc., which we need to do on a corporate level, and security from space. And these are elements that we're also still working on right now. Rapid response, Earth observation, secure communication, etc. I'm sorry, there's not much I can tell you because this is literally work in progress. So it's difficult for me to give you more details. One of the key priorities we have at ESA, I believe Massimo spoke this morning. He probably spoke about cyber resilience. Cyber now is an everyday fact. It's in the news on a weekly basis. Perhaps you've seen or read the news headlines during the last NATO summit, which was early June. Top of the US agenda was cyber for the NATO summit. Now there's a tendency to go towards attribution, which means that cyber is becoming a specific domain of warfare and state-to-state rivalry. That's very important. Considering ESA, what's important to us is that our satellites create data. They create data, they transfer data, and we have user communities that rely on this data, which means that we need to protect that data, the creation of it, but also its integrity and availability. This is probably something that Massimo has mentioned. Now, there are plenty of examples now in the news of how there's eavesdropping, spoofing, etc. So I won't go into these. But basically, we're trying to have an end-to-end policy and response to cyber. This slide that I've stolen from a commercial partner actually shows all the different ways of some of the different ways where our assets or any assets that our communities rely on, because they could be commercial or they could be national, can be interfered with. And this is something we're taking to account in all our cyber perspectives. Now, maybe you know, but we have a specific center for cyber. It is located in Redu in Belgium, dans les Ardennes, where we have a cyber range, which is below right, cyber range already operating for training and other exercises. Now, this cyber range will be expanded in a way, upgraded into a cyber center of excellence. Now, this is a decision that was taken in the last Ministerial Council, and it is currently being implemented. But basically, we wanted a face of cyber in ESA because everybody's legitimate and everybody's involved in cyber in ESA because cyber is a question of networks. Okay, it's protection of networks, and the space system is a network. It's all it is. So what we're trying to do is to have a 360-degree outlook on cyber and have a place where we can do validation, testing, discussing, but also a sort of cyber diplomacy. And that's where we're hoping it will be. And this will be accompanied by a cyber CSOC, Cyber Operations Center. And this is also in the making. Let me reassure you, every mission in ESA has a SOC, obviously, but we're trying to have a sort of a federated system where there will be all the necessary elements integrated in a single infrastructure for the operations, of course, but a little bit more as well towards its testing, validation, react, etc. Our relationship to the EU is a tripartite relationship, basically between the European Space Agency, ourselves, the EU, and our member states. The member states are basically in both systems. Now, what's been happening is that now we have new regulations. They just came in force. So we have what's called the FFPA, the Financial Framework and Partnership Agreement, which was signed on the 22nd of June. It's a pretty big paper with a lot of annexes, which basically regulates our relationship to the EU and the European Commission. Now, that's very important because we are entrusted with delivering Galileo and Copernicus for the European Commission, and maybe in the future some pieces of GovSatcom and SSA. It basically means that we've just changed the governance of space in Europe, and we will be testing over the next 2, 3, 4, 5 years this new system. Of course, we're undertaking programs that have a security dimension. Galileo, again, everybody around the table has heard about this. There are two elements regarding security, of course. The PRS, which is basically the secured system, the PRS, public regulated service, but also the search and rescue signal. Now, Copernicus, that also you've heard about, is a system based on Sentinels, but it's a system of systems where Sentinels add data for in parts, security services, border surveillance, maritime surveillance, and support to EU External Action Service. And through this, the European Commission caters different agencies, member states, etc., with Copernicus data, which is open data. Now, I'll just give you a quick example. In maritime security, we use Sentinel data in radar imagery, 5-meter resolution, which reflects light extremely well, and that's the picture on the left. And if you want to find, for example, in the target in the MED, you use SAR, and then when you want to hone in and know exactly what's going on, then you can move to optical, which is Sentinel-2, 10-meter resolution, but at least you have some intelligence on what the target and what you're looking for. I won't go much into the cooperation with EDA because Eleni was very kind to join us today, but very quickly, we have now a comprehensive cooperation with EDA, which is probably our biggest security partner in terms of cooperation. It goes from a policy point of view, where we coordinate on a lot of things. There are lots of discussions on cyber happening right now, but we've basically cooperated on CBRN, Earth observation, unmanned systems, etc. I'll just give you a few examples. We used to have an implementing arrangement on GovSatcom, where basically EDA was nourishing our studies and our system studies through their own security communities. And now we've just moved to the next level, which is a memorandum of intent of the next generation of secure satellite communications, which doesn't replace the implementing arrangement, but basically takes it to the next step, namely in light of our 4S program evolutions. Now, of course, RPAS was one of our initial cooperation using satellites for beyond line of sight communications and guidance and control. And this is also something that we use in unmanned maritime systems, where we have a demo ongoing on how to integrate different types of systems, PNT, data relay, Earth observation, SATCOMs, etc., in those systems. More recently, we just signed 2 new agreements on CBRN and artificial intelligence. I'm sorry I don't have much results for you now, because although they were signed in late 2019, the lockdown slowed down the ITT process, the demonstration processes. Now another, and the last one I'll be discussing is cyber defense. Very big on the EU agenda, very big on our agenda. This is now a fairly old cooperation. John is personally involved in this. And again, I want to thank his commitment and knowledge and helping us out. It has 2 phases, and right now we're in the midst of the second phase, which is focusing on CTI, cyber threat intelligence, and we're hoping to have a demonstration after the summer. Finally, still in cyber, we are part of the Cyber Ranges Federation, through which we are associated with some of the EDA member states on how to use our cyber ranges in a coordinated fashion and integrated fashion for training, but also exercises. Now, very quickly, I wanted to mention this because it's a lesser known fact. We have a cooperation agreement with the SATCEN, the Satellite Center, which is located in Torrejón in Spain. We don't necessarily deliver products like this one that you're seeing right now, which was a damage assessment over Raqqa in Syria, or this one, which was for one of the CSDP missions over the Med. However, what I wanted to mention is that the SATCEN relies basically on all the sensors they can find. The Sentinels, the Copernicus, to which we are contributing, but also the governmental ones, on which we are not contributing, very, very vastly on the commercial ones, which is basically an illustration of where maybe us in the public sector, we're hoping to do a little bit more to fill some gaps and to make sure that security authorities, including in our member states and within the EU institutions, have the data they need when they need it. Thank you very much. I hope I wasn't too long. Whether now for questions or later through emails, I'll be very happy to take your questions. John, back to you. Thank you.
Thank you very much, Florent, for that interesting presentation. I'm looking around for any questions, but I think your presentation was very comprehensive, and they all have your email address if they need to contact you. Okay, I would like now to present the next speaker, Jussi Luntama, who works as the head of the Space Weather Office of the Space Safety Program for ESA. Jussi has a long career starting at University of Helsinki of Technology in 1991 and has continued working for EUMETSAT and various meteorological institutions across Europe. He joined ESA in 2009, where he was selected as manager of the space weather segment in the ESA Space Situational Awareness Program at the time. Jussi, are you there?
Yes, I'm here. Thank you very much. Can you hear me?
I'm reading you very well.
Okay,
so
excellent.
The floor is yours.
Thank you. Let me just make a precaution. I'll stop my video for a moment because I have slight limitations in the bandwidth that I have available here. So I apologize if you I'm joining the meeting from the framework of another meeting that is taking place, which is also a very interesting topic related to the space weather and the project which is developing new space weather capability for Europe. So in my talk, I will give an overview of the space weather activities that ESA is carrying out and raise some points related to the general theme of this meeting and the workshop. So first of all, the framework. I know that Holger Grag gave a talk earlier today, and unfortunately I was not able to follow that talk, but I'll just mention very briefly that after the Space Situational Awareness Program that ESA started in 2009 and then continued for 10 years until 2019, we have moved to a new program which is called Space Safety. This program, just like the Space Situational Awareness Program, addresses three potential threats to the Earth coming from the space environment. Space weather is one of them. Another one is the asteroids that might be on a collision course with the Earth, and the third one is the objects that we have made ourselves, the man-made objects and the space debris that is in space. In the SSA program, we were focusing very much on monitoring the space environment and understanding, having the awareness of what's going on in space. In Space Safety program, we are also targeting more active measures to mitigate these threats. So, for example, we are also looking at technologies to deflect asteroids from a collision course and also removing space debris actively. For space weather, and we don't have to active measures, so we're best and only defense at the moment is actually to monitor, understand, and forecast what is happening in space weather and provide the information to the end users so that they can take the correct mitigation action against the potential impact. This is a slide that is giving a bit of a background why we are doing this. So space weather and the solar activity can potentially impact a lot of our infrastructure, not just the elements in space, but also some of the infrastructure on the Earth, particularly our power grids. So basically solar activity and eruptions from the sun can directly cause an impact that would actually physically destroy some of the big transformers that we have, power grids, causing blackouts and actually substantial financial damage, which actually could also last quite a time because these transformers are very expensive and also slow to replace. One aspect of space weather is that also it changes the characteristics of the upper layers of our atmosphere. which impacts the radio signal propagation. So even in a situation where we would not have any damage in the infrastructure, all the satellites that we have in space would be working fine. The Galileo system was mentioned and must have been mentioned in many speaks in this meeting today. The Galileo system, the satellites are robust. They are very robust against the environment where they're flying, but the atmosphere can actually disturb the signal so that the ground-based applications or airborne applications of satellite navigation do not have a signal, or their navigation solution can be severely wrong. And one of the aspects which is maybe less obvious, but which is very important, is that the satellite navigation signals are also used as a time reference by many ground-based systems. And the atmospheric disturbances, again, can disturb this time reference, which would cause problems which we don't probably even all know. So the information about what's happening in space, in the sun, and the space weather is very important for many applications. I have a couple of kind of money slides here. In 2016, we carried out a study which we called cost-benefit analysis. We had an independent external team assessing what kind of socioeconomic costs space weather is causing because of continuous, small, moderate, or big disturbances in various activities, and these are the numbers that they came up with. So basically, in the analysis, they concluded that the space weather impact over a 15-year time period could be estimated as about 13 billion euros. And we cannot prevent everything, but if we have space weather services for Europe, so this is what this DO-ESA scenario in the slide from the final presentation study means, we can substantially reduce the impacts. And the benefit to cost ratio that was estimated in study is over 6. So basically it means that for every euro that we are using to build the space weather capability in Europe, we actually save 6 euros in the costs, which is actually a very good ratio for any space activity. This is another estimate from the same study. Here was estimated what could be the socioeconomic cost from one major space weather event. So one event that would cause a substantial disturbance in our activities, potentially causing long-term damage in power grids, disabling and permanently damaging some satellites in the orbit, and actually, as you can see from these numbers, causing, for example, a long disturbance in the aviation activity. It's not that long, actually. We're talking about a few hours here, but the air traffic in Europe would be completely disturbed for a duration of a few hours. The costs accumulate very quickly. And again, if we have the space weather capability that we are targeting, we can reduce the times that this disturbance will last. So we can still not completely prevent the impact, but we can recover much faster, and that way the economic costs will be substantially small. So how do we do this? This is ESA's space weather systems today. So based on the work that was carried out during the Space Situational Awareness Program, we have built a European space weather system. So ESA does not do space weather services. Our expert groups in Europe, in all the countries that are participating in ESA activities, they have the skills, the people, and the means to provide space weather services. What ESA is doing is facilitating this networking of European capabilities and coordinating the developments and utilization of these capabilities and the existing space weather assets so that we can already demonstrate and show and validate the services to the end users. And ESA's role is to develop the system, carry out the testing, verification, and validation of the services, and then when we're ready, this capability can be transitioned into a fully operational system providing 24/7 services to the end users. I will not go through all the details. I really would like to recommend you to look at the website where you can see the overall service system, everything that we are offering there. And you'll find a lot of information and many groups in Europe who are providing and contributing towards the system. In order to assess the data and all the services to all the details, we are asking you to register as a user. This is simply because by registration, we can serve the users better. We know who we are working with. We can provide you a better information. We can help you with your problems and questions. So that's why the registration is recommended, and also some services are behind the registration. But at the same time, you can always go, like the about 2 million people who access our webpage monthly. You can go and just look at what the latest situation in space weather is. And we do a lot of development and implementation of things. And then when we talk about security and safety in Europe, one of the important things that we have also established during the last 10 years is what we call a coordinated communication. I don't know if you noticed, but just about 2 weeks ago, in some newspapers around the world, there was a story that there is a huge solar event on its way to the Earth, and it will disable our satellite systems. I still don't know exactly what created this news, but as I think all of you who are using satellite systems today, you know that it did not happen. So there was actually no event that would have even threatened our satellite systems seriously at that point. The purpose of our coordinated communication protocol is that when a space weather event is imminent or detected that we have an onset of an event in the sun, we can, within a few hours, call in a meeting by all the relevant key space weather experts in Europe. We can create a communication which is objective, to the point, and with the right scientific and technical information, and we can release this information to the users so that they know objectively what is happening, what is our best prediction of what will be happening over the coming hours and days, so that they have a trusted, reliable source of information about what's happening in space weather. So then going into the service provision, this is an example. So if you are operating a satellite, this is a snapshot of the current services and what kind of information you can find from our system. Basically, satellite operators are typically concerned about the environment, especially the radiation environment in space. So we provide information about solar particle events, so the energetic particles coming from the sun that can impact the satellite electronics, causing either transient or permanent damage. But we also provide information about, for example, the solar wind, which can cause charging of the surface of the satellite, causing discharges that can, again, it used to be actually a big problem for geostationary satellites. Now the satellites are designed to be more robust against that. But again, it's information that people want to know in order to be able to operate their satellites efficiently, and also to avoid carrying out, for example, critical operations in the satellite operations at the times when the risk caused by space weather would be higher. This is a picture of the future. So this is our target, what we want to achieve within the next 10 years. So we have a system, but we want to make this system better, and we want to especially target the user needs. So in order to have a better space weather protection for Europe, the elements of this, as we see it, are, first of all, we need tailored space weather services. So the users need to have actionable information so that they can make decisions based on this information, but they also need to have this information tailored to their needs. So for example, a very simple example is that most users want to have traffic lights. Very simple and quick to understand information, whether the situation is dangerous, whether it's moderate or there is no danger whatsoever. So very simple three-step system. But at the same time, most users want these levels and the thresholds between the steps to be tailored to their needs. A simple example, people operating a satellite might want to know very quickly if there is something happening that might impact their planned operations over the coming days. At the same time, people who are protecting the civilians, those are civil protection authorities in Europe, they do not need information about moderate events which will have no impact on ground-based assets, for example, but they want to know when a major space weather event is detected or forecasted. So we need to tailor the information to the right level so that the people know that when some information is coming their way, it's serious. We need a better space weather monitoring system. At the moment, we are relying very much on science missions that have been developed over the years and decades in the past. But these missions are not designed to support operational space weather services. Operational means in this case that the data is needed immediately. Tomorrow's weather forecast the day after tomorrow, it would be too late. But the science missions typically, they download the data with time because the science can take the time to analyze the data properly and correctly. In space weather, operational space weather applications, we need the data quickly. And then we need a resilient society. When extreme space weather events happen, when we have an onset of a huge eruption in the sun, it can, in the worst case, reach the Earth within 15 hours. So there is no time to start to make plans then. The plans have to exist in advance. And then when the event happens, you take the plans and start implementing them. And then, of course, we need to develop new capabilities, new models, satellite-based systems, etc. So I will go a bit more into what we are doing in space in ESA. So to monitor space and space weather, we have split this space segment into two parts. One part on the right, this is the environment in the vicinity of the Earth. Because this is where we see the space weather impacts. We see the impacts of what's happening in the sun, and we can provide information about the space environment. We can help the satellite operators to operate their satellites more safely. We can provide information about what's happening in the ionosphere, whether your radio signals or satellite navigation signals are disturbed, or if there are conditions where a power grid might be impacted. But in order to make forecasts about what is going to happen over the coming hours and days, we need information about the sun and the space between the Earth and the sun. And in order to do that, we have to go further away from the Earth. And one point which is important is the first Lagrange point, which is a gravitationally stable point between the sun and the Earth. There we can observe the sun, we can remote sense the sun's surface, but very importantly, we can also in situ measure the solar plasma which is coming towards the Earth, or these coronal mass ejections like in this artist view here, and we can give information about what is going to happen in the very near future, so we can make a nowcast. The new element that we are adding is an L5 mission, so that's a new perspective of monitoring the solar activity and giving us an asset to do better space weather service. So I'll come back to that in a moment. So I'll go through quickly a little bit of the space segment development. So we are implementing what we call a distributed space weather monitoring system for monitoring the environment around the Earth. We carry out different types of measurements because there are different elements in this environment which is impacted by space weather. The implementation of the system has started. It's in progress. We are demonstrating actually new ways of doing this, which has not been done anywhere else in the world yet. So, for example, we are using hosted payloads, which means that we are flying individual instruments as part of other missions like the Korean meteorological satellite mission, which is carrying a magnetometer from us, the magnetometer called SOSMAC. So we're demonstrating that this is a new way to sustain, in an efficient and sustainable way, build operational space weather monitoring capability. We have radiation monitors. One is already flying on board the European data relay satellite C, and it's working perfectly. We are procuring 2 additional radiation monitors, which will fly, one of them in a commercial telecommunications satellite called Hotbird F1. Another one we are flying with the Lunar Gateway to an orbit around the moon. And this is preparation for the future human and robotic activities on the moon, because the radiation environment there is much harder than on the Earth. The moon is not protected by a magnetic field like the Earth, so the astronauts and also the robots are subject to a potential radiation hazard there, and we need to actually to make a good forecast and nowcast of space weather in order to protect our activities there. And we have a lot of further development in order to make this system more complete, in order to be able to give more precise and more timely information about the space weather events that are either in progress or foreseen to happen in the near future. We are also looking at the use of small satellites to look at aspects of space weather which are not possible, which are not necessarily possible with bigger satellites, but also which cannot be done with a very small spacecraft. One of the elements is actually the continuous visibility of the auroral oval at both hemispheres of the Earth. This is not related to the beauty of the aurora, although these satellites and the information provided by them could be used also to tell people when it's a good time to go out and admire the aurora. But the aurora oval is actually telling a lot about what's happening in the upper atmosphere, and especially the aurora oval tells us when the upper atmosphere is disturbed, so that our navigation signal and satellite communication signals may be disturbed and they will not pass through the atmosphere as expected. And this becomes increasingly important when our activities in the Arctic region are increasing. So, for example, for navigation, when the shipping is starting to use the Arctic routes transport, we can provide better information about when the conditions are potentially hazardous, and you have to be careful with your satellite navigation when we have this continuous monitoring capability in place. It's not trivial to do this because we need multiple satellites to provide continuous imaging of the auroral region. So we are looking at the ways to implement this. And there are potential mission concepts, and we're also looking at the potential international collaboration to implement a mission like this. We're also breaking new area in space weather, in operational space weather monitoring by looking at very small to cubes. This is again something that has not been done operationally before, but CubeSats have mostly been used for technology demonstration. But we are going to demonstrate that actually this kind of an approach is feasible, and it's also sustainable, and it's a way to address certain observation needs that provide this approach provides more flexible and cost-effective way of carrying out space weather monitoring. And this is, of course, this is also a potential opportunity for new space and space business. So either implementing missions that provide data for space weather applications for the ESA space weather system, for example, or European space weather system. But then there are already examples of companies who are building nanosatellite constellations to provide a space weather service directly to the end users. And this is a very interesting possibility that hopefully will emerge over the coming years even more. I promised to talk a bit more about the Lagrange mission to L5. This is another artist's view of what the mission will see. It's not in scale. Earth and the Sun hopefully will never be as close to each other as they are on this picture. But the idea and the basic reason why we want to implement this mission is that if any of you play soccer and you have been a goalkeeper, when somebody kicks the ball very fast towards you, it's difficult to estimate the speed of the ball and exactly where it's going because it's coming so fast. But if you can see the ball from the side, it's much easier to make this same estimate in the direction of the ball. And the same applies to these solar events, the plasma blasts, which we call coronal mass ejections from the sun towards the Earth. So we need to look at them from the Earth perspective, but if we add another perspective on the side, we get a stereoscopic view, which gives us a better handle of how fast these things are. The speed of these plasma clouds is extremely important because that determines the impact that they will have on our infrastructure. Also, the direction is important because sometimes they go a bit over the Earth, sometimes a bit below the Earth. So we need to know which direction they are going so that we can provide the press information. And also from the L5 point, which is at 60 degrees away from the Sun-Earth line, we can see the solar disk before it's visible to the Earth. And that means that we can actually see the sort of emerging space weather. We can see active regions in the sun that will cause flaring for days, and we give advance warnings to the people that bad space weather is on its way. Or the contrary, we can also tell that now the space weather is quiet, there is nothing happening, the sun is completely smooth and clean, which would be a good time to, for example, to fly to the moon. Because you need a few days of quiet solar weather, space weather, in order to be protected against potential radiation hazards during the trip. Flying a satellite to L5 is challenging, and this mission is going to be the very first deep space operational space mission that mankind has ever done. And it creates a lot of challenges for the mission operations. The flight to the L5, it actually takes quite some time. It takes us 4 to 6 months to reach L5 after the launch. And also, even the signal from L5 coming from 150 kilometers away, it takes 8 minutes for the signal to arrive to the Earth. And we have to take this into account both in our space weather services, because there is going to be an additional delay simply because of the speed of light limitation, and also in the satellite operations. So it takes time before a command that is sent from the ground can be executed by the spacecraft. But ESA has a lot of experience of the deep space operations in ESOC, so we're confident that we will be able to handle it, and we will be able to demonstrate the benefits of this mission for the space weather service and the mankind. So then going to my final slide about the challenges of space weather capabilities. The first point is end user needs. The end users, in order to be able to utilize space weather information efficiently, they need early warning, but they are also looking for event-based alarms. So they need information on time so that they can act when something is happening, when we can see something happening in the sun. And this capability we already actually have very well. We have to maintain it, and that also means that we have to maintain our space-based monitoring systems. What we are missing at the moment is the capability to forecast. Because for example, a typical example is the power grids. If there is a potentially dangerous extreme space weather event detected, it's already too late to apply very efficient mitigation methods. You cannot turn off the power. That would be a disaster for the whole community. But you could take measures to protect the power grid, make it less sensitive to space weather impact. But it takes time. So you would need more than 2 days to do that. This is what the power grid operators have told us. At the moment, we cannot give them a 2-day forecast. And for example, the Lagrange mission is a way that we plan to improve our capabilities so that we can give better, more accurate, timely forecasts for longer time periods, but we're not there yet. So we need to improve our capability. And this is what we are targeting. So everything we do is driven by the user needs. The user needs are evolving. One area which is very rapidly emerging is, for example, autonomous transport, probably starting with shipping. And again, when we have autonomous transport, the navigation of the vehicles will be very much based on satellite navigation signals, which can be disturbed by space weather. To be able to provide forecasting of the conditions that might impact the navigation in order to avoid hazards and reduce the risks. We need to do end-to-end modeling, which basically means that we can forecast when we see an event or we predict an event in the sun, we have to be able to forecast what the impact on the Earth and in our infrastructure would be. And in the future, actually, we also consider that we will need to be able to do this for also not just the Earth, but also other places in our solar system where we have human activity. We need, as I already mentioned, we need to do custom tailored services to the end users. There is no one-size-fits-all space weather service. This is also a business opportunity. So there is an opportunity to develop business to address the specific needs of certain end user groups. Aviation is actually, there is already progress towards that, but I think there are many other areas where this opportunity is emerging. And then we have to build and maintain a space weather monitoring system in an efficient and sustainable way. And this is another business opportunity for the future, because when we need these services, when there are commercial users for these services, then also there is a need for a monitoring system for the data that enables these services. And then the final challenge, I would say, for Europe is a provision of operational 24/7 services. At the moment, as said, ESA has the mandate to develop the system, test, verify, and validate the capability, the services, the models, and the end user products. But to turn this into a fully operational system that addresses the user needs. This is something that we are working on. We are working together with the European Commission on this, but we're not quite there yet. So this is the challenge for the coming years in the space safety program. And then finally, new service concepts. When we talk about business opportunities, the evolving user needs. We don't know yet everything. We don't know all the sensitive areas of our infrastructure where space weather could have either a direct impact, but even more likely indirect impact. So when part of the infrastructure is disturbed by space weather, what are the dependencies that would be created by this disturbance? What other parts of the services or could be disturbed because of this? Our infrastructure today is so complex that it's very difficult to do this. We try to do it. We will launch another cost-benefit analysis, hopefully early next year, to cover the evolution of the infrastructure since 2016, and also some areas that we were not able to address in 2016. But again, the results of that cost-benefit analysis are likely to show new opportunities for business in space weather. That completes my presentation. Thank you very much.
So thank you, Jussi. Amazing slides.
Can't hear, John, you have to switch the mic on. Maybe.
It's automatic, isn't it? Yes, fantastic slides, Jussi. I'm just looking around the floor here if there's any questions from the floor. No? No questions from the floor? Okay, that's great. So I've got to say, it's really impressive now that we're collaborating across Europe and with the US, I think, for these complementary systems to handle the projects with the space weather. They're all part of the critical national infrastructure now, and I think it's really important that that's managed by everybody. So yeah, I mean, the slides are very beautiful as well, Jussi, I must just say. They're amazing slides. So I think we thank you very much for that.
Thank you.
So while, so at that point, I'm going to hand over to Petra, and she's going to give you a brief talk. Okay? That's like in Julien.
Thank you, John. So we'll try to give you a very short 15-minute presentation about our SpaceTech 2020 Central Case project. My name is Julien Serie. I come from the aeronautic industry. I'm an airline pilot in Hong Kong for Cathay Pacific Airways. And I started getting interested in space a couple of years ago, and the opportunity to apply to SpaceTech came up. And I got to say, it's been an amazing experience and a great journey. And if you're thinking of applying at ESA or elsewhere, I highly recommend you do it because it's a lot of work, but it's really fun as well. So let me now introduce you to Petra. Petra has been our business owner, and she comes from the Royal Dutch Air Force, and she's been an amazing team leader, and she's really touched us with her energy, her leadership, and a great sense of humor as well. So you can give her a big round of applause.
Thank you so much, Julien, for that introduction. Whoa. Yes, thank you very much for being here. I'm interested in the CCP project. We haven't done it by ourselves, just the two of us. There were 12 people working on this for thousands of hours to make sure that we have a project that's really thought through and analyzed. So we got 15 minutes to present that, which is quite the challenge. And so I'll immediately go with the next slide, which is how we started this. So we were challenged to pick a project in space domain awareness. And we saw that the number of objects in space are just increasing almost daily. We've seen that in the presentation of Holger as well. It's getting worse. And we wanted to focus on one region to make this better. So we started out with the geo region, geostationary. And what we found there were three big problems that were going on. The first one was the problem of size. The really dangerous objects that can really damage a satellite are 10 centimeters and above. And what we see right now with commercial assets, ground stations, is 40 centimeters and above. So we've seen this picture before, the geo region with the red objects and the yellow and white objects just crossing by. Satellite operators can anticipate on these. They see them. But there are a lot of objects they don't see at all, while they are still a danger to their spacecraft. That's problem one. What we also saw was that while some objects are known, we know where they are, that's a little bit too optimistic because there's a huge uncertainty factor, the covariance. We've also seen this cigar before, so you can imagine that if you have to analyze if a spacecraft is really going to collide with an object, you have to take into account these uncertainties, which means a lot of analysis power. But also, you find out that a lot of these alerts are false alerts. So you're spending a lot of time, a lot of effort, and a lot of cost on stuff that's not really a danger in the end. We wanted to improve that too. And then to the last point, it's really difficult to zoom in onto a satellite as soon as you figure out that there's something wrong. The only thing you can do right now is analyze the data that comes in and then see if you can figure it out, yes or no. If you can't, you lose your spacecraft. So it's not a small problem. If you look at the value of only the assets, so just the hardware in the geo region, we get to about 78 billion in 2030. That's the expectation. That's just in geo, just the spacecraft that are out there. We're not talking about revenue. nothing else. Now, going into the risk factor, the cost associated with such a risk for collision is about 230 million of combined risk in 2030. That's not change. That's a lot of money. And like I said, we're not even talking about revenue yet. The stuff you can lose if you need to maneuver your spacecraft and you cannot use it, so you cannot provide service to the customers. So we've been looking into how we can solve this, and we came up with 3 services that we want to provide. It's detect and track, so we can actually see all the objects that are dangerous, and we can have really accurate conjunction messages that don't give you too many false alerts. Then we go into the characterize, so we know what the objects are, what size they are, how they maneuver, any change detections that might occur. And we want to give spacecraft operators the opportunity to inspect their spacecraft as soon as there's an anomaly. To do that, we had to set up a certain amount of requirements, like how often do we want to revisit one of these objects? So the maneuverable spacecraft, we want to observe them a little bit more, like every 24 hours at least. The passive objects are a bit more predictable. We can see them every 48 hours. That's good enough. For the characterize, we had to ascertain which kind of characteristics we wanted to measure and to see to get to the root of the behavior of objects. And then the last one, the inspect. How fast do you want to get there? What do the satellite operators need? And that all we wanted to do with a mission lifetime of 10 years and a budget of preferably less than 500 million euros. So one step further, we're going to the physical architecture. After a lot of analysis, a lot of trade-off, we came to a payload with an aperture of 15 centimeter. And to keep the design really simple, we wanted to have one spacecraft that could do all of these services and not have like different designs, because it would make it more complex and would also drive up the cost. So for the people here, you see the mock-up over there that Julien showed. For the people online, we'll show it after the presentation, so you have a bit of an idea what we're talking about. That's a 2-in-1 model, so it will be about twice as big, and we'll have a little bit of an idea later on if we put the camera on it. Now, we just don't put a telescope into space. It doesn't work like that. We need a lot of subsystems that work together to make sure that this telescope actually does what it's supposed to do. So that optical sensor that we put into space needs to be able to generate electricity. It needs to be able to communicate with the ground, etc., etc. It all needs to work together. Now, we'll get a bit more into the technical part of this, and we'll also give you a little bit more information about how this translates to the financial case, the business case. And that's something that Julien will take over. So up to you.
Yeah.
And thank you very much.
Thank you, Petra. So just to give you a quick overview of the mission, we'll show you the concept of operation. So it's all going to start with a launch segment, launching our constellation into space. We will have 12 detect and track GEOScan in a detect and track orbit. That orbit is 1,200 kilometers below GEO, sub-GEO, and we'll have 5 characterized GEOScan in the characterized orbit at 140 kilometers sub-GEO. The number of spacecraft is dictated by the revisit requirement that we want, so 48 hours for the small objects, the small RSOs, and for characterization, the 30 days revisit requirement. The revisit requirement is actually a little bit better with our choice of spacecraft, and we got a 42 hours revisit requirement for small RSOs. The way the operation is going to work is it's going to be tailored around a suite of complex scanning pattern that will be scanning vertical section of the GeoRing for small objects, and also laterally for active spacecraft around the GeoRing. In the meantime, our characterized GeoScan, will be conducting active spacecraft characterization, and then once again here we exceed the requirement of 30 days and we get to about 26-day revisit. Once data is acquired, it will be linked to our ground statement via our ground station provider, and then onward onto the NAVIR Mission Control Center, which will be based here in the Netherlands. There, the data will be processed and analyzed, and we will dispatch products and services to our customers around the globe. The Mission Control Center will be able to obviously send routing command to our spacecraft, and then when one of our customers requires a close range inspection, we will task via our ground segment one of our detect and track spacecraft to maneuver and position itself around 14 kilometers from the customer spacecraft to take high resolution imagery, and then we'll forward the product to our customers. So we'll have a mission control center with a team of about 40 people in 4 shifts. And it's all going to be centered around a suite of software tailored for our mission and our operation, developed in-house. So that's the mission overview. We talked about the orbit and constellation. The space segment is about a 230 kilogram spacecraft. We need to carry fuel for the Delta V in order to be able to carry those close range inspection. And the power level are kind of standard for that size of spacecraft. The launch strategy, we are looking at launching directly into our final orbit, either via dedicated launch into GEO or a GTO launch with a kick stage motor for circularization. Ground station, we will be renting time on a commercial ground station provider like Amazon Web Services or KSAT. And our mission control center we talked about, and obviously the user segment once again will be an in-house software suite that will be accessible by our customer. This is a development implementation plan. So we are planning to start with a Pathfinder launching in 2024 to validate all the software architecture and the operation, make sure everything runs smoothly before launching our constellation into 2 batches. First batch of 8 satellites in 2026, and then the second batch towards the end of 2026. We plan to be fully commissioned and operational in 2027, and operational for at least 10 years, maybe a little bit more if we have extra propellant left on our spacecraft. And by 2040, we want to have our next generation of GEOScan spacecraft operational as well to provide continuity of services to our customer. The split down of the life cycle cost, we're looking at a total life cycle cost of 466 million, so we are below our 500 million target requirement, and you've got a split down of how the costs are spread around the mission. Just a quick word on finance and revenues. We are looking by the year 2035 at 280 million euros revenue, which makes the business highly profitable from that point onward. And the funding strategy, we'll be looking initially at funding from public and partnership and places like ESA to get our initial funding, develop that suite of software, which is going to be the bulk of the development. We know how to do an optical sensor spacecraft. It's been done before. Developing a software tailored around space-based space situation awareness in GEO is quite challenging and will take, obviously, some initial funding. So to summarize, we want to improve the safety, reduce the operator costs by avoiding unnecessary maneuvers, and also obviously ensure space sustainability via a commercially viable business. Thank you very much. Is there any question? Well, I guess it's time for lunch then. No. Oh, sorry. Sorry. Thank you.
The only thing I'd like to add to that, it was of course a very short presentation. If any of you here or online are interested in our executive summary, please drop a message to either Jose or John, and we're happy to provide it. And I'd like to ask the cameraman for the online audience to put the camera on our mock-up, because we like to show it off.
Yeah, it's good.
So our next presenter, we're very fortunate to have her with us, is a tenured professor at the Faculty of Aerospace Engineering at Delft University of Technology. And just to give you a little bit of background while Jose is transferring the slides across, you have to manually unmute her as well, Jose, in the attendees list, okay? She graduated in 2000 with a laureate degree in experimental particle physics. In 2004, she received a PhD in physics from the University of Rome for Vergate, working on data acquisition system for the spaceborne experiment Pamela. Dedicated to the detection of antimatter in cosmic rays, and in 2005 she was granted a Marie Curie postdoctorate fellow at Agfa Geverat, I hope I presented that correctly, and no, I didn't pronounce that correctly, where she developed a simulation for X-ray health diagnostic systems. In 2006, she joined the European Space Agency in Estec in the Space Environment and Effects section, where she was leading several radiation monitor developments. And again, as I mentioned earlier, since 2015, she's a tenured assistant professor at Delft. So I believe you're going to get a really nice technical overview of space radiation. And that's over to you.
Alessandra should be online. Can you check?
Yes.
Alessandra?
Yes.
Yeah, we can hear you. We can hear you now.
Nice. So, welcome everyone to this presentation. Today I'm going to talk about fault-tolerant open source onboard computer for space application. Next slide, please. Yeah, first of all, I would like to stress the fact that embedded systems were born dependable, because embedded systems were invented for these space missions, Viking and Voyager. So all the building blocks of the modern avionics systems were invented at that time. EEPROMs, microcontrollers, ADC, DSC, software were all invented for these missions. And it's quite amazing because Voyager 2 is still working fine with a bit of aging, but still going very well. And it will be 44 years old in August, so very soon. Next slide, please. Yeah, with this slide, I'm showing the fact that the technology progresses. In the terrestrial application, we can see in this plot the different figure of merits, different performances of a microprocessor over almost 50 years. And we can see that some of them, for example, the number of transistors in a computer keeps increasing very steeply. Other performances, like, for example, the frequency and the power consumption are flattening since about 15 years. But in general, there is a very clear progress across the years. And this is happening in space application too, but hard processors are typically lagging more than a decade behind the terrestrial application. So just to give you an example, the PowerPC 750 evolved from the 90s to 2005 of a factor 2,400 in the commercial version, while the space version improved only of a factor 300. But still, there is a continuous improvement. Next slide, please. In order to design a processor, the first thing to do is to start from a ESA, instruction set architecture. This is the most abstract model you can have of a computer. It defines the basic operations that a computer should support, such as the type of instruction, the maximum length of an instruction, and what is the instruction format. An ESA can be seen as the interface between software and hardware, and there are two big categories, the complex instruction set, which is CISC, and the reduced instruction set called RISC. Next slide, please. In this slide, you can see an overview of CPU ISAs in Europe and US. You can see that there are different categories of ISAs. And in Europe, recently, well, since actually the 90s, we are using Spark as the core component of onboard computers. In US, PowerPC is much more popular, but recently, as you can see, the blue zone, which is the Spark, is also extending in the American market thanks to Coban-Geisler that is becoming more and more established also in the American market. And there is this yellow zone, which is RISC-V. This is what I'm going to discuss in detail in the next slides. But the message is that it is important to start from existing ISA because it is very difficult to design a processor from scratch. Next one, please. And the challenges of the space market with respect to the commercial one are many. There are many challenges related to mainly the fact that the market is tiny. So the most successful processor ever, the ESA's ERC32, sold only 60,000 pieces, which is nothing compared to the consumer electronic market. And this tiny market makes things much more difficult. First of all, the access to IPs and foundries is limited. The non-recurrent engineering cost is huge, especially when you go to the most advanced technologies like below the 28 nanometers. And also, another interesting fact is that there are no GPUs available for space application. This is just because the lifetime on the market is too short to allow the proper space qualification that is needed for a space onboard computer. And then we have limitations due to the physics, which cannot be changed. The radiation environment, as we have seen in the presentation from Jussi, is very challenging and provides a very harsh environment and induced soft errors make the performances of onboard computers much worse than terrestrial application. And then, of course, memory, size, speed are limited. The thermal issues in space are also a challenge. The packaging limitation, power supply stability, these all make the design of space onboard computer much difficult. Next slide, please. And why do we need an open source ISA? I think that it's quite obvious what are the advantages, but the most important one is the fact that we can reuse an established software ecosystem, which is composed by compilers, debuggers, development environment. The advantage of having a large community using that ISA is huge because, the bug funding is much more efficient, of course, when the user community is broad. And this was exactly the reason why in the 90s ESA chose Spark as their basic ISA for their computers. But recently Spark has lost momentum in terrestrial applications, mainly because of the predominance of the proprietary x86 ISA. And then on top of that, there are new markets with different requirements. For example, the mobile devices market is requiring for power efficiency, and this has led to the success of ARM proprietary ISAs. Next slide, please. But recently, we are seeing the RISC-V is becoming more and more popular. RISC-V was originally developed by a university, UC Berkeley, in 2010. And yeah, the idea was have an ISA that was open and free to be used for computer architecture research and education. So it was purely research and education oriented goal. But then the advantages of having an open and free ISA became very interesting for many different players. And the RISC-V Foundation is growing very fast. There are also big players like Google, Qualcomm, IBM, NVIDIA, Samsung, Western Digital, just to mention some of them, are supporting RISC-V Foundation. Next slide, please. As I said, the community is growing very, very quickly. In a market analysis performed by Semico, they forecasted such a strong growth for RISC-V that in 2025, about 62.4 billion RISC-V CPU cores will be needed by the market. And you can see in this graph also the different applications, consumer, communication, transportation, industrial, and under RISC-V. Next one, please. And recently, European Space Agencies, in collaboration with the COBA, GASLR, and also TU Delft, because we are hosting a PhD project in collaboration with these two partners in the NPI program. We are investigating how to apply RISC-V in space. And of course, the key feature is the fault tolerance, because in space, processors should be fault tolerant. In this table, you can see the different configurations that are available from GASLR COBA. In the implementation Noel 5. That's the name of the implementation of COBA and GASLR. Next one, please. So the typical satellite data system architecture is something that looks like this. You have an OBC and the different subsystems, so the power subsystem, thermal control, AOCS, payload unit, and the communication subsystem. So the OBC is the core of the avionics system of a satellite, in any satellite, small or big. The onboard computer is in charge of controlling critical subsystems like the communication subsystem. Next one, please. And in this slide, I would like to give you an idea about the evolution of onboard computers, because as I said in the beginning of this presentation, the technology is advancing also in space. So for example, from the Gucci onboard computer in 2009 to the Gaia onboard computer in 2013 to Oscar, which is an Airbus processor developed in 2014, we can see the improvements not only in terms of frequency, for example, so we go from 24 megahertz to 80 megahertz from Gucci to Gaia. The computational speed in MIPS is from 17 to 65 and 68, but also in terms of power consumption, so we go from about 90 average watts of power consumption to 40 to even 15 for the Oscar CPU, and of course also mass. Mass is decreasing in the context of the miniaturization of space systems. Next slide, please. The typical requirements for space-grade processors are centered around the concept of dependability. Dependability is a concept which brings together reliability, availability, and maintainability of a certain system. Just to give some numbers, a space-grade onboard computer can be required to have less than one reboot in 15 years due to all possible fault sources. So not only induced soft errors from the radiation environment, but also power faults, software errors. And you can imagine this is really a harsh requirement to be met by space-graded computers. For example, memories, commercial memories of 28 nanometers shows in orbit single event upset rate, so bit flips in the order of 10 to the 9th upset per bit per day in a solar minimum in GEO, but this rate can increase of a factor of 3, 4, but even higher in case of solar events, as we have seen again in the presentation from Jussi. Just to give a reference, a processor in terrestrial environment will experience upset rates at sea level of 2 to the 10 to the minus 11. So that's much lower. And in order to meet these very strict requirements, we cannot rely only on a process hardness solely. Fault tolerance is a complex subject. Next slide, please. So fault tolerance is best addressed in a multi-layer design. This is just an overview of a possible fault tolerance approach for space-graded processors. Starting from the lowest level, so on the left-hand side, the intrinsic masking of faults, and then we move to a higher layer, which is the error detection, to the error handling. So not only recognizing there is an error, but compensate the error in, for example, by giving a reset, by correcting or taking action if this is not needed. And with this slide, the message is that fault tolerance should really be addressed at all levels if you want to meet very strict requirements. Next slide, please. And each component has a different impact. This is an evaluation that we have done in a published paper. You will find at the end of the presentation a list of references that I used for preparing this talk. This is an estimation about how much they weight in the overall vulnerability. In this case, it's vulnerability of the system. And you can see that, for example, technology will have a big impact with a factor of 10,000, and environment, so the radiation environment is also having a big impact. Next slide, please. Another very critical component in space processors are cache memories. This we have seen with in detailed analysis that they are the biggest contributors to failure rate. So they have to be addressed with a dedicated radiation hardening approach in order to achieve the overall fault tolerance. Next slide, please. Now, I would like also to touch very briefly on the subject of artificial intelligence and machine learning in space, because this is a very hot topic. And of course, the processors of tomorrow, the new generation of processors, should be enabling this amazing revolution that is happening in terrestrial applications. So why not also space? And in space, there are many areas where artificial intelligence can be really helpful, can really enable new mission objectives. So, for example, the first one that can come to our minds is debris removal. dogging and in orbit servicing. This is really a very hot topic at the moment. At Delft, we have several projects going on in applying artificial intelligence for example, grasping non-cooperative objects and identifying the best possible approach for in-orbit servicing. And then another area where it's pretty clear why artificial intelligence is helpful is landing and robotic in general. So, for example, identification of craters. This is an area where I'm sure we will see a lot of improvements from machine learning application. And another very obvious one is payload processing. This has been already done. I'm going to tell you about it. For example, in cloud identification, identification of features in the images from cameras. This is a very hot as well. And then another very interesting area, in my opinion, is the reconfigurable platform. So the autonomy that satellites can have in the future by using artificial intelligence and, for example, forecasting failures, detecting failures, all of this can be really powered by artificial intelligence and machine learning. Next slide, please. In terms of hardware for artificial intelligence space, we have already some available building blocks, which is great, of course. In this slide, I give some examples, and you can see from the left-hand side, these are the more agile, flexible, and easy to work with. And on the right-hand side, we have the more powerful ones, but also more difficult to use. So we have a Leon RISC-V on the left-hand side, produced by Probam. In the next picture is a NVIDIA Jet Force, which is unfortunately not available for space. So in bold, you will see the ones that have been designed for space. So the bold ones are the space ones. And then, indeed, the Xilinx FPGA ultra scales are also very well suited for this kind of applications, and maybe in future the under development Brave FPGA from ESA will be also used for this. But at the moment, we have already demonstrated that the Myriad-2 Movidius chip, the DPU produced by Movidius, can be used for artificial intelligence in space. Next slide, please. Yeah, this is just an example for how to use AI for payload data processing. The typical application is something that, for example, if done with a traditional approach, will take a long time, or maybe it's not even feasible at all. So this is just a very generic example. It's not a specific case, but you have, for example, the improvement from small areas that are elaborated by a geologist, for example, to a much larger analysis of the data, which can be performed by machine learning. But still, the small area annotated by geologists can be used as the training data set. And so the two approaches will be combined for achieving even more innovative concepts. Next slide, please. Yeah, so I already mentioned that AI was already demonstrated thanks to the Myriad-2 chip, and this was done with an ESA-sponsored satellite VSAT-1, which was launched in September 2020 with a Vega launcher, and it's a 6U CubeSat developed by University in Spain, and together with Cosine, a company close by Estec. And the idea of the AI experiment was to use to detect clouds in the images taken by the camera on board, and the cloud coverage is deteriorating the resolution of the images, and these images are rejected. So they are not transmitted to ground because of the low quality of the data. And this is, of course, of great interest for the future because we know how expensive it is, the use of ground stations. So achieving, filtering already on board is something that is very interesting for future applications. Next slide, please. And of course, there will be many more challenges ahead of us in the future. This is just an inspiring slide, I would say, where we can see at once all the different destinations that the future space missions will have, and all of them will have different challenges, and space processors are the brains of this mission, so we have to take good care of them and make them as powerful as possible and fault tolerant as possible. So next slide, please. Yeah, so this is concluding my presentation. I have shown you today that the spinning of open source ESA has been very successful in the past, and it will continue to be so in the future. And thanks to RISC-V, we believe that we have all the characteristics needed to become a new standard for space processors, replacing the highly successful Spark. And this is due to its openness, its modularity, and thanks to the large growing community base, which is supported also by big players. And on top of that, also the possibility of vector extension could enable onboard artificial intelligence, but fault tolerance remains critical and must be addressed on multiple layers of the design. So with this, I conclude my presentation. I will be happy to take any question if you have any, but you can also contact me by email later on. Thanks a lot for your attention.
Thank you so much, Alessandra. So I don't know if there's any questions from the floor. No, I think everybody is overwhelmed. Very, very interesting, very expensive. I was very impressed. So again, thank you, Alessandra, for that presentation. Thank you to be seated, and we can recommence with the presentations of the day. So I've got the great pleasure to introduce Mr. Denis Bousquet from AXAXL. So we've been very fortunate this year to have Denis and his colleague Dominique Rohrer helping us in a part of our interview process to do the market research. Fantastic support they've provided to us and given us lots of good feedback and input. Just to give you a little bit of a bio for Dominique, he spent several years in the space industry, manufacturing satellites. He's been in charge of telecommunications payload, and he launched the space insurance at AXAXL 14 years ago. AXAXL is the entity of the AXA Group in charge of corporate clients. Denis is a senior space underwriter and global chief technical officer in the space team in AXAXL, in charge of risk analysis, insurance contract negotiation, portfolio management, and support to claim handling. He's a member of the Space Working Group within the French Federation of Insurers and in close contact with various space industry stakeholders. So, over to you, Denis. Merci. So yeah, Denis, I think you need to unmute your microphone. Now you're coming through, Denis.
It's okay?
It's good, and we can see your Space Insurer, current view, and SSA first slide.
Okay, thanks. So, good afternoon, everybody. I will give you an overview of our view of as a space insurer on space situational awareness. Will be a slightly different presentation than what we have seen this morning, which was very, very interesting from a technical and overview point of view. So for you to understand the impact of space insurance with SSA, I will start with a brief overview of space insurance, then some statistics, insurer love statistics, and then the two topics, space weather and collision risk, with the view of today and the view of tomorrow. And then to conclude, the link between SSA and space insurance. So let's start with space insurance overview. The need for insurance in space. We need, and you need insurance in space because there is a high concentration of value and risk. Typical figure of value of a satellite in GEO is between 150 and $500 million, and between 5 and 150 million in a low Earth orbit. And the probability of failure, including the launch phase and the full life cycle of operation, is between 10 and 25% in GEO, up to 15 years, and between 5 and 50% in LEO, including satellites with a life of 1 up to 10 years. So you see, when you combine the value and the probability of failure, there is a big amount of risk. In addition, because it's not sufficient, we have recurring innovation. In space, we have always prototypes, new design, new missions, and always technological innovation. And because of this high value, there is a financing need that's mandatory for investment. In case you want to have a big space project, you need investors. And investors can take the risk of the business plan, but do not want to take the risk, the technical risk of failure. They want this risk to be transferred to space insurer. We protect the profitability of operator, of course, because in case of failure of one satellite, this could have a dramatic impact on their profitability. And as well for institutional project, because we are here at the ESA, space insurance is more and more used by institutions to allow a quick restart of big projects. For instance, if you have a big project and a failure, in order to avoid the time spent to ask for a vote of many peoples and maybe many countries that could last during 1, 2, or 3 years before taking a decision, if you are insured, you can have directly, in a couple of weeks, the amount, the cash from insurance. Insurance is essential for private investment, and we try to be an incentive for systems quality and robustness. So there are two types of insurance. Asset cover, so that we are covering all damage to satellite, including internal and external events. And we are doing this with two types of contracts. The first for launch, so launch vehicle flights, only the launch phase, so that we can extend up to 1 year. So we start at intentional ignition or liftoff, and we can terminate the contract at separation or few days, or typically 12 months after. And then we have in-orbit cover to cover the commercial operation on a 12-month basis that we renew annually. In the contract, we have a sum insured, which is pre-agreed by contract. So that corresponds to the cost to rebuild, relaunch, and reinsure the satellite, or the loss of revenue, or the accounting value. That's very key, because we are basing the premium on this figure, and in case of total loss, we are not discussing the amount of claim. We are just paying what has been indicated in the contract, which is this sum insured. As satellites can have many missions, many designs, we are customizing the contract, and especially what we call the definition of partial loss and total loss to meet the business criteria of the insurer. And what is specific to space, there is a waiver of recovery against the manufacturer and launch service provider as waived by satellite owner. So maybe if you are not familiar with insurance, in case of a claim in a standard line of insurance, we are checking who is liable for the claim, the first one, and who is the origin responsible of the first responsible of the claim. So we can go over the supply chain. In space, No, the operator is paying the premium and taking the full risk. And in case of rocket failure or manufacturer satellite failure, we pay the operator, and we are not asking the insurer of the launcher and of the satellite manufacturer to reimburse us. That's the first insurance cover, asset cover. And then we have liability cover. The requirement depends on each state, requirement in terms of amount of insurance to be bought. It can be $50, $100 million, and the duration, only launch phase, maybe launch phase plus few days or few months, or the full lifetime of the satellite. But even if it's not required, it is useful for operators, because in case of collision, we have seen this morning that more and more collisions are expected between satellites and not between one satellite and one debris. So in case of collision between two active satellites, the operator may have a liability to a third party. So space insurance is available for all types of missions, orbits, and clients. And for you to understand the mechanism of the insurance market, that's my last slide about space insurance. So we are basing our premium based on technical merits, design and heritage, and supply and demand. We are a market. So that means the sum insured versus the available market capacity. So one side, we are a proactive market, asking for technical visibility, redundancy, margins, and we are a reactive market. If we pay big claims, we can ask increase of premium and even contract exclusion. 2 years ago, we had a big claims on the market, much more than the premium, and we ask the premium to double. So you see very few markets where the price can double in a couple of weeks. And due to competition and volatility, we are today more reactive than proactive. And about SSA, in case of an insured collision or serial impact due to space weather, this will or could have an immediate and dramatic impact on the space industry due to increase of premium from the insurer. So let's move to a few statistics. So here, the number of satellites launched by orbit and size over the last years. So we see in blue the GEO, relatively flat, and then in the kind of orange, the low Earth orbit, with in green the Starlink that we can put aside because it's very specific. And so we see, as we all know, the number of small satellites launched in low Earth orbit is increasing dramatically. And we have seen the increase in CubeSat, and now we see more the CubeSat being stabilized, and we see more increase in the what we call small LEO satellite between 10 and 150 kilograms. In terms of reliability, I try to compare two extreme cases. So you have here the reliability of a satellite as a function of its satellite life in months. So from separation up to its life in orbit. And then the reliability that can be understood as the probability of success. So at the time of separation, you have a probability of success of 100%, and then it decreases over time. For GEO telecom, which are big satellites, very expensive, a lot of testing, a lot of redundancy, a lot of investment in the design, you have a pretty good reliability with, after few months, after even 5 years, in the range of between 5 and 10% probability of failure. And extremely, when we take into account the historical data of LEO CubeSat, then you see that the reliability is totally different. And of course, in between, we have a lot of cases, depending on the mission, the design, the testing, the reliability can be between these two curves. The first subsystem contributing to failure is in GEO high power unit. We have a lot of power, more and more power these days, and in LEO, low power electronics. Of course, deployment mechanisms are a concern during the first day of operation, during the deployment of solar arrays and our antennas. So reliability is very dependent on design, heritage, redundancy, and on-ground testing. So now moving to the two external events that a satellite can suffer: space weather and collision risk. So today, for space weather, we are experiencing several in-orbit failures due to space weather. Loss of solar array power, failure of electronic components, such as payload amplifier or processor, that are resulting mainly from electrostatic discharge or single event effect. And in some identified cases, there is a clear correlation of a space weather event and an in-orbit anomaly or failure. Here, you have an attempt to find some correlation. So in blue, you have, for given subsystems, the number of failure. So not only anomalies, that's actually failure of components, not failure of satellite, but failure of component. And in gray, you have a space weather index. And in some cases where the space weather index is moving a lot, we can suspect a correlation between the space weather effect and the subsystem A failure unit. But we need to improve the monitoring of space weather and better understand the phenomena to prevent in-orbit failure associated to space weather. Tomorrow, new designs are more susceptible to space weather. We see onboard processor and active antenna for flexible satellite. Today, GEO telecom satellites cannot guarantee a business plan on a given region for 15 years. So we see more and more flexible telecommunication payload embarking more and more electronics. And these electronics are more susceptible to space weather. The usage of commercial off-the-shelf components, especially to new space, where the space qualification might be slightly different, and we can expect if the radiation tests on ground are not representative enough, we can expect more losses on COTS. On constellation, the impact will be in case of serial losses. When you launch one satellite, if you have a design weakness, you lose one satellite. If you are launching at the same time 20 satellites with exactly the same design and the same process, you may lose 20 satellites due to one single space weather event. And of course, because redundancy and shielding are much more limited. In addition to new design, new missions are coming. Human spaceflight, of course, where space safety is a key parameter, and life extension. When you extend the life of a GEO telecommunication satellite beyond its design lifetime of 15 years, you cope with attitude control system and propulsion, which is used thanks to a space tug, but all the other electronic components that has been qualified for 15 years has to operate maybe 5 years more. So there is an uncertainty around that as well. So new design might be more susceptible to space weather. New mission must properly integrate space weather in the design. And as science is progressing, space weather, I think, will be more and more used. Now moving to collision risk. So today, the density of debris has increased. For sure, the probability of collision has increased. But the probability of intrinsic failure, so that means the failure of an internal component not due to collision risk, is still higher than the probability of collision, even low. This will not be the case in 10 years, but as of today, that's the case. And the conjunction probabilities are not accurate enough. I'm sure you have all in mind the Iridium Cosmos collision 12 years ago, where the very interesting graph from the Aerospace Corporation shows that the probability of this collision was not the highest of the day or even the highest of the week. So we need to clearly improve the accuracy of this data, and we need to demonstrate the reliability of the data such that the satellite operator will use them. So tomorrow, the population of space subjects will dramatically increase. And so we need reliability of data. When we discuss with satellite operators, some of them are telling us, I don't know, I'm not using the conjunction probability because I don't know if I'm doing a maneuver, and maybe I'm going to be closer to the debris than before. So we need to ensure the maneuver is needed and going in the right direction. And so, again, we need to demonstrate the accuracy of data. In addition, in case of collision with two insured satellites or with one high-value satellite, there will be a big awareness of the space community, and especially on the insurance side. And insurance premium will increase. As you have understood, we are a reactive market. In such a case, some orbits might be more difficult to operate and even to insure. We may exclude to insure satellite in such orbit. So we should all make sure to protect space now. So how come we make the link between SSA and space insurance? First, the risk management. Risk management shall be integrated since the start of the project and shall include all phases of the project, including end-of-life disposal. The system design depends on the mission and business plan, of course, but the sensitivity of design versus the space environment shall be studied. For example, the density of the object in the desired orbit at the time of deployment, the conjunction alert accuracy and timeliness, the ability to perform avoidance maneuver and end-of-life disposal, the shielding against radiation, especially for CubeSat and new space satellites, and the redundancy. There is a trade-off between redundancy at satellite level and at system level. For example, having a bigger satellite with internal redundancy rather than having more satellites with in-orbit or on-ground redundancy. And so all these space environments, including for the risk of collision and the space weather, shall be considered at the time of deployment of the system, of the constellation. Once the technical risk management has been conducted, then there is still a bit of risk that can be transferred to insurance. And the insurance cover shall be function as a price. For example, when you have a constellation of 1,000 satellites, the question to have what is the probability to have at least one satellite failure makes no sense. It's nearly 100%. The question is more, what is the probability to have more than 10, 50, 100 satellites? And can I sustain my business plan with 10, 50, 100 satellite failure? And in parallel, the insurance can give a price for what we call excess scheme in excess of 10 failure, 50 failure, and 100, like a franchise in other insurance contracts. So as for any company, risk management is key for long-term business. And SSA and space insurance maybe can partner. So SSA can be a tool for insurance. Collision risk is there, but as of today, lower than probability of intrinsic failure. Space weather is damaging component, but correlation and prediction are not ready yet. And only one insured event will be sufficient to change the insurance market. So tomorrow, SSR might be mandatory to insure low Earth orbit. And insurance may need better data and new services to do their jobs. SSR can be a partner with insurance because, especially for liability, the impact of failure can be well in excess of the value of the project. And our job is simply to spread the risk of failure among the various operations. Insurance may help the market to better use SSA services. We can be an incentive. We can push for some services that we feel are useful for the safety and the space sustainability. And we have some data, type of failure in orbit experience return, that could be useful for SSA as well. So we want to push for more responsible behavior. So SSA will be part of the future of space insurance, and space insurance will be part of the future of SSA. And to conclude, we want to ensure space business on the long term. And we have identified few areas which are not new for you, but we continue as a space insurer to push for them. Identification. We see more and more launches with a lot of satellites on board. The number of launches with more than 10 satellites was 20 last year, and is already 23 this year by end of July. And there is an issue of identification. It takes time to identify which satellite is at which location when you have plenty of satellites separated from a launcher. And there is more risk of failure because the autonomy of a satellite is not infinite. Then ability to move. Having even a small propulsion system for collision avoidance, of course with a passivation, is key. Then cleaning after use. I think the regulation must and will come on this subject. We cannot continue to use space as we do. So we should be ready to do it now. And so we need to be ready to be serviced. And we see here and there various initiatives, very good ones. For example, to have standardized mechanical interface for grasping. So we need to decide and make the design now, to launch the satellite now, to be serviced in 10 or 15 years. To have markers with well-known relative position to help the navigation in case of need of close proximity and rendezvous. And documentation, including external interface control drawing, to be stored and easily available after end of life for active debris removal, even if the company is not active anymore. And at the end, the space sustainability rating is coming. That's an initiative and a decision from the World Economic Forum, and AXAXL is part of this initiative. And trying to have a rating today based on debris mitigation, based on data sharing and identification will be very good, a very key step to encourage responsible behavior. So on ground, the AXA group is putting a lot of effort to be very much green. For example, the AXA has decided to stop insuring and even investing in the coal industry. At AXAXL level, we are insuring corporate clients, and we want to encourage responsible behavior, including in space using SSA. Thanks for listening. I think there are some questions.
Thank you, Denis. I'm going to check Denis in the room. At the moment, it looks like there's no questions. No. John has quite a few questions in the chat, so he's going to handle them from now.
Yes, thank you. Thank you, Denis. Very interesting as always. So yeah, they're in the chat rather than the Q&A, so you'll have to bear with me. Sorry, my mouse is not working. So the first one I have here, I think, do you cover maiden flights in GEO as well?
We may cover maiden flights. That's a question of price. In fact, a lot of risk, nearly all risks are insurable. As long as we have sufficient data to perform our risk analysis, and you are able to pay the correct price. A maiden flight today for one new rocket has a probability of failure between 30 and 40%. So the price could be as high as this. But we can take into account the heritage and the process of the launch agency. That will not be different if the launch service provider has already a strong heritage based on other rockets than on a brand new rocket.
Thank you. Second question here is there an insurance for military assets? Is it different from civilian assets? Can you answer that question? Feel free to avoid it if necessary.
I can answer. So a military asset can be insured. We can define what I said, partial loss and total loss definition. So of course we can insure them. So some of them are buying insurance, some of them are not, and the reason is because they do not want to have people aware they have an issue on a military satellite. So they prefer not to have an insurance payout rather than telling people that you have an issue on a military satellite. But for example, on the launch phase, in case of launch failure, that will be public information. So a lot of military satellites can be insured easily during the launch phase.
Thank you. Next one I've got here. How are we doing for time? Yeah, we've got a few minutes. Do you cover issues preventing business such as RF interference, shadowing, proximity operations?
In proximity operation, because as a standard, we are covering only in case of damage to the satellite, so in case of failure of an internet component. Then, in case of proximity operation, we can cover this on a case-by-case basis, and we need to really understand the process of a proximity operation.
Interference, is that something that you've looked at? RF interference? We understand there's quite a lot of accidental interference at the moment. Sorry. The RF interference, we understand there's quite a lot of accidental interference between different providers sometimes, especially in the telecoms area. Is that something you're aware of, that maybe you cover?
If such interference does not generate a failure of one component, this is not covered. If the interference due to overdrive is generating a failure of one low-noise amplifier or receiver, then it will be covered. Is it clear enough?
Sorry, I'm playing with my microphone here. Yes, I think so. I've got another one here from Darlene Freeman. How does the insurance industry view the reusable launch vehicles and potential impact on commercial GEO launch rates?
We are following the development of large launch vehicles for sure. The impact will be the accumulation during the launch, because if you put more satellites on a given launch, then you have, remember my first slide, a big accumulation, a big concentration of risk with very high value. And such a thing is not is manageable if the sum insurance is not too high, but if you are in excess of 800 million or $1 billion value on a given rocket, that could be much more difficult to insure. But we have to find a solution. As in space insurance market, we have to find a solution for that. So we will.
Okay, I think one very last question, because we're just about out of time. You've got a few more questions here, Denis, but I'll just pick one. How are refueling activities insured? If they're insured.
We could, and we can insure the refueling activity. So far, my first feeling is that there is a bit of risk to try to open a valve that has been in orbit during, let's say, 15 years, and which has not been designed to be reopened. So I will be much more comfortable to insure refueling activities if the design of satellite that is refueled has been done for this purpose. So if you design a satellite for this, then the risk is much lower. Insuring something pretty new, it's just a question of price, but the price will be much higher if the valve hasn't been designed for that.
Okay, I think Eddie is just about ready for us. One last question then from Mr. Krag. Could you consider to use the sustainability rating also as a factor for the calculation of the insurance fee? I think that's linked to your last slide there.
Yes. So we plan to push for responsible behavior, and using this rating will help us to push for responsible behavior. So as long as the people, this rating will apply to a lot of people, we will use them to maybe favor, could be with the price, could be with the cover, could be with some services. So we plan to use this rating to give more favor to the one we will have a good rate.
Thank you, Denis. I'm just having a quick check because there's a little bit of a technical problem with Eddie here. No, that's it. Okay, I think that's it, Denis. So thank you for answering all these questions. Very, very, very interesting. Obviously, lots of people interested in your talk today. Thank you so much.
Thanks.
Okay, while Eddie's just trying to log in here, I'll just introduce you to, I've known Eddie for many years actually, from back in the days on Galileo. He was one of the senior systems guys within the engineering team on Galileo. He's now moved into the human robotics area, He's currently working on the Earth Return Orbiter. So just to give you a little bit of a background, yeah, that's the one, Eddie. Just to give you a bit of a background on Eddie. He's currently working HRE on the Earth Return Orbiter, so you're going to have a really fun presentation today. I've had a sneak preview, and it's really nice. He's worked in the space industry for over 27 years in the area of telecommunications payloads, navigation systems, and deep space missions. Over the years, he has worked for Airbus and Kinetic, previously in the UK for the Defence Research Agency, before finally joining the European Space Agency in 2005. Over the period in ESA, he has spent a significant portion of the time following Galileo, the European GNSS, and the rollout of the system from the initial in-orbit validation to the full orbit constellation deployment, including the ground control segment. Currently, he works in the Directorate of Human Robotics Exploration within the Mars Sample Return Campaign, and he's supporting the areas of communication and security system engineering. And within our office, we're working quite closely with Eddie. And he's been actually one of the key people, and he's still struggling for the technical side.
Make sure this right one's swapped over.
Okay, and then you just need to share your screen, Eddie. You need to share him. Okay, we're just about there, I think. Okay, so yeah, within the ESA Security Office, we're mainly in charge of certification and accreditation. So Eddie has actually been one of our key pilots, our key pivots within the HRE ERO mission, the Earth Return Orbiter mission, liaising with industry, talking about security risk analysis, because Eddie, in his Galileo years, you know, we've managed to work with him very closely. There's a bit of a panic down here. Oh, there we go. Very closely. So fortunately, Eddie has a lot of experience. He's helping a lot with the awareness and security within the agency, within industry, and he's going to give you a little bit of a taster for that now, and it's going to be a very interesting presentation for you all. Eddie, over to you. I'll come off this side because you're taking my...
Yeah. Thanks very much, John. Thanks for the introduction. So yeah, I'd like to talk to you about the Mars Sample Return Mission and the Earth Return Orbiter, and why that's linked with security within this particular context for yourselves within the SpaceTech Symposium. So let me see if this remote works and goes through. Okay, so a little bit of background and what is the subject and where does it come from. So obviously this is really a Mars mission and it's a Mars campaign. But of course, you know, Mars is another planet within our solar system. It's smaller than Earth. It's further away from the sun than Earth is. It has a very different temperature environment. The environment is very different overall between Mars and Earth. There isn't a magnetic field around Mars to protect it from the harmful radiation and from the environment that it's within. Also, because of the different dynamics between Mars and Earth, you know, the time taken for signals to go between Mars and Earth is varying. You know, at the closest time, it's quite short. It can be something like 8 minutes. But when Mars and Earth are at opposite sides with respect to the Sun, you're having sometimes up to a 20-minute difference. And if there's this conjunction, you can't see Mars at all because the Sun's in the way. So these are these things that make life complicated between Mars and between Earth. And just for us to operate together and have communications, you need to have certain capabilities. With that in mind, why is security even relevant? Why do we care about security for doing activities around Mars? You know, is there really an issue? But okay, before we go into that, let's have a little bit of an understanding of the background here. Back in the 60s, we were already sending spacecraft to Mars to investigate Mars and see what's going on there. What you see there is a Mariner image, which I hope is coming up on the screen, from Mariner 4 back in the 60s. At that time then, they were looking at Mars and it was just covered in craters. Then the scientists then were saying, okay, there's not much there. It's not really that interesting. Why do we really want to look at Mars? But they persevered. They continued to try and find out more about it. And with other missions, including here pictures from the Hubble, they started to see, yes, maybe Mars is more interesting than what we first thought. There is what looks like to be an atmosphere there. They could see cloud cover, which said, maybe there is something else there about Mars. You could see that there was potential ice caps on the polars. So they continue to investigate and find out more details. Here you see dynamic changes on the surface of Mars. You can see there that the winds have actually created ripples in the landscape from the dust and from the dunes. And interestingly, they were able to find out that from the color of Mars, why was it red? Well, this is actually from iron oxide on Mars. And also they were seeing there was black sand there, which is actually from a volcanic, potential volcanic or balsat activity there. So over time, we found more and more interesting things around Mars, which are making us investigate more and more. Now today, we have other spacecraft there, which are orbiting Mars, for example, Mars Express. And we have a number of images that we've also taken, and also you have an MRO from NASA and other missions as well. But in this case here, you see a few images from Mars Express, where they've specifically been looking at the large crevasses within Mars, such as the Valerius Marineris. And on the northern part of that, just close to the Lunaire Planeum, you actually have the Ecos Chasm, which is over 100 kilometers long and 10 kilometers deep. 10 kilometers wide, beg your pardon. And from the investigations there is a belief that that used to have water in those areas as well. So there's an understanding of the history of Mars that we're developing over time from our scientific activities. And this also is bringing more and more interest as we go on to where we are today. So this takes me really to the Mars sample and return activities, which are ongoing as we speak. This is a trilogy mission that actually started from myself back in 2020, but for many of my other colleagues, it started much, much earlier than that, when the work on Perseverance and Ingenuity just started then. So those two, Perseverance and Ingenuity, were launched back in July in 2020, and that arrived at Mars 6 months later, so around about January this year. And that's actually landed in an area called the Jezero crater. That crater is also very, very specific because we're very interested to look for certain samples in that particular area. Again, the belief is that there was water once within that area of that crater. And that's also very important because with the fact that there was been water there, which is also suspected to be contributing to life, but water's helping to create certain types of soil buildup. So what you'll have then is residual layers of soil growing on top of each other over multiple periods of time. And then that will create sedimentary rock. So if we can collect some of that information and that data, we can analyze it, and you can look over time and the detail of Mars itself. And that can, you can discover a lot of things over the history about what has happened to the ecology of Mars and how it is today. Back then, not back then, but then if we move forward to what is going on and what we're developing for the Mars sample and return. So first, M2020 will drive around Mars, around the crater, and it will collect samples, and it will actually create a repository of those samples in a specific area as a depot. Then in 2026, we're going to launch also towards Mars another rover called the Sample Fetch rover, which will be developed here by ESA in collaboration with our colleagues in NASA. That particular rover then will arrive in Mars in 2028. So by then, of course, Mars 2020 will already be 8 years old. So it's starting to get on a little bit. And we're worried about then the age. Hopefully it will still be there and we'll be able to make use of it. But it's good that we have another rover there, which will land on Mars with one specific job. It will go from where it lands to the depot to collect all the samples from the depot and take them back to the actual lander. At the lander itself, it will actually put them into a specific launcher. So this will also be a first, because we're going to be having a launch from another planet. And that's, you don't get more exciting than that for an interplanetary mission. That would be very, very unique. And what you see there in the picture also is the container where all these little capsules will be put inside, just at the top. So these little tubes will be collected by Mars 2020, and we'll put them in the depot. We'll take them back to the launcher. They'll be put inside a small capsule inside the launch vehicle, which will then be put in orbit around Mars itself. At the same time, in 2026, we will also launch from Earth the Earth Return Orbiter, which is the one that I'm most interested in because I'm very, very heavily involved in many of these projects. So the Earth Return Orbiter will also have to go to Mars and actually have to catch the sample and bring it back from Mars back to Earth, hence the Mars Sample Return Campaign and the 3 missions that put it together. So let me give you an example of what the spacecraft actually looks like. Okay, so it's a solar-powered spacecraft. We don't have any atomic power on there. This was already ruled out right at the beginning. So many of the deep space missions, because you're going further from the sun, normally you use atomic power just to give it enough energy. That we already knew that we weren't going to do for this particular mission. The consequence is we're doing solar power. We have huge solar arrays. I mean, it really is massive. We're creating basically 41 kilowatts of energy from this solar power. That's not just only to give power just for the equipment, but it's also because we're actually using electric propulsion to get us all the way to Mars and back. So we're not using chemical propulsion and a ballistic trajectory. We're actually using EP thrusting, which is a very low power, but it gives you thrust for a very long period of time for a very high ISP. So we actually have 4 electric propulsion engines on the system, and we have 2 additional chemical propulsion systems, which I'll go on to a little bit later. In addition, there's a lot of comms activities which we have to do. So we have a 100-watt TWTA at X-band, which is the normal one for deep space missions. And we have a large 2.3-meter antenna in order to have a high enough data rate between us and Mars at the maximum distance. Also, because of safety requirements, we actually have to have a triple redundant telecom system. And we have 4 onboard computers with security modules in order to control the communications. In addition to that, because we have landed assets on the ground, we actually have a UHF communication systems for doing the relay between our orbiter and the ground, so that we can send that data back and forth between Earth. So one of the key functionalities of this spacecraft is the overall communications between the Mars assets, coordinating them, and Earth as well. So here you have a breakdown of the actual spacecraft in its 3 main core elements. The bottom part is actually what we call the orbit insertion module. So that's the first chemical propulsion stage, and it's actually a kick stage for as we arrive at Mars, it will do the main orbit insertion, and after that, that unit is dead. We don't need it anymore. It's done its job for us, and we actually eject it because we don't want that dead mass anymore for the later phases of the mission. The central part is the actual main core. The main module for the spacecraft, where you see the high gain antenna, all of the main internal avionics are in that main module. And then on the top there, you see it just standing above it with a tripod and a sort of mushroom there. That's actually what we call the capture containment return system. So that's actually provided to us by our colleagues at NASA, and it actually helps us by we actually collect the orbit sample into that module. We process it within that module. We also do in-orbit brazing within that module when we put the samples into a return system as well. And also it contains the Earth entry system for when we come back. So you can see there's 3 main parts to this spacecraft, which is really much an international activity between ESA and NASA to bring this together, and also with our colleagues in Airbus, who are our main industrial partner for this particular spacecraft. Okay, so what are the different mission phases? I think I've already started to go through it. We're launching from our main launch base in French Guiana using an Ariane 6-4. We have an outbound cruise phase, which we're doing with electric propulsion. We then have the orbit injection using a chemical propulsion system, at which point we dump our orbit insertion module. And then as we start doing an electric propulsion descent phase, going down to the lower levels to a specific orbital trajectory, we then do communications with our ground assets, which is mainly with the rover and also with the lander, and if we can, hopefully with Mars 2020 as well. Then once we catch the orbit sample, and then we start processing it inside, then slowly we'll start spiraling back up again using electric propulsion, and then we'll have a escape velocity from Mars to come back to Earth, hopefully within 2031. This is our target. This is when we want to be back returning towards Earth. Because of course, you have to remember that from the dynamics between Earth and Mars, you always have this 2-year window, which is coming up and down for when the 2 planets are closest together, which is what you're always targeting for. So as we come back towards Earth then, at some point we want to release the Earth entry system to come back into Earth. And then at that point then, the spacecraft, ERO, will be put into an Earth avoidance trajectory so that we then lose and we go back into deep space. So this is our target as well, and one of the activities. You can see it's a very complicated mission with many, many different phases and many different steps in order to get it to actually work and actually to be successful, which also makes it very exciting. Okay, but why security? What does security have to do with this whole activity and this whole complicated series of events? And there is actually a very, very specific reason. You have this group called COSPAR, the Committee for Space Research. And within that, there is a very specific area which I look at, which is called planetary protection. One of the things that's been realized very early on, even before the Outer Space Treaty was signed, which is also part of this group's activity, is that we have to be very conscious and careful of what we're taking out from Earth to other planets and actually what we're bringing back. So this is to do with forward planetary protection, that we don't want to contaminate other planets with certain things from Earth, but also for our own biosphere. We want to be very careful of what we're bringing back into our own biosphere as well. I mean, in fact, this was also looked at, for instance, for the Apollo missions. For Apollo 11, when the astronauts first came back, there were lots of questions about what is on the moon, and they didn't know even then. I mean, now we know that the moon is completely inert, but back at that time, when the astronauts came back, the first thing that they did was to put their astronauts into hazmat suits before immediately when they got out of the Apollo vehicle, and then they shipped them into a containment area for a whole month of quarantine before they actually let them out, when they realized, okay, there's nothing on the moon, we have nothing to worry about. So these guys really, they're looking after our planet for us, and they've set certain rules in place for us on what can and cannot happen when you go to specific planets and specific environments. So we're very careful of that, especially today with issues like COVID and so on. People are very conscious of what you can and cannot do from the space environment. So with that in mind, this is why we have security and safety standards. So really, in this case here, for ERO, it's a safety assurance is what we're looking at from the security context, or I should say security assurance for safety. Okay. So with that in mind then, okay, let's go through it. So ERO is an unclassified mission. It has nothing to do with a restricted level or government grade security or anything like that. We're clearly an unclassified mission, but we have certain constraints that we are taking very carefully, and that's related to biocontamination of our biosphere and of Earth for both forwards, but mainly for backwards planetary protection, which is specifically graded by COSPAR. In addition to that, like many space missions, there is the issue of export controlled, dual use, and bearing in mind the requirements from various member states, ITAR, EAR, and all these sort of items as well. It has to be taken into account for most missions. Of course, we're bringing something that has to land back on Earth, and it has to enter a certain area. Our target land space will be actually in the Utah test range, which is actually a military area in the US. So we'll also have to do coordination with US airspace as we're coming in. I mean, the last thing we want, of course, is to cause an international incident where the US are unaware that this is coming in at a certain time. So this is carefully coordinated with our colleagues in the US so that they know when this is happening, and they can work with us on the inbound trajectory, and they recognize it, and they don't think it's a missile or anything like that that's coming in. It's a very carefully controlled situation and carefully understood. The trajectory will be carefully monitored and precisely known for that particular inbound trajectory. And of course, as has been mentioned with various other colleagues and various other presentations, we're very interested in assuring the mission success and in the reputation of the agency for the quality of this particular mission. So there are many, actually, you can see at different levels, many requirements of why security is actually interesting for us on this particular mission. And I just want to add this slide as well, of course, there's been a lot of interest recently over the past year on hacking, on cyber issues. We have things like the DoD event on their DoD hackathon, where they've been looking at, and they have bring in ethical hackers to help them to understand how sensitive their systems are, or various other systems. We're aware of, if you do a literature search, for example, that there have been potential issues. How real or not they are, it remains to be discussed by various other groups. There have been the events of ransomware recently. We've seen it recently, the case of the Colonial Pipeline in the US. We've seen the hospital in Ireland, which has had ransomware issues. Also with space technology, You get the problem of identity theft on things which are transmitted over the air, for example, if it's not encrypted. So there are cases where you can see that space technology, if we're not careful, it can be abused by certain groups in an unwanted way. Yeah. And this we have to be careful of. Okay, so within this particular project, what is the process that we've used and applied for security? So in doing that, we've been looking specifically at the CCSDS and those particular standards in parallel to the ongoing ECSS development within ESA as well. But the CCSDS is clearly quite well developed. They've been looking at how we've been doing security for a number of different projects across ESA, and ESA has also been working with the CCSDS in developing those particular standards for security itself as well. Within that then, we developed very early on within ERO a security working group to define what were the security objectives, what were the security targets, to go through and identify from our stakeholders what was their risk profile, what was their main concerns. And based on that then we could identify what was the risk appetite and what was their sensitivity level for certain security layers. Then we went through and did a threats and vulnerability activity and identified what was the security risk assessment for our particular project, which then allowed us to feed in to our targets that we had and our requirements for our mission. In addition to that, there is a number of areas within ESA, with our existing standards, such as safety, dependability, reliability, and our testing, which you can map directly to security because it mirrors certain needs that you would have in security. And that brings a lot of benefit and robustness in a security architecture. You don't have to develop it all from new. You can look at your existing processes and the existing ISMS, and you can map that to the certain standards that you need so that you can get commonality without having to develop things from new. And that's very beneficial for any project which is running forwards in its time. Okay, so I want to wrap this up a little bit now because there are certain takeaway messages that I want to put forward to yourselves and to the community. We have to be careful on how we apply security. We don't just say, there needs to be security, so we just apply a certain level of encryption. We need to really target the level of security that we need based on the risk that we actually see. So based on the security analysis that's been performed and based on that particular risk appetite. Because if you put it too high, it can actually be a barrier to the activities you want to perform, depending on what's going on at that time. So you have to target it at the right level for the particular circumstance and for the situation that you're particularly looking at. We need to understand the needs of our stakeholders. What are they really worried about? What is their main concern? What are the assets that we're trying to protect? Yeah, it's not just putting the security randomly. It's specifically targeted for a specific case, for specific situations. And from the risk analysis, we really identify who we're protecting against and what are the situations. And then we focus our security at that particular threshold, and you put it for a specific reason. And then finally, is thinking about the security. There are certain cases where you see where security is just put as a knee-jerk reaction. There is a benefit from thinking of security from an end-to-end perspective. So you start right at the beginning, and you already have some ideas on security right at the start of any particular project, already when you're at the study phase. And that sets the groundwork for gently increasing the security level and getting it right as you go through the project, as you develop it in time. And this is where it's been quite good with ERO, because we recognize that not too late, but also at a critical phase when we're already starting with the ITTs to say, okay, we needed to have certain security there. And then we were starting to ask ourselves the question of what sort of security we needed at that particular phase. So this is something where I wanted to say, please take your security from a full end-to-end perspective, and then you know how much you need to apply at the different phases as you go through. My final message really is that security is a system engineering process. It has a full V life cycle, like many system engineering processes, irrespective of whether you're using architecture frameworks or other model-based system engineering tools. You can apply that exactly in the same way using a system engineering process to security as well, and using a full end-to-end life cycle for security. Okay, I think that was my last slide. So with that, I would like to say thank you, and I wanted to open the floor for questions. Thank you very much.
Wow, thank you, Eddie. So, sorry, I'm going to do it from here. Is there any questions from the floor? That's a big surprise. There's at least one question from the floor, Eddie, so I'll take my mask off here. The sample, how big is the sample, and how big is it that this your ERO has to spot and detect?
Yeah, exactly. It's you can think about the size of a football. It's not much bigger than a football. So if you imagine that's a small thing orbiting Mars, and we're looking to try and find it optically. So we've got a camera on board the spacecraft, which is mounted on the CCRS. There's two cameras there, which is looking around in space for a football orbiting around Mars, around about a 300-kilometer altitude. And then we're targeting it using optics, and then we slowly try to catch up with it, sneak up, and then catch it and ingest it into the system. So it's challenging, and it's a lot of fun. Yeah.
Sounds very
it's a penalty kick. Yes.
Penalty kick, yeah.
I don't like penalty kicks as a British person. They always go wrong.
Not this week.
No.
I've got another one from Nadia. What kind of electrical propulsion are you using?
Yeah, because of course there's two types. There's dual gridded and there's the Hall effect thrusters. We're using dual gridded thrusters. Yeah.
Okay. Okay. Excuse me. Okay, Melanie.
Please. Yes.
I was wondering, you're saying you're avoiding Earth on your return. Is there anything that the orbiter will do after? Does it still have any remaining mission after passing back the sample?
At this moment in time, there is not actually there's no extended mission. So after we've released the sample back to for its Earth entry, we'll do some photography of it a little bit just to confirm the trajectory that it's correct, so that we can then let the ground assets know what's going on in case they need to do anything urgent. But then the Earth return orbiter will do an Earth avoidance maneuver and then just go into deep space. And according to the planetary protection requirements, we have to go into deep space for 100 years. So we then have to just perform the avoidance maneuver to ensure accurately that we will not return to Earth for at least 100 years. Of course, I would love that it doesn't then goes on to an extended mission for something else. But today that's not actually identified. I think if you look at other missions, for instance, like Hayabusa, for example, they then said, okay, yes, great, let's now have an extended mission because they were confident of the life of the spacecraft and they had sufficient fuel. Obviously, we will go with a fuel margin in case there's any urgency, but it's not currently targeted to have an extended mission.
Thank you.
I see you have more questions, please.
Thank you very much. Really interesting. There's obviously plans to maybe land human on Mars before the end of the decade. Are you facing any competition from people like SpaceX, I guess, that are planning to go there and back?
That's one of the jokes that we have indeed within the project. Yeah, if things take too long, maybe you'll start to see people on Mars and they'll just help the rover by putting it onto the That's one of the in-jokes that we have as well. Naturally, there is competition, of course, yes. Because, the whole point is to do this in advance of the need of manned missions. And obviously there's competition obviously with other agencies as well. Yeah, it'd be great that we're the first ones to do it, to bring something back from Mars. Yeah, that would be a wonderful thing. Obviously the Chinese have also just got to Mars as well with their own rover. They're also talking about a Mars return mission as well. So yes, there's the natural competition to be the first one to achieve this great feat. It's a lot of fun. Yeah. Please, I have another question in the background.
Yes, hello. You mentioned that the ECSS is under development, but as far as I know, there is no recommendation for industry right now what to do, how they have to assess their work, what security measures to have in the project. Are there some ambitions to give guidelines for our industry, what to do, in which phases, and also to strengthen maybe the ground segment, because I have the impression ground segment is often forgotten.
Actually, there's quite a lot I could say on that. Obviously, I have to be a bit careful of time as well. But yes, when you look at a system, I'm not only talking about the spacecraft itself. Obviously, there is security infrastructure that we're putting on board the spacecraft, but you have to look at the whole system end to end, including the ground segment. And the ground segment is a key part of the overall system. So when of course, within our context, we're not just talking about the space segment, but includes the ground facilities, what ESOC is doing, what sort of information security management system ESOC will have, or any other ground infrastructure that you're going to be using that has to be looked at from a full end-to-end perspective for all of its security layers. For example, even the VSATs that you're using for your communication system, if you're using VSATs or if you're using a fiber link or any sort of communications, that has to be all part of it for the full end-to-end security. When you talk about standards, I would suggest really to look at the CCSDS, which is the standard that's used for by us as well. It's one of the key ones for security. Even though we're developing an ECSS, that will happen in parallel to that. But from an industry perspective, I think many industries have a good understanding of how to do security and have their own information security management system in place. So when you're looking at an unclassified project, I think the first thing really is to go through the steps and the process that they identify in the ECSS, and then model that and say, okay, how closely does that fit for our particular project? What are the sensitivities? And based on what we're concerned about, then you start to adjust a standard to see what you're required for your level of sensitivity. And I'm pretty sure within the CCSDS, it also gives the hints in that particular direction.
Okay. Yeah. And are there some ambitions to develop something to give a low-cost encryption solution for the European space project, so that not everyone has to develop something new?
Well, I think this is the whole role of standards, indeed, because what you're seeing then is that with ESA, we're developing an ECSS. I think I'm hoping once that's right, it will give us different layers depending on the project types for certain standards, and then hopefully we'll see then that you will be able to get off-the-shelf components and equipments which fit within those sort of standards. Yeah. But it's the future, it's what's being developed, I agree.
Okay, thanks.
Yeah, I hope so as well, yes. Were there any other questions? I don't know if there's anything online as well.
Nothing online at the moment.
Okay.
Okay, thank you, Eddie.
Thank you.
Wow, thank you, Eddie. So I can just probably add just a little bit to what Eddie just said there. There's actually a number of initiatives at the moment. If you look at the ECSS E50 telecom standard, there's already since 2008 a few recommendations. One in particular says, strongly consider CC authentication, yeah, and do a risk analysis for other levels. So that's already since there 2008. CCSDS 350 series are the ones you should look at. There's a green book for the mission planners. So in there you've got a standard set of threats, some examples for different types of missions in there. So they're quite useful references for you. And I think 352, the blue books, they effectively align with the FIPS and NIST recommendations. I think Brandon might be touching on that a little bit later on as well. There are also a number of initiatives as well. There's a project, small project that the TechQ is launching imminently, which is looking at the process for security assessment. And also they produced an internal ESSB, I think, for secure software development. And also if you look at the OPSAT, they've already done some trials of running in software on the OPSAT some encryption as well, aligned with CCSDS. So I think that answers a number of the points, so you can see what's going on. But yeah, there is a lot of direction at the moment within the agency. And I'm getting the questions from Eddie's project manager and other project managers about, yeah, what do we do about putting something like an ECSS? We've got CCSDS, how about something like an ECSS? And I'd also recommend looking at the bundle security protocol as well. I know NASA are looking at that very strongly. And I'm sure Brandon's online now and he'll probably touch on that later on for us, because I know you're interested in that. I'm just looking at the time. It's sort of, unfortunately, we should have Danilo here to give us an insight into cyber threat intelligence. Unfortunately, due to illness, he can't make it today. So I think maybe just for the final 5 minutes here, just before we touch on to a break. I don't know if you've heard throughout the day, you've had 3 people at least talk about risk management. You know, you talked about what is risk.
effectively it's your impact by your likelihood. So what is the impact? And then you do business impact analysis in terms of reputations, operations, cost, time, schedule, how much does it impact your reputation? What will be the damage to you? And within the agency, in our regulation, we have two main principles: protect the investments of the member states and protect the reputation of the agency. What does that mean? It's huge. So from investment with the member states, they're investing in all this future technology. It's unclassified, but it's important for the industry of Europe. So we as an agency, we have to raise awareness to say, well, okay, Mr. Industry, how important is that new thrust you're developing? Would you be happy if we published the specifications for that online? Maybe it's fine. In a symposium like this, if we can present a lot of information, but maybe there's certain information, if we publish that, then we lose our competitive advantage. The exact how you polish the lens could be a very, very specific industry. One company could have that information. So they don't want that published everywhere. So this is something when you think about reputation or you think about confidentiality, integrity, availability, it's about raising that awareness. But also, when you think about likelihood of a threat, you've got the resources, you've got the motivation, the capability. So they're all a factor. So if you're following what's going on recently, the oil pipeline attack recently, which was a supply chain attack, you say, well, how would that affect us as industry during the development phase, during the spacecraft compatibility test? How would that affect us during the launch and early operations? As Eddie was explaining, there's critical phases in the RO. Which points are critical for them? Which points are the most sensitive? Do we protect the whole mission, or do we focus on those key points? So this is what we call risk analysis. We look at all across the phases. We say, what is important to you? How much are you willing to insure yourself? Denis was talking about insurance. Risk is insurance in reality. It costs you money to put a lot of security in. It costs you a lot less if you do it through the life cycle. It is a process. It's not a product, it's a process. You have products that help you with security. So you've also got to think about your adversary. If I've got a science satellite, how useful is that? How important is that for someone to attack? What would be their motivation? So if I go 20 years ago, they'd have low motivation because it's very difficult. I've got to build a big antenna in my back garden. It's very complicated. It's really difficult. If you've watched, there was a presentation by Purvey in Black Hat 2 years ago. 700 euros worth of equipment. He's now linking through to VSATs, sniffing off the link, publishing lots of papers saying how insecure space is. Well, if you're happy for people to read your data, make it public, fine. But let's say the barrier is increasing in a similar way. I'll try and give you an analogy. In a similar way to HTTP and HTTPS, so that what you use every day on your web browser. You're looking for the little lock icon every day now. If you don't see that lock icon, do I trust this website? 20 years ago, nobody cared. Nowadays, do I worry about this? And in a similar way, we see now that the adversary capability, the barrier to access space is reducing. There's more commercialization in space. You see much more interest in space. You'll hear from Brandon about Space Policy Directive 5, published by the US. This space is now officially for NATO, US, and a number of states, the next warfighting domain. So they see it. It's changing. So this is something that, as an industry, we need to raise awareness, internally, externally, and it covers across the board, which is why we're really, really thankful for SpaceTech this year, looking at space situation awareness, the environment. All of that is availability in space. Holger and his team are taking great care of that. We're really grateful for that. You've got the integrity. How secure is your satellite in terms of somebody corrupting a message? And then you've got confidentiality. What do you want to protect? Is it only that you want to maintain the integrity, or you want the confidentiality as well? So all these are basic things that you just think about as industry. So I'll leave you with that, and maybe now's a good time to go for a coffee break. And I think Brandon will be available at 3:30. So maybe if we could be back here just before 3:30. And I know you'll be very interested in Brandon. he is one of the highest profile space security guys around, member of this ECSTS security working group and a number of security working groups. So we're very honoured to have him, and we're looking forward to having him in 15 minutes. So thank you very much. Okay, I hope you had a nice bio break and a coffee, a biscuit. So I'd like to welcome Brandon Bailey from Aerospace Corporation in the US. Brandon is a cybersecurity senior project leader. Josie, can you just check the things are muted from the hall? I'm not sure the panelists can hear us from the hall. You see ECTLS for the room. Newton. Sorry. He's a project leader at Aerospace Corporation. He has more than 14 years' experience supporting the intelligence and civil space arena. Brandon's specialities include vulnerability assessments, penetration testing for space systems, and infusing secure coding principles within the software supply chain. Before joining aerospace, Brandon worked for NASA, where he was responsible for building and maintaining a software testing and research laboratory to include a robust cybersecurity range, as well as spearheading an innovative cybersecurity assessments of ground infrastructure that supports NASA's mission operations. So it's with great pleasure. There we go. I'll hand over to Brandon. Thank you, Brandon.
Thank you. So, yeah. So I've been focusing on cybersecurity for space for a few years now, and spent a lot of time at NASA, but now I work for the Aerospace Corp. So there on the title slide, and these slides have been provided, there are some link to some papers that have been published over the last couple of years, and more to come on that front. But if you're interested in kind of getting introduced to some of the concepts that we're going to talk about in this presentation related to security, give those papers a look. So we'll kind of jump right into it. And the speaker before me provided some good introductions, as well as John, into kind of the shifting mindset as it relates to security in space. So we've had we're moving to this constellation architecture as in the future, and with that migration into that architecture, we're starting to understand what are some of the most likely threats that we may see from a security perspective. So when you talk about security for space, it traditionally, at least in the U.S., we've talked about directed energy, kinetic attacks, jamming, spoofing, those type of EW or kinetic, and cyber has not necessarily been forefront in the discussion. So what we're going to talk about in this presentation is kind of introduction into cyber and what we're trying to do about it in the U.S. and what some of the things that we're trying to promote from the Aerospace Corporation to our customer base, which is mostly government entities in the U.S. So we're going to focus on the cyber side and not really focus on directed energy or any of those other attacks. Those are obviously valid attack vectors, but we're going to focus on the security side. So traditionally, when we talk about cybersecurity for space, we have really been limited to some of the your encryption, your ComSec, or your transmission security transec, and even in some rare cases, maybe some sort of tempest control where you electromagnetic signals emanating from the vehicle that you want to protect against. So it really has been mostly around encryption and authentication has really been where the discussion has stopped, and we're starting to see some changes on our side of thinking outside just the typical encryption and authentication on the TT and C-Link, and expanding into more robust security procedures and security requirements and things like that. Because what we're seeing is the threat landscape is changed a little bit from what we once knew. And this graphic, we'll have variations of this graphic depicted throughout the presentation, but the graphic on the right is just trying to articulate the kind of environment that we live in, from rendezvous satellites, rogue satellites that could come close to yours, to rogue ground stations, to attacking your own ground systems or your user community, doing man in the middle, or attacking crosslinks. So there's a bunch of different vectors that you need to consider when you develop your security strategy. And one of the things that I'm a proponent of is details. So what we're seeing in a lot of publications, articles, blogs that get put out is cyber is really a black box. So whenever you see like a threat assessment, typically on any type of space mission, it'll be, you know, directed energy threat or laser comm threat or something like that, and then they'll have cyber, like they'll just say cyber, and then there's no real decomposition of that. Like, what does that mean? Are you talking about the supply chain? Are you talking about the TT&C area? Are you talking about the ground system? Are you talking about the onboard system? Like, is that a weakness from a cyber perspective? So it's, we're trying to decompose that black box a little bit and educate people on what the vectors could be. And that way you can put in the mitigating factors. So we've put out some papers. Unfortunately, we're going through the process of getting the TOR that's listed there, TOR 2021-133, getting approved through public release so that it can go out to the whole community. Currently, it's just for U.S. government and contractors, but we're hopeful in the near term. It'll be public release, because a lot of the information in this presentation is further expounded in that document. But we do have some ancillary material like linked on the front slide that provides some higher level ideas, not the details that TOR does. So, but one of the things where we feel like we are a little lacking in this area is defining the right cyber requirements. And that if we feel like if we had the right security requirements, we would be in a better situation than we currently are. So that could come through standards, which I've heard multiple people talk about ECSS and other standards that are available. I have some backup slides about what standards are currently available, but we don't have, it's very true that we don't have a kind of a definitely not a global, not even a country, you know, US country security standard for space. And we're starting to see some migration into that as something that we need to address. And we'll talk about what we do have moving forward. So the way in the US, the way we kind of do things is our agencies, could be Department of Defense, could be NASA, could be whomever, they'll have some sort of policy document. And that's where it basically points to some sort of quote unquote security requirement. And what those requirements really are just the control baselines. So I'm not sure if the audience is super familiar with some of the, you know, in the US and how like we used NIST, like 800-53. I think ISO is more adopted in the international communities, but in America, we have, for our national security systems, we have what's called CNSSI 1253, and they have what's called the space overlay that goes on top of that. So there was an attempt to take that kind of default NIST 800-53 control baseline set and try to translate that to security context for a spacecraft as well as launch systems. And it does, you know, a decent job of articulating how some of these could apply. But if you've ever actually analyzed the control baselines that exist through NIST or CNSSI 1253 or maybe even ISO, they're more guiding principles than requirements. And we don't, when you do system engineering, as the previous speaker said, security is a system engineering problem just like anything else. In system engineering, we design to requirements. So what we feel like we need to articulate better are the kind of the requirements that we expect. So we need to get from either some policy saying thou shalt do security to even we feel like you should do access control or account management or whatever program shall do something, to the space vehicle needs to do, needs to authenticate the ground station. The vehicle needs to, do X, Y, and Z, and those type of things. That way we have a better chance of ensuring that we have the proper threat mitigations in there. So we're really pushing to get the specification level requirements established so that we can make sure that we have proper threat mitigation moving forward. And we're going to dive into that a little bit. Like I said, in America, in the traditional IT world, we've lived in the NIST realm, the risk management framework. Some people are leveraging the cybersecurity framework. And like I said before, there was discussion, there has been a space overlay that's been produced. So it's public domain knowledge as well. So if you just look for CNSSI 1253 Appendix F, you'll see what was put together there. It is an adaptation of kind of the NIST RMF baseline for space. It has some gaps, as we found through this analysis that I performed, but it is a good starting point, and that's the key. And that's one of the deficiencies with people who leverage the risk management framework for space or for really any system. They usually take that low, moderate, high baseline watermark, that NIST or other whatever publication you're looking for. They take those watermarks as the measuring stick. Like that's where they want to get to. And if you actually read either NIST or CNSSI 1253 or any of those kind of security focused initiatives, they articulate that that's merely the starting point. That's not the end goal. So if you leverage those documents as such as, hey, we'll take consideration that if feel like we're require a moderate level of security, we'll take what they say into consideration, but we'll also analyze the whole catalog of requirements. We'll do the whole catalog of requirements and we'll add to it. So based on my analysis from the RMF control baseline, I know the audience may not be using RMF, but just as an example, this is an example of trying to apply traditional IT-based policies and procedures to like a spacecraft, for instance. If you take the moderate baseline for a spacecraft, about 75% of those aren't really applicable directly to a spacecraft architecture and a spacecraft technology. And then there's probably around 80 more controls that should be enabled that are outside of that baseline. So my point is, you can't just take these traditional IT standards and adopt them and apply them directly. You have to do some tailoring. And that's what we try to do with the information that we're going to talk through today. So there has been efforts to mold these frameworks, but its uniformity definitely is lacking. And so SPD 5, so for those who are not aware, Space Policy Directive 5 was a policy that was enacted by the previous administration in the government, the Trump administration, to really point out the fact that space and cyber are interlinked, and we really need to do something about it. And we need to put in guiding principles, establish standards, share information, and they pointed out a lot of different deficiencies that we currently have in our strategy for securing space on the U.S. side. And this is just a slide that talks a little bit about it in case you haven't heard about it. And it's essentially, the tagline is basically protect space systems from cyber incidents, which is just like any other incident, in my opinion. We want to protect against any type of incident, but this is focused specifically on security. And it talks about, doing security from ground and space during all phases using risk-based analysis. And it says you must include, the operational technology on the ground, including all the ground infrastructure, including the ICS or operational technology, the software, all the software that is involved. Consider SWAP, size, weight, and power constraints, and what the mission is. And you basically put all that information together to kind of come up with your strategy for securing it. And it goes through a list of some examples that you would want to do. So some of the things that it actually calls out directly, which, if you're looking for a bare minimum standard, in my opinion, of like, okay, if I had to do 5 things for security, maybe this is a good starting point to read this document. It gives you high level, things to do. So physical security of your TT&C environment, which is pretty obvious, right? You don't want someone to be able to walk right up to your command and control workstation and perform some sort of, cyber attack. Then it goes into protecting the TT&C link with encryption and authentication, and then jamming and spoofing protections, as well as supply chain risk management and insider threat. So it kind of covers those 5. A few of those are pretty generic, like supply chain and insider threat. Like, it's easy to throw those bullet points in there and say, do those, but those are extremely difficult problems to solve. So, but it is noted that you should need to consider how the supply chain risk could affect you, as well as insider threat. And depending on, what environment you're in, the science community, maybe not as much, but the national security community has been this way for a long time. But physical protection, TT&C, jamming and spoofing, those have all been things that have been going on for years in certain communities, but maybe not others. So it was good to try to put this out there to say, hey, this is the bare minimum we feel like anybody that's putting something into space should really consider. And then it talks a little bit about, some generic cyber hygiene, which is really repetitive of other things, but it does make call outs to leveraging NIST, RMF, or CSF where you can. And then it goes into promoting best practices and policies through ISACs. So in America, we've established that this space ISAC community, which is more than just America, it's actually a global. We have international partners that are involved in that. So you might want to look into the space ISAC. I think it's like s-isac.org or something like that. to learn more about that, because there's threat intelligence sharing, there's all sorts of information that kind of goes through the ISAC. But the main takeaway from my perspective after I read SPD5 is pretty intuitive, right? Threat-informed risk-based engineering, which is what security professionals that are serious about security, that's what we've always promoted, is understand your threat and understand your risk posture and then design accordingly. So that's nothing really new, but it is good to see, at least from the White House perspective in America, that that's something that they believe in as well. And the Biden administration is carrying forward SPD5. And so we're hoping to see some change in our area. In my personal opinion, as a security guy, which is, you take it with a grain of salt, I suppose, is I think we need to go above and beyond these 5 or 6 areas. And I'll talk about what that is. So why should we do this? Like, what's our motivation? It's not really because there's a policy that says you should do security. Like, that's not the answer. Just because the policy says so, it's really the threat environment's changed. So as John said earlier, space is a war fighting domain. Like, that is where we are moving towards. And there are open source doctrine that has been published from, at least on the US side, from the DIA, specifically referencing nation states that are advancing offensive cyberspace capabilities in the space realm to have superiority from that perspective. So it's not just science fiction at this point. It's open source doctrine, and it's kind of a well known thing. It's not protected by some sort of classification of information. It's pretty widely spread that certain nations are looking to leverage offensive cyber in their strategy for space dominance. So that's just something to keep in mind, and we're moving forward with that. So here's an example. There was a chart in the earlier presentation that talked about some cyber incidents, and so what I wanted to do, like, I like to provide some examples as well, but we're not going to dive into these. These are just a few. I broke them down from like the ground segment to potentially like the link layer to like onboard attacks, and starting from 2005 to 2020, and there's multiple examples of attacks that have happened that we can pull from that used to be hard to find, but now they're a little bit easier to find. I mean, the interesting thing is, I think one of the interesting pieces to all this from a security perspective is just if you follow the industrial control system world, the IoT world, and how that's progressed over the last few years, you can kind of see indicators when you keep an eye on things like DEF CON and Black Hat, and you start seeing presentations pop up, and you start seeing demonstrations of security researchers, attacking various aspects of technology. You're starting to see people get motivated to look into this stuff. So just in the last 2 years, you've seen an explosion of aerospace or space-centric presentations at DEF CON and Black Hat. You've seen the aerospace village even become a thing with a space focus. You've seen the DEF CON Hackasat events. You've seen presentations at Black Hat from various people. So you're starting to see the community start to rise up in this area. So that's proving that in my opinion, the security by obscurity model that we've lived by for a while has kind of gone by the wayside, and now we're seeing people actually starting to look into this. So, I would postulate my assertion is you can have two kind of thoughts on this. So one is we don't have a lot of known security vulnerabilities in our space architectures, like PowerPC architecture or Spark or software that we use like VxWorks or whatever that we're using. We don't have vulnerabilities in that because they were built so secure, like they just don't exist, or we've not had people looking for them. So I'm not sure where you sat on that side of the fence. I sat on the latter side of that because I've seen people start looking into this and they're finding things left and right. So my assertion really is it's like a shark. It's going to be like a shark to water, in my opinion. Once people start looking into these things, there's going to be more and more vulnerabilities that are disclosed and put out into the community. So that's just my take on it. So how do you protect against all this? And so it's really a risk-based decision, and it's where do you apply security to get the most bang for the buck and what makes the most sense. So it is a security and system engineering problem. And the way I like to look at security for space systems is kind of like through the onion lens. So that's the defense in depth applying defenses at multiple layers, so you can hopefully kill the attack chain somewhere along the way. So on the ground system, there's a multitude of controls and security principles that you can apply, and we won't go into each one of these, but this is just kind of a visual representation to kind of articulate, hey, from the data that's on the ground terminal to the software that's processing and interacting with it to the Windows or Linux machine that is networked together, that has some sort of monitoring and computer network defense architecture with some sort of perimeter security, with physical security, with a prevention plan. You have all these things in place, and you may want to pick and choose kind of at each layer where you feel like you can afford the most security for to not have an impact. And you can do the same thing on the space segment, in the link segment. So it's not just protect the ground at all costs and hope that no one achieves access to the spacecraft. It's more, pick and choose where you think you have the most threat on the ground, pick and choose where you feel like you have the most vulnerability and threat on the vehicle, and apply security accordingly. So what we've seen in the past is the crypto comms area over here has been the focus area of where people apply the most security, and they may not apply it on the ground as much. They may not put anything on board the vehicle with any type of root of trust or segregation or least privilege principles, and they may not use software development standards for security for spacecraft software. They may not have any type of fault management, intrusion prevention type of things if something does get on the vehicle. So you can kind of see how this plays out, and you want to pick and choose kind of where your security lies. And from our experience in the analysis that we've performed, doing multitude of pen tests and cyber assessments on ground systems and doing research on spacecraft, the items highlighted in red are where there's pretty regular gaps that are found in security implementations, and there are backup slides that has details on each one of these kind of gaps at a high level. So, and to point out, there's actually documented cyber threats at each layer. So what we're going to talk about is, I'm going to click through this real quickly, the threat side, but the threat agents, if you were to develop a generic threat model, which we've kind of adapted a generic threat model on a tiered scale, the tier 1 to tier 7 is, from a skill and malice overlaid with this kind of generic architecture, we've kind of put this out there into the community to kind of say, okay, if you're if you're a military satellite that does extremely important information gathering and supports war fighting or whatever, you probably want to be resilient against tier 1 through tier 7, right? Because you feel like in wartime people may attack you. You need to be resilient against all sorts of attacks. But maybe on the your CubeSat that's in orbit for 90 days, right? Okay, do you need to be resilient to the most capable state actor, a tier 7? Probably not, because the likelihood of them coming after you is probably pretty low. So you need to be maybe more resilient against script kiddies and hackers for hire type people. So you may need to only be resilient against certain types of threats and not all the types of threats. So it's just kind of trying to get people on this mindset of kind of what we feel like the skills of an adversary are against the attack surface, to kind of articulate, where you need to be from a security perspective. It's kind of some of the information that we've been putting out recently. So what we did was kind of take into account, like a generic threat model, we kind of took into account a lot of information. So what I did was review tons and tons of information across the federal government, civil space, open source, from CCSDS publications to kind of closed source material to aerospace internal information to all sorts of things. And I wanted to see, what are the actual cyber threats to like a spacecraft? Like, how do we decompose the cyber black box to actually mean something on the spacecraft? And that's what we did. And I developed like this generic library that we could use, and then help try to educate people on how to leverage the threats and vulnerabilities that I discovered through this research, and do like a 5x5 ranking to figure out which ones we need to mitigate. So essentially what you have in like that document that I produced, that's currently going through the release process, is I have the tables, multiple tables that have all this information. So I have threats and vulnerabilities, where they came from, what types of NIST controls would help mitigate it, what will be the tiered skill set of an adversary to maybe go after that type of attack. and where it kind of sits in that defense in depth graphic. So I have all these tables that have been put together that kind of cross-reference all this information. So I wanted to make sure I kept where I pulled the information from, like the CCSDS Threat Green Book, or maybe the NASA documents, or maybe something, you know, from the closed source commercial world, and then keep in mind what attack patterns or what CAPEX or attack patterns that people would use to exploit those, and what NIST controls or security standards could help mitigate those. So that was what was put together. And so what came out of the results, so this is a little bit of an eye chart. It's not meant for you to read right now. You can read through these at your discretion later. But the point was to take that generic generic defense in depth graphic and try to overlay all the different types of threats and vulnerabilities kind of that were discovered through this analysis. And so what you'll notice is if you focused all your effort and all your security solution on cryptographic protections on the TT&C link, so you would be mitigating most of these threats in the crypto comms area. But if you look, I mean, there's a multitude of other cyber vulnerabilities and threats that could impact your system at other layers of the architecture. So the important piece is making sure that you understand that there are things at multiple layers that could affect you, and then design your security strategy accordingly. So how do you design that security strategy? And we've heard multiple people discuss risk management, and this is no different. So what I'm proposing is very similar. It's just now you just have a predefined list of cyber threats, and that you would obviously augment with your custom list that you may add through your own analytics. But essentially, you get all these threats and vulnerabilities kind of together, and you rack and stack them against your operational environment. Like, are you in a LEO, a GEO, a deep space, a cislunar? Are you a constellation? Are you a single satellite? All these architectural principles to kind of take into account to figure out where your threats may come from and what's most likely, and go from there and do a risk-based analysis. So when you're doing this risk-based analysis, what we found, and others have actually looked into this, is when you talk about risk, there's so many different ways to look at risk from a risk perspective. So it's like, but there are some kind of three common areas from like a criticality, a vulnerability, and a threat perspective. And one thing I like to understand is like how the likelihood of the threat kind of and risk comes into play there. So I like to add that into the overall calculation. And when we bring the likelihood into like this kind of risk calculation, I break likelihood down into kind of three-legged stool, which is important because I feel like it's important to understand all aspects of likelihood, because some aspects of likelihood would be, how difficult is it for this thing to actually happen? Like, can you do some sort of attack if I'm orbiting Mars versus a LEO mission? Like those attack vectors are a little bit different. If I have a completely isolated ground system where it's not connected to anything, then that changes the scenario. Or just how difficult is it in general to have the knowledge to do an attack? So that would come into like, what are the capabilities of an adversary to be able to exploit said vulnerability, in addition to what's their motivation? So you kind of take into account all these things to kind of help derive what the likelihood of this threat, vulnerability, and risk could really be. So that's kind of the important aspect of it, is understanding, these three-legged stool. So the motivation is always a difficult one, especially in the science community, because I get this all the time with people. It's like, I'm measuring, space weather. Like, why would anyone attack me? I'm measuring space weather, and it's a valid point. Why would they? But it could be just for fun. It could be just to establish that they can do it, to make a statement, or maybe you're right, no one would come after you because your mission's not that important to impact. So it just depends. So a lot of times motivation is a variable that you can't really understand all that well. So you either have to assume, you can make a constant assumption across the board on what the motivation will be to attack you in general, but then you can take into account adversary capabilities using like a generic threat model and the difficulty, put it all together as kind of what you can look for. So if you do that risk-based analysis and kind of going through the whole process, and you have all these threats and vulnerabilities that you've and defense and depth principles, you've kind of done all this work. So the long story short, and the kind of the so what is, if you take into all this information into account, and you take the threats from that previous chart into account. You can kind of do this pseudo measure of risk. Now, I don't want to get into discussions like, okay, is this a 4 on the likelihood scale or a 3? Is this a, are we sure this is a 5 by 5 or could this be a 5 by 4? Having those discussions isn't necessarily super beneficial all the time, because what I am advocating for with people is trying to figure out like where your risk tolerance is and where you make sure you need to include security. So like what I've kind of looked, and I've used this process and used this to kind of really figure out like where that red line is. I mean, if I'm if I have a high risk tolerance, then like maybe I only care about things that are like 25 and 24 on the scale. So then you can get into those discussions on like what's borderline. But if I have a low risk tolerance, then I want to get everything from like yellow and red up. And then the borderline things is where I'm going to have that discussion of like what security needs to be included. So it just depends on how you want to use kind of this process. It's pretty standard. It's not perfect, but the whole point is just having this list of threats and vulnerabilities and doing this analysis and figuring out where your risk tolerance is and deriving some security from that. And if you were to do that on kind of a generic space system, like a generic one ground system with one spacecraft, what's circled in red here, like through that process is like, if you go back to slide 19 here and you see, all these things on this scale above that red line basically are pretty much most of these things that are circled here. So you kind of see how this plays out, right? You think through the process, figure out your threat environment, do the analysis, and then you figure out which ones of these that I really need to kind of worry about. And then you derive your security requirements and security protections from there. So like similarly, you take that defense in depth graphic that I had earlier, then you pick certain security controls that security principles that you want to apply, and then kind of go from there. So it's pretty self-explanatory from that perspective. Now, where the rubber meets the road is like decomposing each one of these little red text buttons into the requirements. And we've already actually done that. But we can't share that whole requirements database quite yet with the community. We're working towards getting that through the government process to get it fully released. But we do have all this information already predetermined. We have every threat that was on that list has mitigating requirements already established, and we're working through that release process. I was hoping to have that approved before coming to speak, so I could just say, hey, you have all this information for you, but it's just not there yet. Unfortunately, the government works a little slow on the approval process of releasing information, so apologies for that. But long story short, there has been it's easy to kind of ignore security at times because we haven't had that gotcha moment for space. Like in the ICS world, we've had it multiple times over. Industrial control system world, we had it with Colonial Pipeline in America. We've had it with other ICS environments. We've had it with IT networks, solar winds. So we've had all these aha, gotcha, big moments in all sorts of other industries. It just hasn't happened to space quite yet. We've had like blips, right? We've had Landsat get a command lock from an adversary. We've had ground intrusions at JPL that have access to certain information. We've had ground intrusions at Kennedy Space Center on the NASA side. We've had all these little blips, but we haven't had this like aha moment in the US. But I think people see the writing on the wall and they're starting to make the shift to say, okay, let's not wait for that aha moment like, oh, something bad really happened to be reactive. Let's try to be a little bit proactive in this area. So that's kind of what we're seeing on our side today. And SPD5, NIST, all these documents, everyone just talks about doing risk-based analysis and defense in depth, or risk-based analysis to help derive your security. So like that's a pretty standard practice. It's just what framework are you using, what data set are you using, and in my opinion, the graphics that I've put through this presentation today on defense in depth, like there's nothing really new there, right? That's just a different lens to look at the problem, because it helps people understand security a little bit easier at times, as opposed to just saying, hey, go read this ISO document or read this NIST document, it'll tell you how to do security. Just trying to do that translation for people that says, hey, when I say command link intrusion threat, that means these NIST controls. That means these principles: authentication, encryption, key management. That's how that translates. So it tries to help people make those linkages a little bit easier. And we've had some, on our side, this side of the pond, we have like some probably inadequate cyber requirements at times, but sometimes we have really good cyber requirements, then we have bad governance. We have, like, the governance just doesn't follow through on the requirements that were established. So we've had both sides of the coin on certain programs. One is like there's been no security requirements, so then governance can't really hold anyone accountable for being insecure. And then we've had good cyber requirements and the government fails to be able to ensure that it was properly
2 minutes, Brandon.
So, yep. And then so you can use threat modeling and this 5x5 type of analysis to kind of go through it with adversary tiers and all that stuff. And all this stuff's written out in various publications that we've put out. And my opinion is, once you actually have your solution put in place, having that governance structure and having like technical evaluation of the actual defenses in place is super important. So you can't solely rely on a standard to protect you. Like, you need people who understand the security details to be able to govern and inspect the actual implementation to make a determination if it's real or fake. So with that, that's all. There's a bunch of backup slides from like standards to gaps to decomposing each one of those defense in depth things into actual, something that you might understand a little bit better. So all this data is in the backup. You can leverage it, and whenever that tour that I wrote becomes public domain, hopefully in the near future, we can get it to John and others, and they can distribute it across the community if you guys are interested. So with that said, I am done, and I will stop sharing. Thank you.
Thank you very much, Brandon. Definitely I want a copy of that tour when it's available. Any questions on the floor here? Do you have any online?
Can't see any online. I've got loads.
Go and ask a question, John. I know you're burning to ask a question.
So, I've actually got about 20 questions, because as you know, Brandon, we could talk all day on this. But in fact, we're already running nearly 7 minutes over. So maybe we'll take it offline, Brandon, as always. So thank you so much. Fantastic.
And I would like... I'm going to present the next speaker now. The next speaker comes from, well, I would say he's going to present a view from outside the traditional space field. He comes more from the cybersecurity domain of networks and the big wide world. He has over 30 years experience in IT security. And Andy, are you there?
Yes, I am.
We're just getting your slides on screen now. Hold on a second.
Fantastic. For some reason, I can't connect on the video, so trust me, that's who I am. But thank you very much for inviting me today. Brandon, thank you very much for a very informative set of slides and information you just shared with the team and panel. If we could go to the first slide, please, John. I actually wrote a paper, PKI and the Modern Enigma of Digital Certificates, for a magazine last year called Digital Forensics. And it was a whole paper on how we had evolved on the encryption and decryption side, which I know Brandon touched about, which is incredibly important. It all comes under PKI. And for those that are not familiar with PKI, PKI stands for Public Key Infrastructure. It was formulated with the American and UK governments to enable digital encryption and decryption through authentication of users and devices. Back in the 90s, it actually started back in the 60s and 70s after the Enigma machine from the Second World War, etc. But I don't want to bore you with that. You'll see here that we've done some research papers for the US on a number of areas, and we actually presented a white paper for the Senate Intelligence Committee post the SolarWinds breach. I'm going to make some assumptions here that not everyone is fully versed in cyber and cybersecurity, so I'm going to try and keep it light. But if you don't know and you have not heard about the SolarWinds breach, it happened in December last year. It's affected 18,000 companies, including the US government, because like a house that was built of a pack of cards, when one came out, they all fell over. I've written a book on that, Stuxnet to Sunburst, and those that are not familiar with Stuxnet, it was the first ever digital weapon that was used to attack the nuclear program in Iran. And there's a lot of contentious issues around that, and that was 20 years ago. So if we could go to the third slide, that would be really helpful, please. All right, so look, if we understand that SolarWinds was the world's largest single ever breach, and it was, you know, there's a lot of assumptions made by various threat actors and state nation-backed organizations. But the one thing I want to point out to you, because from this half an hour that I've got, I want people to be educated in a simple way so they can understand what we're doing, because everyone's online every day. But you'll see this little picture here, and underneath you've got SolarWinds, the lessons of being not secure. If you see in that little top left-hand corner on the address bar, you'll see not secure there. Can you all see that, hopefully? And what that actually means, thank you very much, we should bring that. And what that actually means is that this website cannot be authenticated. You'll see I've actually compiled my email address and password in there. I've not gone any further, but that is cannon fodder to a cyber criminal. And what do I mean by that? Cyber criminals are using open source intelligence, OSINT, which again Brendan mentioned earlier, to understand as part of their reconnaissance which websites and which servers are not secure and enabling them to easily be infiltrated. There's organizations such as OWASP and CWE MITRE and others that will give you all of the ins and outs. You can actually be trained on how to infiltrate websites, and it's been used for many, many years, originally post 9/11 by the agencies to digitally eavesdrop and identify terrorists, but more latterly by cyber criminals to gain access for cyber infiltration or for ransomware or one of the other things that we're seeing constantly. So if we can go to the next slide, it's for me, it's very easy. Now this is public domain information again, so please don't panic. You know, this is SolarWinds' current position. I get asked this on a regular basis. What does F actually stand for? We say it's for fail, but you could call it anything else you want beginning with F. And 10 out of 100, 0 out of 100 is the absolute worst. So what this is actually confirming to us is that SolarWinds' executive team have not addressed the root cause. And the paper that I wrote for the Senate Intelligence Committee, and indeed the book, my first book on Net to Sunburst, which was the code name for the SolarWinds breach, actually proved, I think we were one of the first people in the world, but we actually proved that a subdomain, i.e. a website that was a legacy website that was sitting there unmanaged, uncontrolled, was actually infiltrated, as I explained and showed in the slide before. A not secure website was infiltrated and taken over. We call it domain hijacking and domain takeover. And by doing that, the perpetrators stood up a new website called avsvmcleod.com. You can look it up. You won't find anything there now, but at the time, they managed to get full domain administration access. What does that mean to the space industry? They took over complete control, C2, which you'll be familiar with. If we could go to the next slide, please, John. Okay, so this is how we make up the metrics that we actually utilize to look at why a website or web server are not secure. And you'll be familiar with websites that you go on to that have a little padlock, or they actually have that not secure. And hopefully everyone's nodding their head and identifying with that issue. One of the biggest challenges that Google faced in 2014, that most websites and the intervention of more cyber attacks, the exponential increase in attacks, was they actually introduced HTTPS, and the S stood for security. And in 2018, that went live. So anyone that actually relied on broken protocols and ciphers that were not up to scratch to HTTPS would actually be displayed as a not secure website. And sadly, we find these all the time. Luxury brands, even governments, which I won't go into at this stage. But you can see there's a number of metrics there. And in this particular one, I want to draw your attention to a couple. If you look at redirection, the second one down, the first one, HSTS, is really important, but the second one down, invalid certificate chain encountered during redirection. What does that actually mean? This is relevant to the website that we just looked at above, which was the not secure one. What it actually means is the certificate chain that authenticates the domain owner with this website is intact. This one is not. Brendan touched on the term we're very familiar with, waterhole attacks, whereby somebody can either take over the domain, or just literally loiter, collecting plain text data. It's a really important key, and I'll touch on it just in a minute, where they can take the data, they can encrypt it so you can no longer use it, and then hold you to ransom. You might, as a group, be posing the question, how can a JP Morgan or other companies that spend hundreds of millions of dollars in cybersecurity still not be secure? How can SolarWinds, as a world-leading cybersecurity company, not be secure and leave these things to chance and get breached? It's very questionable, and it'd be a very good question to pose. The bottom line is they are not looking at the front doors. We call it the digital front doors. Consequently, the threat actors are looking at these all day, every day, and they are collating them. It's why you are reading day after day of cyber attacks and ransomware attacks. It's not because companies aren't doing a pretty good job internally, but when the threat actors on the inside, i.e. sitting on the server, they can take over full control. They can do phishing email attacks from inside. So it's no longer an external email, it's an internal email. This is what's going on today. So the second one, redirection, certificate chain encountered during redirection, is incredibly critical. You can look down there. The sub-resource integrity is third party. For people that don't fully understand website development, etc., websites contain content from multiple sources. If those multiple sources aren't checked for security, they could be coded in certain code that would actually relegate a website's security posture. We did this for the government last year. I won't name the government because it's too close to your home for a lot of people here, but they actually had a breach last year, and when we looked at it, the flag that they were using was written in HTTP code, making the whole website insecure, and it relegated the website. That's been addressed now. So there's a lot of things there. The key point to this is that we use these methods, these open source intelligence methods, to provide actionable intelligence to strongly bolster a company's security posture at the front door. Cyber criminals use the same capability, not ours, but the same capability to identify access points to infiltrate. This is a really key issue. So we're in a race. We want to try and prevent infiltration or controlled infiltration by the company. The cyber criminals don't care. They just want to get access. Once they get access, they can move laterally and do whatever they want to do, even to the position of SolarWinds, where they issue certificates and upgrades with malicious code on, affecting 18,000 customers. Next slide, please, John. So, who's this guy, Andy Jenkinson from Windsor, who lives near the Queen Castle? Forget who I am. This is HackerOne's report of 2021, and it's taken directly with permission from them. And you'll see that it says here 96% of hackers hack websites and web servers, which is up from 71% in 2020. You'll see the little bar graph along there. Nearly twice as many hackers hack websites as any other application. And we have some incredible technology internally, but it's not looking for people on the inside. Once they're already on the inside, they can get up to all sorts of mischief and attacks, typically unknowingly, for many, many months. The SolarWinds initial infiltration was in March 2020. It wasn't even detected for 9 months. Next slide, please. Okay, so as I say, and very kindly introduced, security within the space area is not something we've messed about with too much. It's not something we've delivered much. I've just got involved with a number of companies in Australia that are looking to launch their own space shuttles and things in the near future. And the next slide will quite alarm you, but this is the reason we're here. You may or may not know this, that NASA has 23,699 websites. The vast majority are legacy, and quite a majority are also not secure. If you take on board the previous slides we've touched on, not secure, there are two versions. Not secure means the certificate is invalid, it's misconfigured, or it's expired. Insecure means the website is misconfigured and has a number of issues that can all be attacked. Each one of those red crosses represents a number of attack vectors for cyber criminals who can buy the appropriate attacks and methods on the dark web very simply, very easily. The very next slide should make everyone alerted. Could I have the next slide, please? Now, this one should pop. We saw the F-rated SolarWinds, and I could show you 1,000. We've actually researched over 1,000 companies, including the Colonials, including JBS Foods, including the Casilla. All of these companies were maintaining suboptimal websites where the initial infiltration took place. Let me ask a question. If a nefarious actor is 3,000 miles away, how do you think they get access? It's digital access, and in the vast majority of cases, we've seen the slides, 96% of hackers are hacking websites. We've investigated 1,000 plus cyber attacks and ransomware attacks. In every single case, we have found suboptimal security, typically F-rated, across the board. For protection, because we've actually started talking to all of these companies, each one of those Fs represents a separate space entity within Australia. There's one there for NASA that we've redacted, and we've had conversations with NASA. They're fully aware of the challenge they have, which is really, really unfortunate, because you need an army of people just to try and look after these things, which is where we've come in and which we've developed. But the reality is, at the present time, if you read the little bit I've put on the right-hand side there, if you are F-rated on your website or your web server, it's like a cyber attacker walking into a Starbucks, gaining access and taking whatever plain text data they want, encrypting it and selling it back. The worst thing we see, and I could quote many companies, so I'll avoid doing so, the worst thing we see is even post-attack, when it's been proven, like the SolarWinds slide earlier, when it's been proven that the attack utilized insecure websites, gained access, they still have not remediated the issue and the root cause several months after. Now there's calls for that to be criminalized, but that's another discussion. And I think we've got a final slide. And this is, just for fun, really. The Hubble site, I know the Hubble spacecraft has had a number of challenges over the last several weeks. It's just coincidentally, maybe, got a very insecure website. Could the challenge be due to operational infiltration? Of course it can. Next slide, please. I'm very quick, very easy. It's like my racing times. If there's any questions, I'd be delighted to field them. But the bit that people are missing, and we're in discussions with the Department of Homeland Security and other governments around the world, and in particular in the Australia part of the world, the DOD, etc., we have evidenced this on many, many occasions, that people are not considering their website, their digital footprint. I leave you with this thought. If you had a 1963 Jaguar E-Type and you lived in a high crime risk area, would you leave that car with the keys in ignition and walk away for a year and expect in a year's time to come back and it be there? That's what's happening when people create websites. Today, I have shared some information with a group CISO of a global brand. I won't mention the brand, but a global brand you all know. They're in one of the top 10 global brands in the world. And I said, you may want to know this, your websites are totally open, as were SolarWinds when they were attacked. And he said, that's not our problem, we outsource our websites. You can outsource everything apart from responsibility and accountability. You must make sure your supply chains have security on their websites facing and connected to the internet. Otherwise, it will be a case of when. I hope that was informative for you. I've kept it short and sweet. I could talk about PKI for hours. I could talk about cyber attacks for hours, but I've tried to limit it. If I can be of any service to anybody and help you understand better, we have white papers, we have books, we have everything that's available. Is that okay?
Thank you very much, Andy. That was always a very thought-provoking discussion when you start presenting. I'm going to ask if there's any questions on the board. Any online, John? Stand by? No? I was just WebEx playing games.
Maybe I did a good job.
Maybe. Okay, I'm going to present. Thank you again, Andy, and I'll talk to you later on. Cheers. Interlude. I'd like to present Marco Langbroek, who is a consultant at Leiden Observatory on SSA. He's part of the PHOTOS project, providing deep space tracking capabilities for the Royal Netherlands Air Force. For the last 15 years, he's been an active member of an informal network of satellite trackers and specializes in tracking and classifying certain questionable satellites visually using various telescopes and photographic equipment. And are you ready, Marco? It's Friday afternoon. What do you expect, guys? Whose bright idea was to have a conference on a Friday? Yeah, it seems I'm missing something here, guys. Hopefully, the next symposium we'll all be here in presence and we can all actually go out for a proper beer on the beach. Ready now, hand you over. There you go, Marco. It's all yours now.
Okay, well, nothing to see here is the title I've given my presentation. The photograph that I show you here, I made this photograph in April of 2018, and what you are seeing here is the roof of my neighbor's house. The roof of my neighbor's house, and you see a satellite trail here, obviously an object in low Earth orbit. If you look in the public satellite catalog from SpaceTech, etc., nothing should be here. So there's nothing here, nothing to see, move on. Well, in reality, there obviously is something, and unfortunately, the clue has been given away. I wanted to pose the question whether anyone could guess what this object is, but I think most people already saw it in the next slide. It's not working. It's actually this object, the X-37B, the robotic space plane of the US Air Force, which is a classified object, meaning that the orbit of this object is not made public. Now, how do we know that this is actually the X-37B? I will tell you somewhat later during this lecture. Like was said in the introduction, I'm a member of a small informal group of basically amateur satellite observers, international group, very loosely organized around a mailing list, the CZL list. We have no central board, we have no director, we have no secretary, just a bunch of people cooperating on this mailing list. There's one person who voluntarily collects all the observations we do, does the main orbit calculations and puts them in a catalog that is available on the internet. Worldwide, there are maybe 15 observers cooperating, really active observers cooperating in this network. There's a much larger group of interested people, but really active observers are maybe 15 worldwide. Strong concentration in Europe at the moment. The core of our group is basically in the Netherlands and Britain, but we also have observers in Italy, Germany, the United States and Canada, for example. We observe with very simple equipment. Really, to do useful space tracking, you don't need big, expensive telescopes. And we basically observe from our backyard. And this image actually was taken last Wednesday and shows the place where I observed, the communal garden of the building I live. And here are two of the attendees of this very symposium who visited me for a demonstration of my technique.
That's fantastic.
Thank you. Well, this is the kind of equipment I use. Basically two techniques, photographic, that is how I started. And since a few years also with very sensitive video techniques. The video camera is a very sensitive surveillance camera, which you normally put outside your door to keep an eye on your property. It's very sensitive, able to film at night. I use a number of photographic lenses with that camera, and basically for a part the same lenses I also use with a quite normal mirror reflex, digital mirror reflex camera, a Canon EOS type. So this is all basically very available and not too expensive equipment. The video camera works in, it's a analog camera, and it works in cooperation with a GPS time inserter, which taps a very accurate time signal from GPS satellites and imprints each video frame with a very exact time, basically with a millisecond accuracy. Well, what we do, like I said, we do observations, and we use these observations to maintain a catalog of classified orbits, so of objects that are not in a public catalog. And at the moment, we have some 200 of these objects in our catalog. And in fact, a few years ago it was even as much as 400 objects. And the reason it's less now is, amongst others, because the United States has been declassifying a number of these objects. Most of these objects that are not in the public catalog are American, but not all of them. There are also some German military payloads, Italian, French payloads. There are also Japanese that are also in this catalog. Well, in my case, we use very different techniques. Some old school people in our network still use binoculars and a stopwatch. And actually time when these satellites pass certain stars, and they are able to actually get very accurate results with that method, surprisingly enough. A number of other observers like me use these more sophisticated methods using video and photography. And after I have obtained images showing a satellite, basically I use software to do real astrometry on these images. So you use the stars in the background to create an astrometric grid. And from that you can very accurately determine the positions of the satellite on these images, and from that the positions in the sky. And you can do that for, I have software to do that for photographic images. And for video images, I also use quite even better software that is almost fully automatic. And this was originally developed to get astrometry on video imagery from close approaching near Earth asteroids, but it's very suitable to do this kind of work with satellites as well. While the older software that I use for my photography was originally meant to measure images with meteors on them. It's going very slowly, I note. It's not going on real speed. This is what such a video looks like, only that it's very slow now. Normally it's on normal speed. And you see two objects passing by here. And these are two of these classified objects. You won't find them, you'll find them mentioned in the catalog of SpaceTech, but not with orbital elements. You find them mentioned with their identification number. All these classified objects, when they are American, have a number consisting of the USA and followed by a number. These are, in this case, we know that these are naval ocean surveillance satellites. They always work in pairs, very closely together. The interesting thing is that in this space catalog, you find the first payload you find designated as payload. The second object is always designated as debris. but it's very strange debris because it's maneuvering debris that closely follows the other one. And we know that these satellites are used to actually geolocate shipping on sea based on the radio signals and radar signals from that shipping. And by an interferometry approach, they can then geolocate those ships. This is another example from how I use photography, and we see a number of objects. In this case, we see two classified objects. Here is one ESA 267, which was a very interesting one because a month after it was launched, it made a very close approach to the International Space Station, to within 6 kilometers. And it's still not quite clear to us what was going on there. There's an object in a high orbit which is classified space debris, because that also exists. It's a rocket stage from launch to geostationary altitude, and these rocket stages are also kept classified. And then there are two unclassified objects that are basically space debris, old rocket stages. If we go a little bit higher in altitude, we go to high elliptical orbits and medium Earth orbits. And this is again an example. This was launched last year in an orbit that previously had not been used by military satellites at 11,000 kilometers altitude. And you also see two unclassified objects here, a old Chinese rocket booster and a GLONASS navigation satellite. And then going even further, we go to geostationary altitude. And again, this is all done from Leiden Center, so not the best place to observe, but you know it's very possible. For me, the geostationary objects are quite low below, quite low in the sky. And you see each arrow is pointing to a dot, and all these dots are commercial geostationary satellites. But this one, PEN, is a classified one and a very mysterious one, and I will give a case study of how we found out what this very mysterious payload is actually doing. Well, all this work of finding these objects, cataloging them, and trying to find out what they are, actually in many cases already starts before launch. Because when an object is launched, parts of airspace and parts of the ocean have to be closed because, for example, the rocket stage is placed down there. You don't want to have that happen on a ship or something like that. So, and that's public information, must be public information. But it's for us very interesting because the positions of these closed areas actually define a line, which is the direction of launch, and from that we can calculate the orbital inclination that is being launched in and the orbital plane that's being launched in. And based on the type of rocket that is used, but also because we sometimes recognize particular inclinations as belonging to a particular satellite program, we often can also make an educated guess about the orbital altitude. So you even before launch, you already have a rough orbit along which you can search. And what we next do is, when the launch happens, is that we keep an eye on that orbital plane that we defined, and we look for objects that we cannot identify in that orbital plane. And in many cases, we quite quickly find them. We often have had cases that were on the second or even the first revolution, we already picked up the payloads. And next we keep following them until we have a good orbit, and of course that orbit has to be updated again and again, also because these things maneuver periodically, etc. So we keep following these objects for years and years. Oh, that's the wrong one. Yep. So we determine these objects, but and determine orbits, but that's not the only thing we do. In order to characterize these objects, we also look at other aspects. We look at the type of orbit, we look at orbital behavior. Are they repositioned at various intervals or not? We also look at photometric behavior, so brightness behavior of the payloads, for example. And all these things gives us clues as to what these things might do. So in our network, we have observers who observe and create the data for these orbit determinations, but we have also people like myself, for example, who also like to do this kind of analysis to further grasp what these objects are. And the orbit type often already gives you a good clue about the function. For example, when you see objects in low orbit, in a polar orbit that is sun-synchronous, meaning that it basically follows the precession of the sun, which basically means that the satellite passes over a given area around the same time every day. That already tells you that it's very likely to be a remote sensing satellite. For example, a satellite is taking detailed images of the Earth's surface. America over the last decade has also been launching a number of classified satellites that they launched in retrograde orbit, so an orbit that goes against the rotation of the Earth. Normally you would not do that because it takes more energy than to launch in a prograde orbit. There are only two reasons why you could do this. One is because you have a range safety issue, which is, for example, the reason why Israel launches into retrograde orbits, because if they would go into prograde, they have to launch over the neighboring Arabian countries, and that's difficult. But there's no reason why America would do this, because they do have access to prograde launch trajectories. And one other reason why you should do this is when your payload is actually a synthetic aperture radar satellite. Because then, I'm not a radar expert, but I've been told that because of the added velocity factors of the Earth rotation and the satellite going the other direction, it actually helps you in getting more information from your synthetic aperture signal. So from this class of US satellites, we are quite certain that they are synthetic aperture radar objects belonging to a particular project that we know that exists, which has the codename Topaz and was previously known as the Future Imagery Architecture. Apart from looking at the types of orbits, of course, many of these satellite programs are basically employing multiple satellites that form a constellation. And that constellation, when it forms, is often quite recognizable. And from launch times and launch planes that is being launched in, we often can connect launches to one of these programs because of the type of orbit they are launched in as part of a constellation. Photometric behavior also is an important clue, especially in the very early stages of such a classified launch, to determine, for example, which object is the payload and which object might be a rocket stage. And there's some, I have an example here. This is actually the rocket stage from the launch that I earlier showed you, that is at 11,000 kilometers in a photograph. And in this case, we were tracking two objects from this launch, one that is stable in brightness and maneuvers every now and then, and one that is clearly variable in brightness and does not maneuver. So it's a quick and logical conclusion that this is actually the Centaur upper stage of that launch. And especially with video, which you have a very good time control, you can get very nice brightness curves showing the variation of this object. In this case, this is this rocket stage, and this is shortly after launch, and you see that it varies in brightness with a peak-to-peak period of around 138 seconds. And this kind of very slow brightness variation pointing to a tumble is very characteristic of rocket stages. And in fact, this is a similar curve I made a month later, and then the period of this tumble had already changed from 138 to 114 seconds, which is also very characteristic of these empty rocket stages, that they show this slow tumble that with a periodicity that changes over time. So if you see this pattern, it's very likely to be a rocket stage. Still, you have to be, and it's a pity that the video is not working that nice, because now you won't see it. If this would be playing well, you would see that this is an object that's very rapidly flashing, like a stroboscope. It's 5 flashes per second. But this is not a rotating rocket stage actually. This is a payload, and in this case the flashing is part of the operational process of this payload. We know that because it's a very regular pattern that keeps being the same for many years. It has a sister ship, USA 31, that has exactly the same pattern, again with 5 flashes per second. And in this case, it is clear that it's an operational spacecraft, basically, and that it's something else. And what it probably is in this case is that it might be spin stabilization. Another option is that it might have a rotating element on it, but that's much less likely. So brightness variation gives you information. It gives you information whether an object is tumbling or not. It might give you information over stabilization characteristics. With single flares, it might give you information about shapes. The most interesting cases are where there's an object that for a long period has been stable and then suddenly starts to show brightness variations. If that happens, you know there's something happening. And basically it's either end of life of this object or some malfunction. Well, like I told you earlier, this is the slide from the start. How do we know that this is the X-37B? Well, in this case, it's largely based on the orbital behavior. In this case, unlike some previous X-37B missions, we did not pick it up directly after launch for various reasons, only much later. But we could reconstruct that the orbital plane was over the launch site at the moment of launch, which already is a strong suggestion that it is connected to that launch. All these X-37B missions have shown a very characteristic, very low orbital altitude, below that of the ISS, and very frequent changes in orbital altitude. This is something that a normal satellite does not do, but these X-37Bs clearly do this, and it's probably related to testing experimental technology under various altitude regimes. So we noted this pattern, and from this we are quite certain that this object indeed is one of these X-37B missions. And indeed, when the this particular X-37B mission landed again, after that date we didn't see this object again. So it's very clear that this was this space plane. For time reasons, I'm going to skip this and go directly to the case study. As an example of how we slide this, this kind of detective work involved, this is one of the most intriguing cases we have had. A launch in 2009 that was very mysterious from the start. It's a launch to geostationary altitude. Normally, even with classified launches, it is known which agency is responsible for the payload. It's announced that it's, for example, a payload for the National Reconnaissance Office or a payload for the US Air Force. In this case, they didn't disclose anything, niente, nada. The only thing we knew was from a launch patch that appeared that the name was PAN, and the persistent rumor is, and is quite likely correct, that PAN actually stands for Pick Any Name. What was also known is that this was the result of a very quick program with the mission basically commissioned within the issue being brought out, and the launch being actually, we know that Lockheed built it, that they obtained a contract in 2006, and they already launched in 2009. So a very quick scheme, and that's completely built with off-the-shelf components. And Lockheed did announce that they used a commercial satellite bus, the A2200, for this satellite. And after we were starting to follow it, initial ideas was, because it was also mysterious, that it might be a dedicated communication satellite, for example, for the CIA. That was bolstered in the start because one of our observers noted it sending radio signals at a frequency that was previously used by communication satellites. We now know that it's not a communication satellite because after we had been following it for a while, we noted a very unusual pattern. What you see here is the longitude over which of the sub-satellite point over which it is placed. This axis is time, going from 2009 up to 2016, and over the course of 5 years, it was very frequently relocated in longitude. Now, this is something that you normally do not do because it takes a lot of fuel. So normally you put it at a certain longitude, keep it there, and do not move around as much because that basically the lifespan of your satellite will be much shorter if you maneuver this many times. So this was an odd, very odd pattern when we noted this. You see, it did so for about 5 years, and then it became more stable until very recently. This is an updated graph. In May this year, it started to move again, and I actually think that in this case, it is because it's end of life of this satellite. These frequently relocations were not two random points. We noted that each time it was relocated, it was put very closely to a commercial satellite for satellite telephony. Again and again, and we also started to note at a certain point that these satellites had something in common, and that is that their spot beams served particular areas, notably Pakistan and Afghanistan, and the area around Yemen. Along with this satellite becoming operational, there was a strong rise in the amount of drone strikes in these areas. These are, of course, the classical areas where the war on terror is being fought. And was being fought, and so we started to develop the idea in our group that this satellite might be connected to this drone war. And the idea was that it was positioned so close to these satellites and able to intercept satellite telephony from this area, and that these signals might help to geolocate targets for this drone war. Well, at that point we got very uneasy, and I must say that up to this point we had kept all this discussion in a quite private circle. We did not discuss this on the public mailing list, but this was private communications between a few observers, including me, and a few analysts. And when we started to develop these ideas, we decided to not go public with this because we didn't want to help bad guys, basically, but we also were concerned about possible repercussions for ourselves. We didn't want to end up on no-fly list or being whisked off in some black helicopter to Guantanamo. So we decided for a long time to stay quiet about this. Around the same time, I realized that there was another satellite launched in the same year that was basically doing something similar. It's of a different character than PAN. It's actually, we know that this is part of an already existing program, which has the codename Advanced Orion, which we designate as mentors. These are very recognizable because they are very bright, and they are very bright quite likely because they are signals intelligence satellites with a huge unfoldable antenna is rumored to be 100 meters wide, and that is why it's so bright. It's much brighter than other geostationary satellites. And they launched one the same year, and unlike previous satellites of this type, this was placed very close to a commercial satellite, Thuraya, which at that time was the leader of the field for satellite communications in Northern Africa. So was this coincidence or not? Well, that Thuraya satellite is actually, it's geosynchronous but not geostationary. It has a clear inclination of a few degrees, so each day it's making a small analemma, a wobble along the perpendicular to the equator. And Mentor 4, which was placed next to it, is very carefully following the same wobble. So no, this is no coincidence, and we were later proven right with this. Because in 2016 something happened. The Intercept, a news website founded by Glenn Greenwald, a well-known investigative journalist, was publishing a whole series of articles based on the Snowden files, the leaked documents by Edward Snowden. And some of these documents actually pertain to this classified satellite program. And at a certain point in 2016, they published a large article about the drone war and the role of satellites in this drone war and the role of 2 satellite control stations, Pine Gap Facility in Australia and Menwith Hill in Great Britain, in this drone war. And in these documents is a lot of information about 2 particular satellites that are used in this drone war. And from the information in these documents, it's very clear that it is talking about the very same satellites that I've been showing you. There are even some pictures in some of these documents, and like I told you, we know that PEN was based on a commercial satellite bus from Lockheed, and this is basically what we are seeing here. This is indeed the shape of that particular satellite bus. There was this rumor that these Mentors, these very bright satellites, have this huge unfoldable umbrella-like type antenna. This is what you are seeing here. So this and along with the proposed launch dates, because most of these documents date from just before the actual launch of these objects, made very clear that this must be the same objects. And there's interesting information in this that actually confirms everything that we were already developing in ideas about these satellites. For example, considering the satellite that must be PEN, or as it's called in these documents, Nemesis 1, very ominous name. It said that these satellites function to target commercial satellite uplinks not normally accessible via conventional means. So indeed, these satellites are placed next to these communication satellites to tap these satellite uplinks. About the other one, the very big one, some interesting information as well. It's talking about that. Well, the satellite is placed near Australia first in a checkout position, and it's checkout for a certain while, and then they let it drift towards its operational position. And the documents say that during that drift, it was cataloging transmitters in China. But then when it arrived some 45 days later, which matches our observations at the destination, it picked up new primary missions, which was twofold, because a normal Mentor mission is basically this Afghanistan-Pakistan exfiltration, listening with big radio air to radio communication from a wide area. But in this case, it also mentions that it had another mission as well, and that is Thuraya collection. And this is the one that was placed very close to that Thuraya satellite. So this confirms that my idea that this satellite is part of the same program and doing the same thing with Thuraya is basically correct. The interesting thing is that this particular satellite, Mentor, had a delay in its launch of a few years. The interesting point is that that delay was introduced around the time of the conception of the PEN project. And my idea that I cannot definitely prove, but that I have, is that they were developing very rapidly this PEN project. And someone realized that if we take that same kind of equipment and put it on a satellite that we are already about to launch, we can have a second satellite doing basically the same. And I think that might be why there was a delay in the launch of this satellite, because they had to adapt the satellite to also facilitate this new mission. It's very interesting that both satellites are named in the same document, so it's clearly that they are regarded as part of the same program. Some of the other things in these documents are actually borne out by our observations as well. Here you can see, for example, this is this drift phase initially, and then it arrives at 44 east, and then it stabilizes next to Thuraya after that moment. The documents mention that before Mentor 4 there was another satellite monitoring Thuraya, which is interesting because there was no other satellite that close to Thuraya before. So that surprised me. It suggests that this monitoring of Thuraya has changed. That with Mentor 4, who is dedicatedly scanning Thuraya, and with the PEN, who is basically moving in, working in a roving role where it visits several satellites, that they were doing something new that is not being done in these previous monitoring events. We nevertheless could identify this earlier satellite. It was another Mentor satellite that was not that close to Thuraya, in the general vicinity, but not as close. And you actually see that before Mentor 4 arrived at this position, Mentor 2 was at 44 East. Then Mentor 4 arrives, and after a quick brief checkout period, it takes over the mission. And the satellite that was there, Mentor 2, then starts to drift and moves to a new position in the Western Hemisphere, which tallies with the documents which say that this satellite next was used to target Latin America. So our observations very nicely fit what is in these documents, which not only shows that our ideas about this satellite are basically correct, but incidentally also shows that the Snowden files are real. They are not fake, they're real. So that was quite a detective story for us to unravel, and I've actually written when after the paper in the Intercept appeared. I thought there's no real reason for us to keep quiet about this, so I've written a quite elaborate paper explaining this and some other dimensions, like my worry that this same kind of technology might be used for industrial espionage, for example, in a paper in the Space Review, which you can find online. It's free to read. And you find a link to that particular paper on my blog. It's in the sidebar of the blog is a link to a number of external papers I've written, and it's there as well. And on the blog itself, if you visit that, there are various presentations of my observations, but also analysis of various kinds of satellites. So if it interests you, you can look at it. And I had a small parting gift, but the video is working that badly that I'm not sure. This was filmed last Wednesday, and this is the Proton rocket stage from the Nauka launch. And somewhat later in the sequence, you can see that it's accompanied by 3 debris pieces in front of it, fainter debris pieces. It's a bit unfortunate that the video is this slow, but so I'm not sure whether you actually see the debris pieces as well. That concludes my presentation. Are there any questions? I see. Mm-hmm.
Can you repeat it for the virtual audience, the question?
Okay, I will repeat the question. The question was whether, well, I noted that we were worried about possible repercussions for ourselves if we would go public. And the question was whether we noticed anything about that. No, so far not. I must admit I've not been to the USA for a very long time, so I don't know what will happen when I will travel there. But I don't think it is a problem because it was in the public domain already through this big article in the Intercept, for example. Our activities, not just on this satellite, but on the other satellites where we do publish things, do attract some attention. I know of at least one report by an American defense contractor which is not so nice about us. It's a bit derogatory about us. My weblog in the past years has been visited by, for example, IPs belonging to the NSA and the CIA. And in one case, even IP belonging to the executive office of the US president. That was around the time that the Japanese spy satellite malfunctioned and was coming down, and that I'd written something about that and created some media attention. And apparently somebody in the US president office thought that might be interesting maybe to brief their president or whatever, but anyway, they visited. So yeah, we do get some attention, but nothing nothing so far that really harmed us or whatever. And we are trying to be like there was a reason that we did not go public with this particular case, for example. So we are trying to be very conscious of what we do make public and what we do not make public. And our main goal is to to create this catalog for various reasons. And one reason is that, frankly, it's ridiculous that these objects are classified, because many of these objects you can see even from Leiden Center with the naked eye when they pass. So these things really are not that invisible. And in fact, I think there are some very unrealistic ideas about secrecy in some circles of the, notably the American defense world. I've seen articles about some satellite systems which boast about how difficult to detect they would be, while in reality I can see them with the naked eye from Leiden. And that's dangerous, because as a military, if your military strategies are based on a mistaken notion that your enemy doesn't know where your space assets were, that can mean that your whole military campaign can go awry. So the secrecy notion, when it's not really secret, it's dangerous. So this is one of the reasons why we publish these orbits, to show that it's not realistic secrecy, for example. Another reason why I do this is I come from a very different background. I'm an archaeologist, actually. It's my original background. And this is a kind of space archaeology, because in these secret space programs, this is where the real innovation takes place. The Hubble Space Telescope is based on a much earlier space satellite, for example. So there's a lot happening in this classified world, which is actually on the forefront of the developments, in many ways, of developments in space, but it's all hidden away. And for me, this is also a way to make available for history, basically, these things that are happening in space that we're not supposed to see, but still, on the technological front, are actually very important steps in space. Okay.
Well, thanks again to Marco. He's the CEO and founder of SKUDO. Just to introduce Stefano, I mean, I think Jose introduced him before, but Stefano Alberico, he's the founder and CEO of SKUDO, an Estonian startup. And Stefano has 25 years experience in the telecoms area. So Stefano is just going to walk us through some of the activities he's been doing and what his company does. And I think you'll find it very interesting. I found it very interesting the other week when we did the final presentation in ESA. So yeah, apologies for this, everybody, especially to Stefano, who spent so much time preparing the video. But yeah, I think you'll find it enjoyable.
The video will be online.
The video, I think we can make available. I'm looking at Peter.
Yes.
I think so. Okay, over to you, Stefano. Thank you.
Thank you very much, John, and sorry everyone again. And so I can walk you through my presentation, that's no problem, but unfortunately I will not be able to give you a demo again in the middle of the forest. I don't have the equipment with me. And okay, now I can see I'm watching the presentation in a small mobile, so now it's fine. Again, presentation has been done. You can just move to the next slide. I'll give you I will walk you through basically a little bit the technology we are working as a company, and then a little bit the details, the activity we had with the ESA, with the agency. So when we started a few years back, the first main product we built has been basically a hardware security module developed entirely in Verilog within a single FPGA chip. So our idea was exactly to pack all the crypto functionalities and without using any third-party software library. So we own and developed all the crypto function ourselves, and that also means we can port our HSM on any basically FPGA chip. We don't have any brand lock-in. But the very interesting part in this, which I'm very, very passionate about, is that we strongly believe as a European company to build, this has been all built and designed in Europe, and we believe especially for, let's say, cybersecurity application in Europe, we should use European-made technology. So this has been one of our driving force behind this. And most importantly also is that since we use FPGA, so our HSM is entirely verifiable by third party. So if today you buy, let's say, an encryption chip, an HSM from any brand, in principle, you get an ASIC chip and you just have to blindly trust that it does what it's supposed to do, but the factor is that you cannot verify if there is some, let's say, hidden functionality. So we want actually instead to be completely transparent, and hence we can have our HSM verified by any third party. Next slide, please. So if you just, let's say pop the hood, for those familiar with an FPGA, of course, it's, let's say, nothing new. So inside the chip, of course, you have all the different kind of functionalities. And the beauty in this approach, of course, is that we can flexibly change the different soft cores. So in this case, we might have some symmetric encryption, different algorithm has been implemented. We will see in the next one a bit more in details which one. But this approach, for example, would allow us to be already ready for, let's say, PQC, post-quantum cryptography, because we can, and we will develop certain new soft cores so that in case we can replace an algorithm with another and be ready with the same solution, be ready for the PQC. In the next slide, please, we should see, if I remember, a list. Yeah, that's just for, let's say, the one are more interested in technicalities. You can see the list of all the soft core that we developed in Verilog. So we have the typical AES and GCM for symmetric encryption and authentication, which is widely used also by the agency, and which are the one we use also for our activity. And interesting, of course, is also the true random number generator. So we use the Figaro configuration, is a Fibonacci-Galois ring oscillator. And there is plenty of documentation, of course, about how good is the entropy with such solution. But anyway, this is what we build, and we have done certain tests, and it looks actually pretty good. And that's basically the element we use also for any basically key generation. So we resort to this DRNG inside our chip. Next slide, please. And after the chip, what we have done is we start to build, of course, some, let's say, basic solutions, some PCB where we mount the chip, because of course the chip itself is, let's say, unusable if you not provide some interfaces. So in this very small PCB, we have this FPGA. In this version is a 17 millimeter side, but our HSM actually fit entirely the smallest available chip. This is an Altera Max 10. And there is also one version which is 4 millimeter per side. So we can fit basically the entire HSM inside a single FPGA of 4 millimeter if we want. But for our case, at the moment, we are using this a bit bigger version. And it clocked at 100 megahertz, and we have different electrical interface like SPI, UART, I2C, and we're working also on the gigabit, so the RMII interface, because the chip per se, actually, it's pretty fast. So we have a couple of soft core for symmetric encryption. So one which is very, very compact, and it goes up to, I think if I'm not mistaken, I remember 175 megabit per second encryption speed. And then we have another soft core which is a little bit bigger, but it goes at 1.4 gigabit per second encryption speeds. So for that reason, of course, we have to be ready also to have a gigabit interface. And the one basically on the right side is the one we have been using now for the ESA activity. So it's a model which is slightly bigger than the smallest. So it has actually 16,000 logical elements. And we have been using this version for also the demo that today you are not going to see, but I will walk you through verbally. Next slide, please. So for the hash is the name of the activity we were running with for the agency. We started last summer, and we just ended a few weeks back. So we had the final report that John was mentioning. And overall was we started with an analysis of the HAPS market. So the idea was to analyze the high altitude pseudo satellite market and try to understand which kind of product, of course, with related to cybersecurity and encryption, which kind of product they were looking for. And then we made quite interesting, I would say, analysis of one of the protocol, the CCSDS SDLS protocol, and we end up actually modifying, building two extended procedure and implementing them that would basically allow the SDLS protocol. For those that don't remember, actually SDLS works just with symmetric encryption, and there is no even actually very strong authentication. And so we added this extended procedure, basically adding the capability of using a standard PKI. The fellow before he was talking a lot about the public key infrastructure, so that's exactly what we implemented in this activity. And we allow basically through the STLS to use a PKI, to use a certificate, and to use asymmetric cryptography. And next slide, please. So the first was a bit of the market analysis, and we talked with a few companies. There is a list there. So Thales, Alenia, Airbus, and various others. And we started, unfortunately, it was summertime last year, so we didn't got too many, let's say, also answer, most probably because people were whether busy or on vacation. But from some of them, we got also a questionnaire, and we got some answer. And so we're collecting a little bit of feedback. If we go to the next slide. So some of the aspects that we got is that this kind of company, at least for the hubs market, they are looking really for off-the-shelf component, and they insisted very much in having some standards, for example, related to encryption that would be adopted. So they're all were basically asking for having a standard implementation of some security. So the STLS appears to be also definitely a viable, not the only one, but definitely a viable solution. And that's why now with the next slides, please, with the activity that we started. So we, as I mentioned before, we tackled the problem of improving the security of the STLS. And as you know, most of you I'm sure know, in some the mission that you want to use this STLS and you want to use some encryption. So what you do is that you generate a bunch of keys, symmetric keys on the ground. You upload this key, you inject the keys to the satellite before the launch with a very, let's say, secure mechanism and surveilled situation, and then you upload this key and then you launch the satellite. And once the satellite is in orbit, then through the STLS protocol, you can actually switch through the different keys. So you consume the keys, and the operator on the ground decide this factor, and then you go on, let's say, for the entire life of the mission. Of course, this has a lot of problems. One of the very evident is that if you compromise your keys on the ground, basically you compromise the entire mission. There is no way to securely rekeying, let's say, this satellite. So, and the second one, very important, is there is actually no authentication at all. And most importantly is the satellite, so the endpoints doesn't have any mean to authenticate the operator on the ground. And by this, I mean, there is a lack of basically public certificate, which would be the solution to implement also a strong authentication. So next slides, please. And that's exactly, like I mentioned, what we were we designed and we implemented. So we started to use a certificate and generating a certificate for the operator on the ground and a certificate for the satellite itself, and then using, again, typical PKI infrastructure, using some algorithm like elliptic curve Diffie-Hellman, so ECDH, and all this cryptography function running within our single FPGA. So we implemented this functionality through these two extended procedure. And so using, again, STLS, we were then able to generate identity, verify identity, so digital certificate, establish a secure channel, and at that stage we were able to do authentication bidirectional. So for the first time, let's say, with this approach, a satellite itself can authenticate the operator on the ground and vice versa. And then we were able to do, for example, over-the-air rekeying, so the author function in a very secure environment. Next slides, please. The way we implemented is, as you can imagine, this was actually, I would say, a small activity, lasted almost a year. So I would say we have done a few miracles. And since, of course, our focus was mostly on developing and working on the encryption part, then to test it, we had actually to build or to find a wireless link. So we had actually to build the entire wireless link. And the target of the activity was to go through a metro balloon, a strato balloon, to be launched at about 25 kilometers. So we would attach our payload to this balloon. And we picked basically an existing infrastructure which runs over a VHF link, so 144 megahertz dot 800. There is, so it's a ham band radio, and we use very famous and very old technology which runs about the packet radio modem. So it's a very slow 1200 baud packet radio modem that runs over VHF, this 144, and provides basically AX25 data frame. So all this technology, which is basically the green block on the left, we got it, let's say, existing. So we had anyway to integrate all the rest in this. So we ended up basically putting our TC, telecom and telemetry frame from the SDLS protocol on top of the AX25 frame. This is, of course, a bit unorthodox approach, but that's revealed to be pretty functional. So using existing radio packet modem, we managed to build this bidirectional link. Next slide, please. And this is just a little bit more in detail about the extended procedure that we build. It's on top right, these two green blocks. So they represent the functionality that we build for implementing the PKI functionality and securing the channel. And at the same time, of course, we had to implement some functionality from the basic SDLS. And one thing we didn't know at the beginning, actually, is there is no reference implementation of the SDLS. So we had to build ourselves whatever we needed. And next slide, please. I'll try to see if it's... yeah, so this is basically the real picture of real hardware we have been using. On the left side, the station 1 basically is the ground station. And on the right side, the station 2 is the balloon. And the same kind of setup we had on both sides. So the onboard computer, let's call it like this, is just a Raspberry Pi. It's connected to our chip, which, if I'm not mistaken, should be the label number 3. So both ends rely on the HSM on that chip. So every crypto functionality, every key generation, every certificate is generated, stored, verified within the chip on both ends. And then we just use this packet radio modem, which just go through a normal radio, 144 megahertz radio, through a sound blaster for the audio. We used AF-SK coding, so the audio frequency shift keying, which goes back to tens of years ago, when probably people remember using the modem at home and listening those frequency shifting nice audio. So we had exactly the same, and unfortunately in the demo today you cannot hear, but otherwise during the demo we do. So I can actually walk you through now in this demo, I think in this slide. So the idea again was to launch the station 2 attached to a balloon and then start to have this communication. Now one problem is that this radio, of course, it's like a walkie-talkie, so it's not full duplex. And to basically solve this issue, we just implement a very simplistic time division multiplexes. So every minute, starting from counting the seconds at 00, we decided that we give 5 seconds to the balloon to send a message. And then after 5 seconds, we switch. So the ground would be able to talk for another 5 seconds and then switch back. So we have basically 12 slots every minute, and 6 of them are uplink and 6 of them are downlink. And this was just very simple. And we use, of course, both system, as you can see, as a GPS chip attached. And from the GPS, we got, let's say, clock. So both basically ends were in sync, thank you to the GPS. And so we were able to actually separate the uplink and downlink, and just based on the timing. And then using the solution we showed you before, again, every 5 seconds, basically the onboard computer on the ground or on the balloon were having this slot to be able to send the data. And in the balloon, we had some sensors, thermometer, pressure, humidity, plus, of course, a GPS that would send the coordinates. So when the demo starts, you will have actually, when you will see the video, you will have different windows, terminal windows connected to the Raspberry Pi. So we use Linux operating system, and so we would launch the different components that were listed before. And since, because of COVID, actually, 19, we were forced to cancel the physical launch of the balloon. although we were ready. And so we had to resort of doing this on the ground. And the only extra trick we had to implement, because of course being on the ground, the GPS would generate always the same altitude. Our mission software on the balloon were actually relying on the altitude to decide what to do. So a different height would decide to send certain information versus others. For example, when it was falling back, it was focusing on sending GPS information so that we would be able to track and recover. So since all the software was ready, listening to the altitude, then we decided to implement actually a dummy GPS. So we before the mission, so when we do the demo, we actually connect to the different sites, and in real time we collect the wind data, different altitude, wind intensity and direction. Then we calculate actually the trajectory of the balloon based on those data. And basically our software would then feed all the different points on the trajectory to the mission software. So the mission software basically would believe it's flying, but actually it's not, because we fake the GPS demo. Of course, we keep using the GPS real chip for the clock, but for the coordinates would be just a simulated trajectory. And so when the demo starts, basically you will also be able to graphically visualize this trajectory through the Google Earth plugin or software. So all this you will see in the demo. And then you will basically, when the balloon is flying, you are able to receive the telemetry data from the balloon sent every certain amount of seconds. And at the same time, you can actually follow in real time the trajectory and the path of the balloon, because we are using this network called APRS.fi from Finland, which is one open service and software which is collecting all the data that use exactly this 144.8 megahertz network and this technology that I mentioned to you. It's widely used actually for many ships, tracking of some ships and cargo, and also balloon, actually meteo balloon. So this is just a service, and since our data use exactly that format, then if you go on the home page, you are able basically in real time to track the balloon, which would also help us eventually to recover it. And then this is the telemetry data, and then the last bits, of course, we had also telecommand. So from our mission control on the ground, we are then able to to generate the identity on the ground, to perform the entire PKI deployment, to upload the public certificate, and then once the link is established, we can do a notar functionality. So we can upload in our demo, I think it's about 12 keys, and then we can start using the key for encryption or authentication, so we can consume the keys like normally you would do with the STLS. But of course, you are able also to upload new bunch of keys. And then we had a couple of commands that you can send, again, fully encrypted, end-to-end hardware encrypted, to ask the satellite to send you back some telemetry data. And one was about cutting the wire that connects the balloon to the payload, because being in Estonia, quite close to Russia, let's say we saw that there would be a risk that probably the balloon would go over the sea or over the border to Russia. So we had a button, basically the panic button, that pressing that button, we have a relay on the balloon that trigger a hot wire that burn the wire that connecting the payload to the balloon, and then the payload would fall back, and there is a parachute that would just deploy because of gravity. So that basically would be triggered by this telecommand. It's just a demonstration that you can send command basically to the balloon. And in the future, we plan to now extend over all this work we have done. We are actually already negotiating a new activity with the agency that is supposed to start around September, October. And the plan there is we will work with another company from Estonia called CGI Estonia. And we are bringing basically this technology to the OPSAT satellite. So we are basically uploading our HSM to the OPSAT. I think it's even probably in the next slide you can move. Might be the next couple of slides. There is something about this. And so we are going to upload our design. Yeah, I can talk about this. You can just move to the next one. I will just say, yeah, this is for the next activity. So we will upload our HSM to the FPGA, which is already on board of the OPSAT. and then we will implement basically our functionality as a sort of HSM as a service. Now on the OPSAT, there is this framework called NMF that allow to develop different application, software application. So our HSM functionality will be basically provided through these platform services to any application that runs on top of the NMF. In fact, the CGI is developing their own application for their own activity, and they're gonna use our crypto functionality from our HSM. And the second part of the activity will most probably we will connect, of course, and provide end-to-end encryption and deploy the PKI also to the ESOC in Darmstadt so that we can do a full, let's say, space demonstration and full test of this end-to-end encryption and PKI using also both the satellite and the ESOC on the ground. I guess that's quickly, it's about it. So there would have been a demo, but I think we can make it available, both even presentation and demo, just a demo as you want. There is a video and you can watch in there. I think that's conclude my presentation.
Thank you, Stefano. We will try our best to make the demos available online, or if it's not possible, people can ask us and we can try to share it via other means.
Absolutely. Or they can contact me by email.
Apologies on our side for the technology fail. But
no problem. No
Friday
problem.
afternoon gremlins.
Fine with me. So if there is any question, otherwise I'm here.
John, do we have any questions online? I've just got my glasses because I can't see.
Hello everyone, my name is Stefano Alberico. I'm the founder and CEO of SKUDO. We are based in Tallinn, Estonia. And today I'm going to introduce to you our company, our technology, and then we're going to present a little bit more in details our recent activity we completed with the European Space Agency, the results of that activity, and then will be a very nice live demonstration of part of the technology we developed in there. And at the end, of course, I will be available for a question and answer. So at SKUDO, we basically develop an entire hardware security module within a single FPGA chip. So we took all the crypto functionality developed in Verilog without the use of any third-party library, and then put inside its FPGA. So we are completely brand independent. So we are using at the moment Intel Altera, but we can move to any chip because, again, we don't use any library. And very important is that we developed and manufacture all this entirely in Europe, and we strongly believe that we are made in Europe, we are a European company, and we believe that European Union should use actually encryption and cybersecurity technology made in Europe. So this is very important for us. And one other advantage that we get by using FPGA is that we can get third-party independent review to verify our implementation. So someone else can actually verify, certify that there is no backdoor. And this is something you cannot have with the normal traditional HSM. So when you buy an HSM of a certain brand, you blindly trust that there is no undocumented functionality, so nothing else inside. There's no way to verify that part. And this is also important that we don't have actually any operating system, so we really do everything in Verilog, bare metal programming, and this is try to reduce as much as possible the surface attack. Now, if we pop the hood very simply, inside an FPGA, you find different building blocks. And one advantage that we have, and since we own all the source code, we can easily interchange or replace any functionality. We can, for example, integrate a new post-quantum cryptography and just replace a module with another one. So we would be ready for PQC as soon as we implement a new module. And that's really very, very handy. Now, there is a list of algorithms for those that are more interested. So you can see the traditional one, AES for symmetric, Camellia, and then we rely very much on elliptic curve for all the asymmetric cryptography. So the ECC and the Edward curve for the signature and verification. And then for the random number generator, we use a ring random number generator. Yes, we use a ring oscillator. So the Figaro configuration is Fibonacci-Galois ring oscillator, which is, of course, a very interesting module. And moving to the size, actually, you can see this is the real devices. So we design and actually manufacture also the PCD ourselves. Of course, is assembled in Europe, not in China. At the moment, we assemble this in Belgium, but we're planning to move the production here in Estonia, in our home country. And the PCB actually just contain the FPGA chip. And now in our current portfolio, we have two different versions, which are basically different from each other from the amount of logical element inside the FPGA. So on the left side, you have the smaller one, 8000 LE, and the right side a bit bigger with 16K LE. And again, all our entire HSM fit in this smallest one. So all the encryption algorithm that we mentioned for building the HSM fit this 8000 LE. We have also a couple of versions for the AES and the GCM. So we have one that using less resources, FPGA, with an encryption up to 175 megabit per second, or we have a bigger version which is much faster, goes up to 1.4 gigabit per second encryption speed. So you can imagine this is really, really very capable chip, and it's clocked only at 100 megahertz, 100 megahertz. And then you can interconnect and exchange data using SPI interface, so it's only 4 wires, or I2C or UART, and in the future we will have gigabit per second using the RMII interface, which we are developing and testing. Now, going in details about the HAPS project, so this hash contract we have with the ESA is we were exploring and talking with different HAPS companies, so high altitude pseudo satellite in Europe, try to collect some requirement and marketing needs to better understand how they would use cybersecurity. And then another very important aspect, the more technical one, is that we have been using the CCSDS STLS protocol, and we have been modifying this protocol, adding to extended procedure to be compatible with asymmetric cryptography, so with the PKI, with the digital certificate authority. So we modified this protocol. It typically works with the symmetric encryption. And the result of the marketing has been, actually this marketing research has been built talking with different companies in Europe, like Thales, Alenia, or Airbus, or CNES, and others. And we have been submitting some email and then questionnaires, and we collected the information and we compiled some result. And very important couple of aspects. One is that those companies for the HAPS application are looking to build, let's say, to get actually off-the-shelf components, so like radio module, ready-made, that would use, very importantly, some standards. So they all ask for standard, and definitely CCSDS seems to be a great candidate, and that's why we would like to continue to work also in this direction. And if you consider today, if you think today that traditional cybersecurity or traditional encryption you might have on a satellite is using, for example, SDLS, is based on pre-loading the pack of symmetric keys on the satellite, launching the satellite, and then through the protocol SDLS you can actually consume the different keys. So there is a bunch of keys and they are consumed one by one based on the operator needs. But this has numerous drawbacks, and of course one of them is that if you compromise the keys on the ground, then you are actually compromising the entire mission, because there is no way to securely upload any new key. And there is also no authentication method on, for example, the satellite itself and the operator operating and uploading those keys. So that was one of the main reasons why we decided to do our technical implementation. And again, so we took this SDLS protocol, we changed and added this extended procedure so that then we would be able to provide an end-to-end encryption, and most importantly a bidirectionally authentication, so that both satellite, balloon and ground station can be authenticated to each other using a very strong asymmetric cryptography based on digital certificate and digital signature. And for the demo purpose, all we had to do is we have this encryption technology we developed. Now we need a wireless data link to test it in actually HAPS conditions, so in a limit of the stratosphere. For doing this, actually, we took just existing technology, ready-made hardware and software, and we basically plugged and integrate our encryption part. So we resorted to the VHF radio, 144.8 megahertz, so it's a ham band. And on top of that, we found some technology called APRS.5, so this radio packet modem, which use AFSK coding. And so basically this left part, green part, provide to us a data frame, using this ready-made module. And so on top of that data frame, which is basically a payload, we put our SDLS TCTM data frame. So we just use this existing technology to carry our SDLS frame. And so we have done this integration and using actually very common hardware. On the SDLS side, as I mentioned, we build 2 extended procedure, and you can see on the green part is session management services and the publicly infrastructure service. So those 2 are 2 new extended procedure which we designed and developed and implemented ourselves with a set of functionality now here depicted in green. And then of course we had to rely to the existing SDLS, and for that we implemented, again in green, few functionality to be able to run actually our demo and execute our implementation of those 2 extended procedure. And for the demo, as I mentioned, we are using very standard component and existing devices. So we are using this VHF radio. On the left, you have basically the ground station, and station 2 is the balloon or satellite. And we are using a Raspberry Pi and Linux operating system as an onboard computer, which is then connected to our device, number 3 in both setup. And then we have a GPS on both sides and sensor, for example, thermometer, pressure, humidity, and a relay also on the balloon side. But now, unfortunately, due to COVID, we had to cancel the real balloon launch, so we're planning to launch a strato balloon. So we resorted to doing this demo on the ground. Of course, as you can imagine, the encryption per se works on the wireless link, whether the wireless link is horizontal on the ground or whether it's a vertical into space or stratosphere. So there is really no difference in that. But of course, it would have been nicer to have a real balloon flying. So today, the demo that you're gonna witness is gonna be run on the ground. And for doing this, the only trick we had to implement is that since the GPS will always give this level altitude and not moving into the air, so we are going to replace the GPS with a simulator, which is providing coordinates to our software, mission software control, which believe to be flying, so have a different altitude and hence doing different kind of procedure, but in the reality is on the ground. And this software that we built to replace the GPS, of course, is collecting real-time data from different sites, meteo sites. So we collected different at different altitude, different speed and direction of the wind, and we plotted. So when the mission starts, we plotted the new trajectory, basically, of the balloon, and those coordinates will be the one that we will inject to our mission software. Finally, we see that we definitely want to continue to work in this sector, meaning further developing the CCSDS protocols and definitely SDLS, or expanding toward other protocols, and again using our HSM, which actually we want to expand. So we want to add new functionality to the HSM and implement it, of course, in the FPGA. And in the future also, one very nice possibility would be to integrate software-defined radio, which runs on FPGA, with our encryption. So we would have actually in a single ComSat module built around an SDR, we could have our SDLS hardware implemented in cybersecurity, let's say, end-to-end encryption inside the same block. So this would be an interesting product both for space application and also for drones. And very interesting is this new contract we are negotiating, we are about to sign with the European Space Agency and also with another company called CGI Estonia, so a local company. And together we are going to actually implement something using the OPSAT satellite, which is already orbiting. And SKUDO in particular is going to, of course, move our technology to the satellite, which has already an FPGA. So we are literally going to upload our HSM to the flying FPGA chip, and we are going to provide our HSM functionality as a service. So anyone developing, for example, NMF, which is a framework available on the OPSAT, anyone developing an application for that framework, for example, CGI Estonia is going to do it, they can use our functionality from our hardware chip in a transparent way. So they're going to use this nanosat service platform, and they're going to make software call, and we are going to provide the crypto functionality through our chip. So this is part of the new contract that we're going to implement. And another part, of course, we're going to demonstrate our PKI end-to-end hardware-based encryption when the satellite is connected to the ESOC in Darmstadt. And now you're going to see a live demo of what I presented to you, and I hope you will enjoy. Thank you. Hello everyone, let's have a quick demo about our technology. Given the limited amount of time, I have to try to compact a lot of information, so please bear with me. Today we're going to demonstrate our technology connected basically to potentially to an air balloon, which now we simulate with some electronics, and all the demo is actually running on the ground. So we have a ground station and a simulated balloon station or satellite, each of them implemented basically by a Raspberry Pi. You can see in the picture the actual hardware. So you can have a Raspberry Pi, is the red one, and connected to our encryption chip, it's just the green device below this red box. And then we have various sensors and GPS units. Plus, you see on the right side VHF radio that will be working and provide us the connectivity, the wireless link that we will be using for this demo. We are using actually the 144.8 megahertz ham radio band. And inside this onboard computer, basically the Raspberry Pi is our onboard computer, we are going to have our software running in there, which will connect with the packet radio modem implemented through this radio, VHF radio, and then we'll talk to our hardware chip. And the hardware chip will provide all the encryption functionality needed to implement this demo. And this will be, of course, end-to-end, so the same equipment will be on the ground and same equipment on the balloon, let's say on the satellite. The only difference is we have a bit few sensors on the balloon side. And these radio are actually not full duplex. So one little trick we have been using is that we use a sort of so-called time division multiplexing. So you see on top of the picture this band that represent a different kind of time slot we're actually assigning. So we divided a minute of communication in 60 seconds, and we have 12 slots. So exactly every minute at second t equals 0, we have the first slot. Every slot lasts 5 seconds, and what we do is that first start the balloon to send down, so at t equals 0, then at t equals 5, we have the other way around, so the ground station is able to send. And then after another 5 seconds, the balloon is able to send. So this way we have hard-coded actually assign this time slot to the two different stations so that they will not overlap when they have to talk to each other. So this is very simple but works very well. And we are using the APRS network to send this data, and typically this runs actually over AX.25 protocol, and typically it takes on one single transmission we can transmit around 250 bytes of data payload, and inside this payload it's exactly where we put our SDLS TCTM frames. So we're going to pack them inside the AX25 frame, which is our physical layer that runs over this VHF function. And then we're able basically to communicate, send a telecommand, and receive telemetry data from the satellite or balloon. And all the information, of course, are end-to-end encrypted, again using our HSM and using our modified SDLS protocol as we saw it before. We have also a functionality called over-the-air rekeying, the OTAR. So we are actually able to generate different keys on the ground and upload them to the balloon in a very safe way, of course using our authentication and encryption provided by the hardware device. Now we will see then quickly the different windows in the coming in a few seconds. This will be the main one representing the graphical user interface of our, let's say, mission software that runs on the ground. So we are able basically to generate user credential, and then we are able to sign it and then exchange the public keys, so deploy the public key infrastructure to the satellite or balloon, and from there, once the PKI is distributed, so the certificate are signed and exchanged, then we are able to establish a secure channel, run then the SDLS on top of it, and then execute different commands as mentioned before. So we can send telecommand, and we can receive telemetry, and we can use different security association SA index that will represent actually the different index of this SA, and we can activate encryption, will be AS, and then we can have also authentication, activate or deactivate. So depending on this operation we will do on this graphical user interface. So this is just to get you familiar with what we will see now. At the moment, the balloon actually is moving. You see already the altitude changing. So the balloon is following now the simulated coordinate. So the balloon is effectively flying, and then we will see also graphically. Now I walk you through very quickly the main part of the demo, which is how we use the credential, how we deploy the PKI. So first of all, we have to generate basically the credential for a new user. And the initiator is the ground operator, and the receiver is the balloon site. The balloon, of course, must recognize the user, and the user must be able also to prove his identity. So we generate now this new long-living identification key pair, and the one of the certificate authority must sign it to indicate the trust. So we need to sign, and we can do, for example, as now with the hardware, this signed hardware interface, which basically means using the HSM manufacturer certificate authority. So let's say SKUDO company is a manufacturer of the HSM, so we'll sign this, and this will be needed to verify the authenticity of the chip. Then we have a sign authorized, which will be used for sign with the mission operator CA, and then we could test with a sign unauthorized, which will demonstrate that the user is not recognized. Now I have to skip various of these tests because it will take 10-15 minutes more, and we don't have enough time. So once it is done, then we can request the deployment. So in here, when we pass the request deployment, then there is the initialization of the extended procedure. So here we start to work with the SDLS part. And the balloon can only recognize at the beginning the user sign with the manufacturer CA. And because there are no other certificate other than in the HSM, then there is nothing else to recognize, basically. Now, the operator CA will not be recognized until the PKI is completely deployed. And any unauthorized CA will never be recognized because nobody actually uploaded the certificate. Again, here you have a lot of communication ongoing. Now, you don't hear anything because I'm switching off the radio, but I will let you hear very soon. So right now there are messages going up and down in both directions until, as you see, the identity is verified. And when the balloon is just started, we assume it's just, let's say, manufacturer. So there is no mission operator data and no other keys, completely empty. And it's important actually to create this balloon identity that will be recognized by the mission operator. In fact, now the first step was to do the PKI deployment and asking the balloon for the credential. So this will be basically including generating a new key pair on the balloon, and then HSM reporting the serial number, and then exchanging basically this information. Now we do a connect. Now there is a request to connect. And this can be done only after, as we see, we authorize the user with signing his ID. And because the session negotiation must provide balloon identity, the connect can be performing only after PKI signature and deployment step, so not before. And in fact, we have the session is rejected. So this is just to demonstrate. So now we have to do the sign and deployment first. And at this stage, now we need to pass the public key of the operator CA to sign it. And this is done in embedded, let's say, authorized certificate authority. We click, in fact, this sign and deploy, and now the balloon key is signed and sent back to the balloon public key is signed and sent back to the balloon, including the operator CA public key certificate. And then when this sign and deployment is done, the balloon can recognize the mission operator users, and the mission operator can validate the balloon identity by checking the signature of the balloon public key. Of course, the operator CA certificate is public, and so it's known to every participant. This is a very standard, let's say, PKI steps. So at this stage, in fact, the PKI is deployed, it's confirmed. Now we are able basically to have a strong authentication between the two parties, so ground and balloon, because the ID has been exchanged. So now let's say we want to use this demo, and we can actually generate a new identity, which is now the user. A user on the ground, an operator, want to access the balloon or satellite. So he generates this new key pair, and then we need to sign, let's say with the hardware certificate, or sign actually with the authorized. And then we connect. So now we are able to connect to the balloon, which before it was rejected. Now, while this is happening, actually, I can even make you listen the command. So I'm switching on my monitor VHF radio, and then now you will hear this was one packet ongoing. So every more or less 5 seconds we have messages. As you know, this is using AFSK, so it's the audio frequency shifting keying, the modulation that we are using. Now, we can see now the connection has been established. So we have actually a secure connection. Now we can actually do, for example, a author. So we select the author. So this is now a telecommand, and we send. So this generates actually various PDU. So there will be many messages that are queued and sent. Okay, so now we have the confirmation. So they say selected is 1, and we uploaded 12 keys. So we send this batch of keys to the balloon or satellite. So now we can actually start to use them. So for example, we can actually activate the encryption. Okay, now as we can see, the operation has been performed successfully, and now the encryption is activated. So as reported in here, the AES now is active, and of course we have been consumed one key from the batch. Now we can consume another key, for example, to activate the authentication. So we can just send the telecommand to rekeying the activation, and this again will send I think 8 PDUs, and will take around 1 minute and 1 minute and 20 seconds to perform. Okay, now as we can see, the authentication has been activated, and SA index has increased, and one more key has been used. So from this moment on, we have full encryption and authentication active. So all the data, telemetry data that are exchanged and they are received, they are encrypted and authenticated with STLS, with our extended procedure. And now a quick one, we can actually send a command. For example, we have a relay now on the balloon that was supposed to cut the balloon loose and recover the payload in case of emergency. So we are going to see that we send this telecommand, again encrypted. Here we can see cut loose has been issued. Now, you can't hear probably a click, but basically there was a relay which has been open for a couple of seconds, which is used to trigger a hot wire to burn the cable and release the balloon. So this is another example of telecommand that can be sent to the balloon. Okay, so now I think this will end this part of the presentation. I don't have much time left. I'm going to show to you now some very quick graphical representation of the balloon. Okay, this is actually live, so you can go to the site aprs.fi, which collect all the data coming from the APRS network. Now, in this moment, I just isolated our balloon, so which is transmitting using a specific code sign. Here is Tallinn, so we are in Estonia. The balloon has been actually launched with a simulated coordinate by the Vormsi island, and this is the actual path that is following, and it's sending about updated, I think, about every minute the position. The balloon is actually moving. So here you see this has been just updated. So there are the information, and at the moment is on an altitude of 12,000 meters, and it will continue, and this is the direction that he is going. So and this is actually the graphical representation of the trajectory. So this is basically a file which has been generating using the different real-time metadata. So we have the takeoff, then there is actually a rapid change of altitude, and then the balloon will burst and land. So this is the predicted balloon landing, and this is the balloon launch. So we can see in three dimension. Okay, this ends my presentation. Hope you did enjoy, and I'm available, of course, for any question. Thank you very much.
Thank you.
Simak is dialing in from the US. He is the co-founder and CEO of Kayhan-Space, holds a PhD in aerospace engineering from the University of Colorado Boulder, and has supported various NASA and JPL missions. And he's going to discuss his current new startup, I believe, if I'm correct. So,
awesome. Yeah, thanks so much for having me. Do I have permission to share slides?
Yeah, I gave you.
Looks like my share.
Yeah, excellent, thank you.
Okay, thanks so much. Yeah, that was easier than I thought. So, thanks so much for having me. I'm Simak Hesar, CEO and co-founder of Kayhan-Space. And what I'm going to talk about today is what I call it, making space flight safer, past, present, and future. So, quick look at, what has been the history in the sort of space debris environment, what we are doing today, and what we see is going to happen going into the future. So, just to set some, set the stage in terms of definitions. When we talk about space situational awareness, it's really, and in the DoD settings, it's sometimes referred to as the space domain awareness with some additional components, but really the comprehensive knowledge of resident space objects near Earth space environment. The comprehensive knowledge that is needed to basically protect the space assets that are in orbit from space debris and other objects that might provide or present threats. So, space debris can be referred to both artificial as well as natural. But obviously, when we talk about the SSA, there's not much one can do on the natural item, debris, but really the focus is the artificial debris, and those are the ones that have caused issues and damages in the past, and continue to cause, to present threat to space operations. So a historical overview of the space debris problem. Obviously, this plot is a little bit dated, but you can see that quick, rapid increase of the space debris population in orbit around the Earth. The recent estimates they vary anywhere from 500 to 1 million pieces of debris object. Obviously, these are estimates. We can only track today about 30 or so, 27 to 30,000 pieces of debris object in orbit around the Earth, and hopefully with added tracking capabilities, that's going to increase. But that's just the tip of the iceberg that we can see, and there has been collisions in the past. I've highlighted few here, and obviously the Haiyan 1C weather satellite and the satellite missile test that contributed to many pieces of debris objects. And one thing I want to, and obviously the Iridium Cosmos collision, those were really high profile events. One thing that came to my interest is that there was another collision in 2013. One of the Haiyan C debris that hit the Russian Blitz satellite, laser range satellite, that kind of highlights the fact that the space debris objects stay in orbit for many, many years. They can fall into basically stable orbits and stay there for hundreds of years, and cause threats and decommission satellites. And obviously, recently there was an anti-satellite test, weapon test by India, and and obviously there are more examples like this. These are just some highlights. So really, like I said, the estimated 1 million pieces of debris objects. Obviously, these objects travel in orbital speed, depending on the geometry. The kinetic velocity or the conjunction velocity can be 10 times faster than the speed of a bullet, or even higher. Depends on how these two objects come close to each other. And like I said, a single collision can generate thousands of more pieces of debris object, and could render an entire orbital regime unusable. And obviously, this has been depicted in the pop culture in movie Gravity, not really accurately, obviously, but Donald Kessler predicted, once the density of space debris goes above certain limit, the chain reaction is quite possible. And in the past few months, we have seen this worrying trend, right? So here I have highlighted two high-profile events that happened just this past April, and this highlights the fact that we really need to be cognizant of this problem and resolve it. And one of these events involved the life of the astronauts as they were going, ascending in their trajectory, which turned out to be at the end a human error, which really highlights the fact that there needs to be better systems and processes in place to detect, avoid, or prevent these type of events. So why should we care about this problem, right? And obviously, everybody in this conference, you are involved in space, but really, the problems that happen in space do not stay in space, and they affect our life here on Earth. So, and the way we look at Kayhan, we look at space is a really infrastructure that supports trillion-dollar industries, from transportation to supply chain, air travel, national defense, even food production, agriculture. So, there was a report out by NIST, National Institute of Standards, that said that if there's a loss in GPS service, there would be a 1 billion loss in U.S. economy impact per day. And that report went on to say that if that outage happened during the harvest season, that amount of impact would be actually double the amount. So we can quickly see that how intimately interconnected we are to space on every day of our life as we are working, as we go after living our lives. Everything we do really depends on space, from food we eat to when we are looking for directions, or even if we want to live safely and from the national security standpoint. So what is the current trend in the space industry? And there's the thing that kind of worries us, right? So just to give a context, since the dawn of space age, humanity as a whole, we have launched about a little bit more than 8,000 satellites to orbit around the Earth, which has contributed to this 1 million piece of debris object, small and big. And I'm sure everybody knows that, with the launch of mega constellations, in the next decade alone, we are going to increase the number of these objects by, almost tenfold. Obviously, there are different estimates, 40 to 60 in the next decade. And, there has been estimates also of up to even 100,000 satellites being launched to orbit. So you can quickly see the scale of the problem that is increasing very rapidly. Not only that, as I said, in this graphic on the right, it shows that, today we are reliably tracking about, space surveillance network in the US, and obviously ESA, as well as, the ESA debris office, space debris office. They're tracking about 20,000, 23 to north of 20,000 debris object that we have custody on. And with the with Space Fence coming online, that is estimated to increase by 100,000 objects that we can track. Depends how many we can get custody on. Reliable tracking. And the problem it brings, it causes, is that the processes that satellite operators today have to contend with the space debris problem is not scalable. It is prone to human errors and delays, as I discussed earlier in my remarks. So, that is, we believe that that's not a sustainable process, and both the governmental agencies as well as the commercial industry need to step up to address this problem. And I'll go through what we think the right approach is in basically both leveraging the industry and technology as well as policy. So what are the technological solutions? So obviously, first thing first, we have to avoid, and we have to efficiently and in a scalable manner avoid upcoming conjunctions or collisions of debris objects. And that is one of the aspects we think the technology can help tremendously, and that's where exactly Kayhan Space comes in. And what we have built and the support that we provide to commercial satellite operators is autonomous collision detection and avoidance system, a truly autonomous system that enables the operators to be able to scale their capabilities or their constellation, and without having to scale the manpower that needs to constantly track these objects. So that is one of the focuses. The autonomy and scalability, we believe, is one key driver of improving the way we can address this problem. Another thing is I talked about Space Fence, improved tracking. The more we look, the more we see. And, we right now, today we can track objects reliably, objects on the order of 10 centimeter or larger. Obviously, improved tracking will reduce the size of the object that we can track, increase the number that, as I said, creates its own problem that now we need automation and scalability to be able to contend with those all those conjunction alerts that we are going to receive as operators. But also we have to look, right? We have to improve tracking to be able to track, especially objects that are smaller, that are poorly tracked, that have large uncertainties that cause issues operationally. Other processes that we think that technology can help, the other approach is mission extension. This is obviously have been demonstrated by Northrop Grumman, the mission extension vehicle, MEV mission 1 and 2, that demonstrated that it is quite possible to send in spacecraft and refuel other spacecrafts. And, majority of the time, spacecraft become decommissioned, as you know, because they run out of fuel. So the more we can extend the life of existing missions, the less need there is to launch new spacecraft. So that is another aspect that we think the technology should focus and can help to address the problem. And finally, as you know, there are companies that are demonstrating capabilities of actively removing debris objects. And obviously, we cannot remove every single piece of this million piece of debris object. That is simply not feasible. However, we can remove problematic debris, right? We can remove debris that have high rate of conjunctions. They are in, large rocket bodies that can cause serious damage, and they are non-maneuverable objects, and they could be in, elliptical orbits that are not very easily, predictable compared to, circular orbits. And they can come in a very high relative velocities due to their, orbital orientation and the size of their orbit when they come in close contact with other objects. The technology should and I believe will be used to perform this functionality. Just a quick note on our on the Kayhan side. As I mentioned, we have built a truly autonomous collision detection and avoidance system, which is scalable, and the goal is to essentially reduce the response time by, in fact, 95% reduction in response time is a conservative estimate. We have seen much faster response times. And the goal is to eliminate human delays and errors from the critical path of response to a potentially dangerous event. And we really believe that is the only way that we can contend with this growing problem, because as long as the technology is used to help operators make decisions, that is where we can utilize it to aid satellite operators to focus on their core missions and not have to scale off manpowers and team to do analysis manually. And really, we believe manual processes are not scalable. Yes, that is what we focus on the decision support really for the operators. But what we also believe at Kayhan is we truly believe that technology is not only technology is not the answer. In addition to technology, technology can be helpful, and obviously, as I just talked about, there are many different aspects that the commercial space industry, as well as obviously government, can perform capabilities to mitigate the problem. However, the technological solutions can be, should be accommodated or accompanied by regulatory solutions, we believe. And policy has to be done. There was in fact a hearing, Senate hearing here in the US yesterday that a panel of industry representatives, former director of Department of Commerce, research representatives, were on the hearing on this panel for space traffic management and space sustainability. And the message was that, yes, I mean, today the commercial industry has the technology to mitigate this problem, and we do need common sense regulatory framework. And, you know, obviously, I'm sure many of you are familiar with the NAPA report and the Space Directive 3 that came out basically in the US, but I know that there are similar initiatives in the Europe and other parts of the world as well, that the idea was that, you know, to have a central entity such as Department of Commerce to be responsible for establishing what's called the open architecture data repository, that it's a central place that collects data and provides space safety and sustainability services to public and, you know, to operators, to research community as a whole. And, you know, we fully support that. But that's just US. What is about international cooperation? And we believe at Kayhan, our view is that international cooperation is key. Obviously, you know, the space does not belong to any particular nation. And, you know, a safe, sustainable space is a win for everyone. So, you know, for instance, the space sustainability rating that has been initiated on the ESA side from the Office of Space Debris Office, and I know that it has had quite a bit of traction on the US. We fully support that type of initiative to really put some of the responsibility. Yeah, thank you. Some of the responsibility on the operator side to basically make sure that they have a sustainable process. And obviously, United Nations has a role to play. And what we believe is that, you know, obviously, you know, the Chinese rocket deorbiting in a couple of, you know, 2 months ago, that really, you know, highlighted the problem, right? That there has to be international cooperation with Russia, China, and other nations. And I'll close my remark. You know, I was researching about this topic, and I came across this quote from this website that early years of air traffic control, and I see a really good analog here, because, you know, in early years of air traffic, you know, there was not at least in the US, there was not you know, overarching regulatory frameworks, and which caused in mid-air collisions, and you know, interestingly, Department of Commerce stepped in to start some regulatory framework. And I want to leave with this thought that really today in space, in commercial space industry, I believe that we are at an inflection point, and I do hope that as an international community and as an industry, we make the right choice to make sure that the space stays sustainable and vibrant and thrive. So with that, thanks so much. I am happy to answer any questions if there is any time.
Thank you, Dr. Simak. That was really interesting and valuable information. Any questions on the floor? Dr. Hesar, sorry. Sorry, Dr. Hesar. Any questions on the floor? John, any questions? We have a question over here.
Okay. Thank you very much. Very, very interesting. I have actually 2 questions. The one is, if you had better data, would you purchase better data? And the second is, could you describe a little bit how your kind of product look like? I mean, how do you deliver your product? So can you make it a little bit more tangible? Thank you.
Absolutely. Yeah, thanks for that question. Yes, we, in fact, the process that we have built a data agnostic platform. You know, our main source of data comes from the Space Force today, but we get data from the owner operators themselves, as well as third-party providers. And yes, to answer your first question, better data, more accurate data is always welcome, obviously. But it's just not data, right? It is also better algorithms. So better predictive algorithms that we work on, better prediction of the space weather, for instance. That is, I guess, my question to your my answer to your first question. Secondly, we focus on automation, and the way you access our platform is mainly via APIs, and we integrate into the workflow of satellite operators. It's better if we detect the conjunction, we push notifications, and if there are certain thresholds that are met that we work through, we go ahead and generate avoidance maneuver trade space that are consistent with satellite operators' constraints, physics-based and non-physics-based constraints, and that is automatically generated and delivered to operators.
Thank you very much.
Does that answer your question? Yeah.
Yes, thank you very much.
We have one final question from the online community. John?
Yes, certainly. It's from a Mr. Bill Dye. Suppose there is a bounty system to reward anyone who safely removes space debris. What technical challenges do you foresee for the referees who must determine the bounty price on a given piece of debris? Any other challenges?
Yeah, that is
nice,
a very
easy
good
question.
Yeah, we can talk hours about that. So I think, I don't know if I can answer that question directly, but I'll try. And really, what I believe and truly believe is that, and I mentioned that about the hearing, and I believe that anything we do, any regulations, the regulatory framework that we put in place has to be informed by research and science and physics, right? And we don't want to just put regulation just for the sake of putting regulations. Things that make sense. And I suppose in your particular question, the objects, we know, based on the tracking we have, there are certain objects that are more problematic than the others. And obviously those will be the highest priorities if we have the reliable technology to go and grab them and deorbit them. So I think that will be my answer.
Thank you very much. Okay, once again, thank you to all the speakers. Shall we applause for... You had to wait a long time, and we really appreciate your patience. Okay, I think we're going to